I think we got a really nice location. Thanks to everyone that submitted the paper. Thanks to the reviewers, the program committee, and to everyone that was involved in the organization, in particular to Joseph Tassarotti. I think we have an awesome program. So we're gonna run from 9 a.m. to 6 p.m. We have totally 18 talks over 5 sessions, and we cover applications of Daphne in industry, academia. We talk about testing, comparison with other tools, proof at scale, probabilistic programming, and code generation. Before we begin, let me just make a few organizational remarks. So talks are going to be 15 minutes plus 3 minutes for questions. If you have a question, you're just going to queue up for the microphone here. And yeah, if you're a presenter, please introduce yourself before the session, just a few minutes before that. Finally, toilets are on the right, I think for men, and on the left for women. And after the workshop, we were thinking to hit maybe a local pub, so everyone is welcome to join. Finally, there have been a few points that the organizers asked me to make. So there is the point that currently COVID levels are low in London. Nonetheless, there are hand sanitizers available throughout the building that you're invited to use. Secondly, there is the Maxwell library on the first floor that is set up as a cafe, not just throughout the breaks, but throughout the whole day. And finally, the building has a rooftop that I'm told has a really nice view. So please check it out. Unfortunately, it's closed today. Yeah. Okay, so that's that. I'm just going to hand over to Rustan for a few moments, and then we're going to start with the keynote.
Good morning, everyone. I am really delighted to see so many of you here and to see such a great program for the first Daphne workshop. It is this month, it's been 16 years since the first bits of first lines of source code for Daphne came together. So it's been quite a while, and it's for most of that time the project has been active, but it's never been as active as it is today, both in terms of users and contributors. I'm delighted to see so many contributors overall, and the topics actually today are going to be quite a variety of things. I think that when Daphne started, the idea was just to have actually to begin with, just some little toy example that you could run through and test out dynamic frames. And we know that Daphne does a whole bunch more today, from testing to quantum things to really running production things at Amazon as well. So with that, one more thing. It's great to see so many, and with so many papers, and we have we're going to go, I think, longer than any workshop. And so with that, you would think we would have contributors from everywhere. But there are very few women in the room. There are many more women contributors to Daphne than the room represents. So next time around, please make sure that we have an even larger representation. So thanks, Stefan. Thanks, Joseph, for organizing, and hope you all enjoy it very much. Thanks.
Okay, thanks, Rustan. So the first session is going to be on applications of Daphne. And we are lucky to have Tej Chajet for the keynote. Tej is an assistant professor in computer science at the University of Wisconsin-Madison. Before that, Tej did a postdoc at VMware Research and a PhD at MIT. And today he will tell us about the role of Daphne in the development of DaisyNFS, a verified concurrent file system.
All right, thanks, Stefan. So, hi, my name is Tej. Today I'm going to talk about a line of research that culminated in a verified concurrent file system where the proofs largely use sequential reasoning within Daphne. This is going to be a little bit of an unusual talk in this workshop in that about half of this proof was carried out using Coq and Perennial and Iris and this very heavyweight infrastructure, and the other half is carried out using Daphne. And a lot of the project was about combining these two. But I'm going to talk about both pieces, and I'll talk about some interesting details about the Daphne side of this project when I get there. My research is broadly about system software, and file systems are just one example of this kind of software. Even if you don't directly interact with these kind of systems, this is the software that powers applications on your phone, your computer, and the servers running all the cloud software that you use. A couple characteristics of system software make it particularly challenging, and are why we might want to apply verification to it. First, systems export an API that many applications use in slightly different ways. And second, they run in a complex environment that has concurrency, crashes, and they have to directly interact with devices. While testing has been hugely successful at making systems reliable, of course, we want to use verification to make them even more reliable, and to be able to cover all of the uses that an application might make, as well as all of the possibilities at execution time that come from concurrency and failures. And despite, and maybe I don't need to say this in the talk, but I think it's always worth reminding ourselves that despite their widespread importance, bugs in critical system software are still routinely discovered. And systems keep evolving. As they accumulate features, they'll also keep accumulating bugs. So my vision is to use verification to build reliable systems infrastructure. And in this talk, I'm going to focus on one piece of that, which is the file system. So whenever we do verification, we have three components. We want to take some code, a specification of what the code does, and some sort of proof that shows that the code meets the spec. And that something like a proof assistant, in this case, there's going to be two proof assistants involved. One is going to be based on the Coq prover, and the other one is going to be Daphne, are going to show that the code actually meets the spec using the proof as kind of a hint. In recent years, systems verification in particular has kind of turned a corner with a number of systems verified in just the last decade. These projects have all expanded the kinds of systems that we can tackle with verification. For example, reasoning about distributed systems. In this talk, I'm going to talk about DaisyNFS, which is a verified concurrent file system. It's partly verified using this infrastructure called Perennial. It's partly verified using Daphne. It combines PL and systems techniques to be able to stitch together the entire proof. So DaisyNFS, as the name kind of hints at, is a verified NFS server. NFS is the network file system, and NFS is a good there's a few reasons why NFS is a good target for verification. So first of all, NFS is widely used by many people, and it's widely supported with many servers and clients of this API. Which means that if we have a verified implementation, there's many clients that can use this. For example, Windows, Mac OS, and Linux all have NFS clients that can connect to an NFS server. And second, in the pursuit of good performance, NFS servers and file systems in general are sophisticated and concurrent, and which leads to a lot of bugs. And finally, because this is a file system, the bugs are particularly costly because they can lead to issues like data loss, which you just sort of can't recover from. There's no coming back if you lose your data. So DaisyNFS implements the NFS API. At a concrete level, DaisyNFS is written in Go. Part of that is directly written in Go. Part of it is written in Daphne and then extracted to Go code. The whole thing links together, compiles to a server binary, and then clients interact with that server over the NFS protocol, which is this standard, there's an RFC for the NFS protocol that describes how you're supposed to interact with an NFS server. So why do we use Go? Go is compiled, efficient, and has very good support for concurrency. And on the Perennial side, it was good for building the tools that we needed to support the verification infrastructure. I won't talk about that in great detail, but there's good reasons why we used Go. What makes DaisyNFS special, of course, is that it has a proof. Roughly speaking, what the theorem says is that the server correctly implements the NFS protocol in a linearizable way. So every operation is going to execute atomically, according to our specification of what NFS is supposed to do. And also, if the system crashes, your data is always going to be durably stored. So regardless of when the server crashes, when you restore the server, you get back all of your data. There's two core challenges in verifying a file system. The first is that the file system is generally expected to keep your data safe, even if the system crashes, right? So even if that server crashes, which might happen due to something unavoidable, like a kernel panic or a power failure, or your laptop runs out of battery. Even in this situation, after you reboot, you expect your data to still be there. And the second big challenge is concurrency in the implementation. So just as concurrent software is going to be hard to write correctly, it's also going to be hard to verify. And to illustrate both of these challenges, I'm going to give an illustrative example of a little piece of something that a file system needs to do and what goes wrong with concurrency and crashes. So this operation is the remove operation, kind of at a very high level, which deletes the file named name inside the directory pointed to by dino. This operation has three high-level steps. So first, we're going to unlink the name from the directory. And then we're going to want to free up the space that was formerly used by the file. So we're going to go look up that file, and we're going to go free all of its blocks. So there's a few things that can go wrong. So the first thing that could go wrong is that the system could fail between 1 and 2 and between 2 and 3. So I'm going to talk about both of those. So first of all, if there's a crash between steps 1 and 2, imagine that we've durably stored this unlink, but we have not gotten yet to freeing the blocks, then this crash is going to leak all of F's blocks. So after the reboot, F no longer points to these blocks, so they're kind of dangling. You can recover those eventually, but this is still not a great situation to be in. And then the second bug that I'm going to illustrate with this example, suppose we don't have a crash, we just have concurrency. And in the middle of these of steps 2 and 3, another operation comes along, and it adds some additional blocks to the end of F. Because we separately got the blocks of F and then we freed them, those blocks will never be reached, the file is deleted, and again we have a resource leak. So we'll never get around to freeing those blocks unless we do some sort of global recovery. Now, in these examples, the only thing that went wrong is that we have a resource leak. But these are just meant to be illustrative. In most operations of the file system, there's multiple operations that up to multiple data structures, and crash and concurrency bugs from interrupting and issuing part of these operations can be much more serious than just leaking resources. We might return the wrong user's data if we get confused about permissions. We might lose user data permanently rather than just leaking blocks. In a verified file system, we want to systematically guarantee that none of these problems occur. So the overall approach that we take in this project is in order to scale it to something like a file system, is to separate it into two parts. The first part at the bottom is a transaction system that guarantees atomicity. This is going to essentially address these key challenges of crashes and concurrency in a generic way. And then DaisyNFS on top is going to implement the actual logic and application logic of the file system entirely using transactions. So the transaction system is going to address these key challenges, but as a result, it's going to use more heavyweight verification techniques. And on the other hand, DaisyNFS is going to enjoy sequential reasoning, and that's going to allow us to scale up verification to something this large. We need to just write a lot of code to be able to make a file system actually work. And there's a careful specification for what GoTXN does to be able to bridge the two, right? Because we're combining two verification tools, we need to argue why the result is still correct, despite combining the results from two different tools. So I'm actually going to start with a specification that captures what transactions in GoTXN do, and then I'll turn to both sides of this specification. Actually, let me pause for any questions at this point. Yeah?
Oh, it's very clear.
Okay. No questions. Yeah, feel free to stop me for questions, by the way. I can dynamically tune how long the talk is. Okay, so GoTXN implements a transactional API on top of sort of a raw disk API. The caller is going to take a whole bunch of reads and writes of individual objects, say implementing the remove operation, inside begin and commit. And GoTXN is going to guarantee that that code appears to run atomically. And that's going to be with respect to both crashes. If you crash and reboot, either all of those operations are persisted or none of them are, and also with respect to other threads. Other threads observe the entire transaction or none of it. The transaction system specification starts out by saying, what behavior do we expect to have for each transaction? So this is just a spec level of what begin, write, and so on should do. This part is fairly intuitive. We kind of can easily say what read and write do. The execution of this transaction is going to be more complicated because it has intermediate steps for all of the individual reads and writes. And actually, the execution goes down all the way, when we're modeling the execution of the transaction system, read and write have a bunch of smaller atomic steps corresponding to sort of every line of the Go code. So what we want to say is that every actual execution should be allowed by the specification. This would be relatively simple if we just had sequential transactions and nothing else. But we also need to handle crashes and concurrency. So to specify crash atomicity, we now need to allow two possible specification behaviors, even for this transaction. Because we say it runs atomically, if the system crashes while running the transaction, it's possible that it becomes a no-op, right? If we crash too early, the transaction can't run. There's a lot more executions. Now we can stop at any prefix of the sequential execution. And we still want a refinement-like property where every crashing execution has a corresponding allowed specification execution. It'd be rather difficult to prove this by just directly reasoning about crashes at any point. We instead want to do something a little bit more systematic. So the way we're going to do that is we're going to write specifications for the individual operations of begin, read, write, and commit, rather than having to do some sort of consideration of all possible transactions. So I'm going to use this transaction as a running example for the talk, which copies a block that it reads from address 0 to blocks 1 and 2. The first thing that we're going to do to describe the transaction system is it's going to manipulate a logical durable disk. So this is going to correspond to this is the abstract state of the transaction system. So at this level, so the overall effect of this transaction is pretty easy to state, which is I've already given it in these abstract states. The initial state has some block v in address 0, and it's now in addresses 1 and 2. It's implied that the other addresses are not modified. So the first question that we have to ask to be able to give a crash specification to the transaction system is, what should the state of the system be between writing address 1 and writing address 2, right? So remember that the top and bottom are what the transaction system actually exposes. This intermediate state is not going to be the same thing, right? It's going to have buffered something before actually committing it at commit time. What we want to capture is that even if the system crashes in that weird intermediate state, the final logical state is going to be either the initial state or the final one. So the first idea that we introduce is to have an in-memory view of the transactional disk that represents the progress of a transaction. So the idea is that this lighter color represents what the transaction would commit if it were to commit right now. It also is what the transaction reads from if it reads its own writes. It's just like the logical durable disk, but it includes all the buffered writes from the transaction so far. And this in-memory view of the transaction allows us to specify exactly what happens at all the intermediate points of the transaction system. Finally, when we get to commit, the role of commit is to turn that logical in-memory view into something durable. So we can formalize the part about commit that I just said as a specification in Hoare logic. In this Hoare logic spec, we have a precondition saying we have some durable disk that is from the beginning of the transaction, we have some in-memory state, and whatever those two states are after commit, the durable state is going to match the in-memory view. So that's what captures the idea that we persist all of the buffered writes. So this doesn't yet capture crashes. So to do that, we wrote a new program logic called perennial, which extends an earlier logic that only had sequential crashes. So for now, we're going to just add crash conditions to the specification, but note that eventually we're going to have a logic that also has concurrency. So actually, the idea of crash conditions is pretty simple. we're just going to add an additional post condition called a crash condition that says what the states would be if you crash at any point during the body of tx.commit. And in this case, the way we capture atomicity of commit is that the durable state on disk is going to be either the state before this, either the durable disk that we started with, or it's going to be the current in-memory view. If we crash late enough in commit, it's going to have already persisted all the writes.
Ted, I have a question.
Yes.
I understand the specification. I guess my question is, are there commits that are so large that it's not possible to implement that specification? Because, I don't know, you've got to write a gigabyte of data. How can you guarantee that you will either not write any of it or write all of it?
That is an excellent question. So the actual specification does allow commit to error, which happens if the transaction is too big. So our actual transaction system does have a limit on how big transactions are. If we want, we could extend the specification where you had to first prove that your transaction is small enough in order to guarantee that it commits. Or we could extend it with some sort of evidence on failure for why it didn't commit. Eventually, I think there are cases where, so I think the final transaction system actually, the only reason it doesn't commit is because of transactions being too big. But our specification is not precise enough to capture that. Because we're not doing a liveness proof, we're not on the hook to do that at any point. But it would still be nice to extend the proof, at least at this low level. Okay. So far I've given you a specification for what a sequential transaction system would look like. But we also want to capture concurrency. We're going to run transactions concurrently at the same time. So the transactions should still be atomic. So if we're just talking about the spec level, not yet at the implementation, when we run tx1 and tx2 in parallel, we do expect two possible behaviors at the spec level. It's allowed for the system to run those transactions in either order. There's a lot more interleavings at the implementation level because for efficiency reasons, we're not going to take a giant global lock. We're going to allow the implementations to interleave. Nonetheless, each of these should correspond to one of the two orders. And I'm just giving this as an illustrative example. This specification should hold for any combination of concurrent transactions and including multiple transactions in a row on the same thread. So concurrency means that the sequential reasoning that we did before is not going to work. At an implementation level, when we run these two things, we can say that there's a durable disk at the beginning. We can say there's some durable disk after the commit. But this is going to require us to talk about all the concurrently executing transactions at the same time. We somehow want to be able to separate reasoning about each transaction in isolation rather than having to talk about some global set. So we developed a specification that uses an idea that we call lifting to solve this problem. The key idea is that we introduce a logical notion of lifting that moves a part of the logical disk into each transaction. So that first step in this proof or in this specification is a purely logical thing that says that we're going to move ownership of the footprint of each transaction into the transaction. And now, once we have this local view, and of course, if you're familiar with separation logic, this should be quite familiar to you. We are ultimately going to use separation logic to be able to model this specification. Then within each of these threads, we can use a very similar specification to what we had before, because each transaction is only going to modify its own footprint, and implicitly it keeps everything else the same. And that means that when we run commits, we can commit logically the part of the transaction modified, and then return ownership back to some global state. One thing I should say at this point is that it appears like the proof has to move ownership. It has to know ahead of time what the transaction is going to read in order to move the ownership all at once. In reality, this lifting can happen dynamically within the transaction. So you can actually acquire, our system ultimately is going to acquire ownership on demand as needed. It's not going to require that you specify ahead of time what addresses your transaction wants to read. To implement this specification in, Adam.
So I'm just trying to think what this means for the programmer's view of this abstraction and how much of the implementation technique is being built into the specification? Like if you try to acquire a location that someone else has, the spec says you block, or what happens there?
That's a good question. So this specification is baking in some notion of separation already. So this is an adequate specification. Okay, I should say that there's two layers to our transaction system itself. There's one layer where we assume that when you write to an address, you have exclusive ownership over it. And then the layer above that gives you exclusive ownership by acquiring locks, a per address lock.
This feels like a more complex specification than the programmer would want.
Yes. Yes. So
You're suggesting it's a good trade-off to make the verification of lower levels easier?
yeah. So it's a more specific specification that takes into account exactly how we implemented this layer of the system. Not exactly, but I mean, the ownership reasoning, the ownership principles have been baked into the specification. You would need some extension if you wanted to, say, do something optimistic. If you wanted to have optimistic concurrency control, you need a more sophisticated specification at this level. At the end, though, we're going to say that you give the system a transaction and it runs it atomically. And it's going to be a refinement proof that says any combination of transactions is going to appear to run atomically. There's a refinement. That spec would be preserved even if you had optimistic concurrency control. But the intermediate spec that actually reasons about ownership is specific to our ownership discipline. Yeah, another question.
So you don't have concurrent read possibility?
Yes, we don't have concurrent reads. I think that could be lifted. There's nothing fundamental to the approach. It just would be more complicated. We would need to have a read-only notion of, we need to have a read-only ownership notion. That would be like lifting, where you lift only a read-only part, and then we'd have read-only locks to be able to implement that ownership. Yeah. Okay, so to be able to formally model lifting, we use separation logic. It allows us to express the disjointness between transactions in a very nice way. A key primitive is that we introduce this points to assertion within separation logic. It's going to be a custom assertion that talks about our resources. It's not going to be the traditional points to fact that talks about the heap. So we're going to introduce two types of assertions, one that allows us to capture the durable part of the view, and the other for the in-memory per transaction view. And separation logic is going to guarantee that two threads can't both have conflicting views of the same address. Now we can give a specification to commit that looks very similar to what we had before, but instead of having the whole disk and the whole in-memory and durable disks in the precondition, we're going to instead have just the part that the transaction is actually committing. So this is all the ownership that the transaction has accumulated throughout its execution up to commit. And now you can see a specification that looks very similar to what we had before, but the meaning is now that this is now a concurrent separation logic specification, and it allows other commits to run concurrently as long as they have disjoint preconditions. The specification looks pretty simple, but it hides a lot of complexity inside the implementation, where commit is running many things concurrently, and the crash condition, even though it just says this A or B, is hiding the exact moment inside commit where we actually go from giving durably all the old addresses versus all the new values. And actually that operation where we switch from the old state being durable to the new state is not even within the body of the commit code. It happens in a background thread that is constantly trying to commit new transactions. So taken together, we can give specifications to the rest of the API. Reads and writes are actually relatively simple because they're just modifying this in-memory view. A lot of the complexity is in commit. And I haven't shown here the logical operation that lifts a durable points to fact into an in-memory one. It's not actually, it's not a physical operation, it's just a logical one. So again, I'm kind of skipping one step in going from here to the next slide, where this is a separation logic spec for the individual operations. We gather all of this up into a refinement proof that shows that if you have an arbitrary set of transactions, it runs atomically when you run it through GoTXN. So every actual, yeah, Sam.
The question about the commit, the post condition. Can you, after a commit, can you write that if commit succeeded, then do something
You can run more transactions after a commit, yes. But you're no longer within the same transaction. So you're going to lose your transaction, and then you can start a new one.
Yes, but new one is guaranteed. Is the new transaction guaranteed to be able to see whether the old one committed? Is there a way it can check whether?
Yeah. So the actual specification is basically commit returns a boolean saying whether it succeeded,
Okay.
and then the post condition is like, if not okay, then you get back the old durable state, and otherwise you get this post condition.
How can this work with if the actual commit code happens in a background thread and not in the code?
Oh, commit blocks until that thread. The actual commit code does block until that thread. What I'm saying is that if you were doing a linearizability argument, this becomes difficult because the linearization point is not within the body of commit, which for some refinement techniques, that's actually tricky. Yeah, Adam.
So how does the API you expose in Go allow for planning about complex orchestrations of many threads with many transactions and something like you use protocols for Idris for modeling how things can evolve across threads?
Yeah, so the Go API consists of these operations, and you could use concurrent separation logic to stitch together multiple transactions. We tried to do this, and actually that's when we developed DaisyNFS, where we instead switched to Daphne to do the reasoning about the transactions, which greatly simplified things. What we didn't do is something where so you described orchestration between threads. So what you could actually try to do is you could try to have a combination of concurrency control between the transaction system and your own code that maybe shows that a higher level operation is atomic, even though you decided not to use a transaction for the whole thing. We didn't try to do something like that. Instead, we used some careful system design so that every operation really is a transaction. And so you get atomicity from this proof itself.
If I was just running, let's say, a bunch of transactions that are transferring money between bank accounts, classic example,
Yeah.
could I do a proof in your top layer about the bank account total sum of bank account balances always being equal across?
Yeah. Yeah, so you could actually do that proof just using the Daphne approach that I'm about to show. So you could write those transactions in Daphne. You do have to define what it means for the sum to be the same. One way that I've done this before is you can write an operation which, within a transaction, checks all of the bank accounts and sums them up. And you would be able to prove an invariant that this transaction always observes a constant sum.
Got it. And if we had some more complex relational example,
Same thing. I mean, yeah. You could write any invariant. I mean, the file system relies on a very complex invariant over the entire state.
including we could use some Go state if we want.
Yep. That's exactly what the file system will have to do. Yep. Okay, so again, the final theorem for GoTXN is this actually fairly complicated refinement theorem that says you take an arbitrary program that uses transactions however it wants, and it gets a refinement result. All of its transactions are going to appear to run atomically, again, with respect to both concurrency and crashes. Okay, so just to summarize, the perennial logic allows us to specify this crash and concurrent behavior. I didn't talk about the proofs at all, but of course perennial also allows us to do those proofs. And the lifting specification allows us to separate out the reasoning and the specification of concurrent transactions. I think I'm a little short on time, so I'm going to say less about the body of GoTXN and how it's actually implemented. Suffice it to say that there's a reasonable amount of complexity and concurrency within the body of GoTXN, within the implementation. Let me just highlight one slide here. That one of the key components of GoTXN is this write-ahead log. The write-ahead log's job is to do this core task of I have a bunch of writes, and I want them to all happen atomically, but I also want to do this very efficiently. And there's 3 steps in the path of making that multi-write atomic. It's first buffered, then it's logged to a fixed size log, and then eventually that fixed size log, we have to free up space in the log by actually moving it to the rest of the disk. And the cool thing about this write-ahead log is that all 3 of these operations actually happen, sorry, I don't think these annotations are that helpful. Those 3 operations on this slide can happen atomically, can happen concurrently in 3 different threads. We can have a transaction writing to the buffer. We have logging and installation happening lock-free without interacting with each other. Okay, so I'm going to skip all of this and start actually talking about the Daphne part of this project. Okay, so recall that what we actually wanted at the end of the day was a verified implementation of the NFS API, which is going to use GoTXN to make the operations atomic. But we still need to actually implement all of the file system operations and logic. So the first challenge that we first have to solve is we have to formalize the NFS API. Then we need to actually leverage atomicity from GoTXN. And then finally, we actually need to fit all the operations into transactions. For the most part, this is straightforward, but there are still some things, there are some operations which could get very large, and we have to figure out how to fit those into transactions. The first question is what the specification for NFS should be. So we start with RFC 1813, which is the standard that defines NFS v3 specifically. While this document is actually pretty good in the space of RFCs, it is 130 pages of prose, and it's not really specific enough. It doesn't really cover all the cases. So the first step, kind of the standard technique, we're going to define the state of the file system first mathematically in Daphne. It's basically going to be a map from inode numbers to some sort of file contents, and the file contents are going to be either directories or data. And then we write the specification of each operation as a relational predicate that says how the state transforms from the old state to the new state, and also what the return value is. So similar to remove, we're going to give a specification for every operation in NFS. Then the top level specification that we're going to give is a refinement theorem that says if you run NFS operations concurrently in any with any set of NFS operations concurrently, then whatever the code actually does is going to execute. It's going to appear to execute each of those operations atomically and according to those mathematical predicates that say what each operation does. And the proof is actually essentially just a composition of what we prove in GoTXN. The GoTXN proof says you can take that execution, it corresponds to a simpler execution where the transactions are atomic. And then the proof that we're going to do in Daphne is going to show a refinement from this sequential execution to an even higher level specification where each operation is just replaced with a single predicate that says what it does. Okay. So this is what justifies why combining a refinement proof in perennial and the Daphne proof actually results in a correct statement for the entire system. The way we're going to prove the transactions is the standard Daphne approach, actually. We're going to define an invariant that we're going to define some ghost state for NFS, and then an invariant that connects the state of the logical state of the transaction system to that abstract state for the whole file system. Then we'll show every operation preserves this invariant, and then the overall proof can chain together this across multiple operations. The way that the specifications are encoded is using a requires and ensures clause on every operation. In the signature, you can see that we have this requires ensures, and we ensure remove spec as well. You can see that it also has a transaction argument, and the Go code that surrounds this, that connects it to the NFS API, is going to be responsible for starting and committing that transaction. So what we know about its body, we know that its body is correct from Daphne, but then to actually run it, we need to start and stop the transaction. Now, I show the remove operation actually because it brings up an interesting implementation challenge. When we remove a file, if the file is gigabytes in size, then it actually isn't really possible to free the entire thing in one transaction. It's going to require too many writes to the disk. So in order to solve this problem and still use GoTXN, what we actually do is we split remove into multiple transactions. In Daphne, we add a method called zero free space that you can see the specification says it's a valid transaction, but it doesn't change the abstract state of the file system. all this does is it recovers any space that the inode has that it's not currently using. And then in the Go code, we separate remove into one transaction that does the actual logical remove operation, and then zero free space, which is a logical no-op, but physically recovers all of the space from the file. And I think the actual zero free space has to be run multiple times in a loop in case the first one also runs into the transaction size limits. And because this is a concurrent transaction system, we can use the Go statement to run this in a separate thread. So we don't actually have to block remove on having the free space recovered, since the caller is not going to observe the logical effects of that operation. Okay, I'm going to pause there and take questions, and then I'll go through some evaluation results. Yeah?
You're calling FS that zero free space, so directly the Daphne method, or are you calling something that wraps that in a transaction?
Something that wraps that in a transaction. I was a little bit imprecise about this whole thing. Yeah.
On the right, there is that Go code.
Yeah.
So what's the relationship between the Daphne code and the Go code, and how do you kind of, with your overall proof, what's the glue that shows that you really
Ah. Yeah. So we are trusting that we call the operations at the right times with the right arguments in order to relate the DaisyNFS D binary to the proof. What the proof really shows is that if you write an application, any application, using all of the methods of the NFS API, then those operations are going to appear to run atomically and correctly. It's your job to figure out when you should call which operation.
Is there also some sort of, assuming you've got the mapping of the data types from one language to another language? Right?
Yeah, yeah.
The ABI, I suppose.
Yep, so what needs to line up is that we have an axiomatic object in Daphne that says, here's what happens when you execute within a transaction. And then that axiomatic object is going to be replaced with the actual GoTXN code. And the specification for what GoTXN says every read and write and such does has to actually be this a refinement of what we say in Daphne, what we promise to the Daphne code. That's the linking step that is unverified. Right, we're making an assumption about how GoTXN operations run in Daphne that needs to be met by the code. Yeah, anything else? Yeah.
More very basic question about Daphne Go connection. Are you using the Daphne transpiler
Yes.
from Daphne to Go?
Yes, yes.
You have some at least syntactic, it looks syntactically similar, hopefully, Daphne and the Go output, or?
Sorry, wait, we're using the actual official compiler.
Sorry?
We're using the official transpiler.
Yeah, okay.
Yeah.
So you have some pretty good connection, actually. It's not like a model and a different code.
Yeah, so that, okay, I was completely ignoring the, I completely trust Daphne on translating the actual code that we verified in Daphne. What Daphne can't really help us with is the specification that we wrote about GoTXN is just a bunch of axioms in Daphne. And there's a bunch of proof in Perennial about what GoTXN does. Those two have to be connected to each other. And those are not the same code. I mean, they can't be the same code. Yeah.
On this slide, it looks like the Go code on the right you manually wrote, but what I
Yeah.
previously thought you would be doing was to generate that Go code from Daphne code, or to
Okay.
from Daphne code?
So what's generated is fs.remove and fs.zero free space are intended to be the transpilations of each of these Daphne methods. So we do have to write wrappers. We also have to write a decent amount more code to actually write to implement the wire format and to connect to sockets and take TCP connections and all of that. We don't try to compile all of that from Daphne. I mean, I would love to do that. I don't know what that would mean. Okay, so let's see. What do I actually want to talk about? Let me just talk about a small number of evaluation results. So let me zoom out a bit and talk about some high-level results about, especially the interesting lines of code. So GoTXN is about 1,600 lines of code. So this is the code that we actually had to have pretty tricky reasoning about. Whereas DaisyNFS is 3,500 lines of Daphne, of executable Daphne code. What I want to highlight here is that GoTXN required a proof. This proof here is, the proof that we had to do for GoTXN in Perennial was 35,000 lines of code in Coq, whereas the proof for DaisyNFS is about 6,000 lines of proof in Daphne. So even though this is less code, this is kind of a good highlight of how much trickier it is to reason about crashes and concurrency compared to this top part, which is extremely productive to work on, right? And it was really only because of Daphne that we're able to scale up to all the code that we need to be able to implement an efficient and realistic file system, right? So for example, we need to have triple indirect blocks in order to have even reasonably sized files. So I've talked about some of these trusted computing-based aspects so far informally, but I do want to just detail them slightly. There's unverified code, especially the code that connects to the network protocol is all unverified. The specification for NFS is not something that's formally linked to the RFC. This is something where I'd love to have more work on, actually, of treating the NFS spec as its own object and connecting it to the RFC and to other implementations. We also trust that, so I'm going to ignore the third part. That's for GoTXN's code to be connected to its model. And then we also need to make sure that GoTXN, as specified in the perennial proof and in Daphne, match up. I'm actually going to skip all the performance. I'm going to skip most of the performance results. I want to talk about bugs instead. So we didn't find bugs in the verified parts. Don't worry. But we did find bugs in the specification and in the unverified glue code. I want to talk about one interesting one. The proof assumes the caller provides a bounded inode. The reason why I want to talk about this is that Daphne has a new feature that would have basically addressed this problem. So what happened is that our Daphne code takes an inode type as an argument. An inode is a Daphne subset type that's actually guaranteed to be within the range of bounded inodes. It's guaranteed to be a valid inode number. And the Go code just passes a uint64. And this type checks in Go because those two are the same. Now, the problem is that the Daphne code is implicitly assuming that all inodes are bounded because it's assuming that you're going to pass the inode from verified code. But here we have an obligation in Go to actually meet this precondition. Now, of course, I know I should meet all the preconditions, but this was kind of a hidden precondition. There's nothing distinguishing I know saying that it's a precondition. You need to know the definition of the type. So I think now it is possible to fix this in Daphne by asking it to check all of these things dynamically, or to audit where you have preconditions. Okay, so in my -1 minute, I'm going to just briefly show some performance results. I do have -1 minute.
You have plenty of time.
I can go till 10?
Your talk started at 9:10, so you have...
I can go till 10:10. Oh, shoot. Okay, never mind. Then I will not skip this. My bad. Okay, so let me talk about the performance results then. Actually, these are good. These are important limitations as well to cover. So there are a number of features that we cover. There's also some limitations. We do have, as I said, we have triply indirect blocks to be able to have up to 500 gigabyte files. The GoTXN proof has some limitations that I won't talk about too much since I didn't talk about perennial. In DaisyNFS, we don't have symbolic links or access control. And we also don't have paged readdir. I think the first two are just a matter of extending the specification and the proof and the implementation a little bit more. Symbolic links are just another set of operations that have well-defined semantics. Access control is very similar. Paged readdir would be an interesting one to cover. What this means is that readdir is split into multiple non-atomic parts. There's a project called SibylFS that gives a specification for readdir for Linux. And I think it'd actually be very interesting to take that specification and port it over to here. It would be it would still be a non-atomic specification. And so you need to cover things like the iterator being invalidated by modifications to the directory in the meantime. And this is a fundamental part of NFS, right? So you have an RPC that comes in that starts a readdir, and then you could have you could interrupt that readdir by modifying the directory in the middle. That's just a part of the network protocol. Let me do this quick demo, just to show that DaisyNFS is kind of a real file system. So this is a demo recorded from my laptop a while ago now, but it's still from my laptop, where I'm going to run DaisyNFSD. Can you see this at all? Yes, okay. And then I'm going to connect to it using the macOS NFS client. Okay, so I'm switched over to Finder, and I'm connecting to it just like I'd connect to any other NFS server. Then I drag a file in. Just for fun, I'm going to crash the file system by killing it. I promise this does not persist things. This actually crashes it. And then I run recovery, restore the file system. In the background, macOS actually transparently reconnects once it discovers the server is back online. And then we're able to open back up the file. OK, so that's an evaluation of just running the server in one example. Of course, we did a slightly more rigorous evaluation. So the first question that I've already talked about is, does Daphne reduce the proof burden? And indeed, it was actually quite significant. The other thing I should mention is the timelines for both of these. GoTXN was, let's see, maybe like a year and a half with well, for just the GoTXN part. The infrastructure took even longer. And several of us worked on it, I think 5 or 6 authors. Whereas DaisyNFS, essentially I wrote by myself because nobody else was interested in using Daphne at the time. I'm joking, it's because it wasn't that much work. Okay, so I talked about trusting. Okay, let me talk about the testing. So we use several testing methodologies to test that DaisyNFS actually does what it's supposed to. We have unit testing for all our Daphne support libraries. I was very scared about writing any trusted code in Daphne that Daphne is using. We also ran a high-level end-to-end testing, like FSStress, CrashMonkey for testing crashes. This last one, I can't give too many details on because it was kind of a half-baked research project that Robert Morris was doing at the time. But it found a bunch of bugs in our unverified code especially. So let me talk about more of these bugs because I think actually several of them are interesting. An example of a spec bug that we were just missing is that create and makedir allow an empty name. They originally allowed an empty name. This is just an example of not faithfully translating every line of the RFC. So I think this is again a case where it'd be interesting to take, instead of starting with an implementation and trying to give the spec, it'd be interesting to start from the RFC and try to produce a faithful model of the RFC that's validated against a real NFS server, rather than starting from our implementation. And then to be able to join those two together. There's another one that I think is actually really interesting, which is that, again, in this code, so I already said that we're assuming a precondition that the inode number is bounded. There's another much more subtle implicit assumption here, which is that when we give a byte buffer to Daphne, Daphne is going to assume that you are not modifying anything in the state except through the transaction system, right? For this code to run atomically in Daphne, you need to not have concurrent modifications. And the reason why you don't have concurrent modifications is because the transaction system guarantees atomicity. But there is some heap memory from the buffer. And it turned out that our RPC system could take a buffer from the network, it could pass it to the right handler, it would go through this system, and then it would be passed to GoTXN, where GoTXN assumed that it had complete control over that buffer. And in the meantime, while this thing was running, and then once the commit returned, it actually came back to the RPC system, and then it reused the buffer. If you ran another RPC afterward, you could actually corrupt the state of GoTXN. Because the same buffer was actually sitting in the GoTXN code as was sitting in the RPC code. So this is an example where we were assuming exclusive ownership over some sort of some state, and that exclusive ownership was not guaranteed by anything. Yeah.
Yeah, is that why? Because you're modeling, I'm not quite sure if they're both. I guess the top on the left is Daphne code, and that buffer is just a Daphne.
It's a Daphne object, yeah.
It's a Daphne object. Presumably it's just a Daphne array, so it's immutable. And
Yeah, Daphne is just, it's assuming a sequential programming model, right? And we believe that's justified because of our atomicity proof, but this is one of the dangers of making an assumption like that. If you do have any other data, you have to actually guarantee that it also is, in some ways, we're assuming all writes go through the transaction system. Yeah. And then the Go code kind of has no way of, if we were using Rust as our surrounding language, we might have been forced to ask the question about ownership at some point. I don't think Rust completely solves any of these problems. At some level, you have to make assumptions about ownership and then actually guarantee them. Yeah.
Do you provide any support for functional correctness proof of applications built on top of this?
Oh, yeah, that's a good question. So the short answer is we don't. You could use this as a library, and then you could verify your applications. If you're actually writing an application that uses the NFS server over the standard API, then it would actually not be completely sound to use this specification because you're not going through our API. You're going through the client system, and the client is issuing RPCs on your behalf.
Do you have a formalization of what constitutes a legal use of your?
Anything is legal. Well, what I'm saying is when you issue okay, there's a subtle difference between you run a file system operation, you run a read and a write using the Linux API, then the Linux client translates those operations into NFS operations. The spec is about the NFS operations. It's not about the POSIX API. If you could actually write an RPC client that directly issues NFS operations, and then the spec should totally apply to that program. Or you could skip the entire NFS part and just treat this as a library that happens to look a lot like the POSIX API, as just a bunch of methods. And then you can write an application that directly interacts with the disk and gets all of these proofs.
What's the form of your theorem that says the direct RPC version is sound with respect to your library?
It's the same proof that.
You showed us some pictures that have a bunch of transactions with parallel composition operators between them.
Yeah. So I mean, it's a. Yeah. So there's an on-paper proof that we have that composes the formal proof from GoTXN and kind of the obvious simulation result you get from doing Daphne proofs.
And is that with a fixed upfront set of transactions?
No.
The pictures would indicate?
No. It is a for all programs that use transactions. Okay. Okay, yeah, so those were the 3 bugs that I wanted to talk about, yes. Okay, yeah.
See, just to follow up on that, see, for all programs they use transactions. So we have at some point there's a server that's perpetually handling requests.
Yes.
And the timing of these requests depends on which transactions are running at what time.
Yeah.
Logically, how do you phrase this so that the transactions can be started at any point?
Okay, so the proof is about an arbitrary program that uses the transaction system however it wants. So it's a, and then that program can also be concurrent, right? So the server is an example of such a client. What isn't connected is exactly, so the server chooses to run operations when it receives them over the network, and there's no link between the network and when it issues these operations. I mean, we're trusting that you translate and you read you connect to clients correctly and you parse these RPCs correctly. But then that's about it. After that, you get the operations that you wanted.
Is there an assumption that the program runs for a finite amount of time?
No. Yeah.
So this question might not type check, but
Okay.
I think you mentioned that you axiomatized some of like the concurrent separation logic or like atomicity requirements in Daphne, and that was
Yeah.
your. So I'm curious about like when you were writing your Daphne proofs, like did this what kind of automation came freely from this axiomatization, and what kind of stuff did Daphne have?
Okay, so let me be a bit more precise about this. So we didn't have to axiomatize anything about concurrency reasoning in Daphne, per se. As long as you run all of your code within a transaction, you get to use the standard program logic of Daphne. Because your code appears to run sequentially, we believe it's sound for you to reason sequentially and just follow whatever Daphne is going to do. It does require that you not escape the transaction system. That's really the restriction here.
Okay. So what kind of stuff were you axiomatizing? Like two transactions run like a transaction?
What we're axiomatizing is what happens for each transaction system operation.
Okay.
Like what do reads and writes do?
I see. Okay.
Yeah. It's a little bit more complicated than what I said because the transaction system allows you to read and write sub-block objects. That's the only reason why this transaction system, like, you might think it's just completely trivial. It is almost completely trivial except for the fact that we have sub-block objects.
Okay.
If it were just reading and writing whole blocks, I think like there would be almost no question about that translation. Yeah.
You can't even write concurrent programs at the Daphne level. Is that right?
No, you can't, except for maybe very recent features. But no, you can't write a concurrent program.
So there's no kind of that. You can't even write down the concurrent programs you might want to verify in terms of some higher level app spec here, let alone carry out that proof. That would all be informal reasoning as well about the logic behind correctness at the application level.
Yes, that is correct. You would have to go down. Yeah. Okay. Yeah. That is true. This is one reason why it would be nice actually to not do this in Daphne and to do everything in Perennial. But I don't know how to reconcile these two things, right? Like you really do want the sequential reasoning, but if you want to build a taller stack, if you want to actually consume this specification from a concurrent program, it's not like you can go back and forth easily. I mean, we did go from transactions to Daphne, but that doesn't mean that we can go from Daphne back to Perennial. That's a completely different connection. Yeah.
So you had a slide where you showed bugs that you found. Did you also find bugs in the Daphne implementation you wrote while writing the proof?
Oh, all the time. Yeah.
Okay.
Yeah. I mean, the Daphne code is full of bugs. I didn't even consider those to be a problem because, I mean, it was very much incremental. Like you'd write some code and then write proofs and then in the process, of course, discover bugs and fix them. I think there's I looked at the source code recently and there is a comment to the effect of like, this is something that I don't completely understand, but the proof forced me to do it. And, you know, so I did it. I think that was a case where like, it's a subtle bug that I don't fully understand that the verification caught. As far as I mean, it's also possible that there's a way to work around this and not write this code, but I think that's actually a very cool aspect of verification. We had another example of that in GoTXN where one of the undergrads on this project decided, he discovered that something was not necessary for the proof and it would improve performance, so he got rid of something that we thought was necessary. And I thought that was very cool. This is an example of where verification really helped us develop the code. Okay, so let me briefly go over performance results. I'm happy to take any more questions, but let me just give you some brief idea of what performance looks like. The setup for this evaluation, we ran on an AWS i3 bare metal instance. This is a fairly beefy machine. It has 36 cores, running at 2.3 gigahertz, and it has a very fast NVMe SSD. We ran 3 benchmark setups. The first one is a very metadata-heavy benchmark that creates and deletes constantly small 4 kilobyte files concurrently. Large file just writes a very big file. And the application benchmark here clones and compiles a C program. The first thing that we did is we compared all of these benchmarks on an in-memory disk. So this is challenging because it means we can't hide our performance behind I/O performance. And there's a single client, so we can't just parallelize our overhead across multiple threads. These are results normalized against Linux, so Linux always gets 1. DaisyNFS gets pretty good performance. It's comparable to that of Linux, but it's not quite as fast as Linux. I think even in the large file case, the DaisyNFS is just, it's a little bit slower than Linux. Linux has a slightly more sophisticated logging design. So what about concurrency? Concurrency was a major part of this work. So to do that, we took the small file benchmark and we created and deleted files across a number of clients, and we varied the number of clients. This time we run on an NVMe drive, which gives both DaisyNFS and Linux a chance to actually coalesce concurrent writes. we find DaisyNFS does get better performance as you add clients, but the performance saturates and it hits lock contention at some point at a common lock in the write-ahead log code. Linux and it scales a little bit better, but it also peters out at some point. In all of these benchmarks, we do find that the CPU isn't fully utilized, the disk is not fully utilized, so it probably is lock contention for Linux as well. But it just has slightly more sophisticated locking and logging. To conclude, DaisyNFS is a verified concurrent file system. We verified it using a combination of automated and interactive theorem proving. And the transaction system enables us to combine these two very different verification approaches. One that requires us to reason about crashes and concurrency directly, and then Daphne, which allows us to do very automated sequential reasoning. Thanks, and I'm happy to take any final questions. Yeah.
So in the specification for commit in the transaction system, it seems like you were saying that on the crash it should behave like a no-op, but I also got the impression that you wanted to immediately at the point of crashing already be a no-op and not allow for some sort of recovery or repair phase after the crash?
So the crash, what I mean is it's either a no-op or it's the full operation.
Yeah, I saw that, but when the crash occurs, it'll be a no-op, right?
Up to some point, it'll be a no-op, and then
in some scenario of crashes, it'll be a no-op.
Yeah.
Right, and to me, it seemed like in that scenario, in the implementation, you want it to be at the point of crashing already be a no-op instead of also allow for some program to run after the crash as sort of recovery or repair phase.
Oh, okay. So the specification is actually contingent on recovery. What it means to have this logical state is if after a crash to actually get that state, you do need to run a recovery procedure.
I see.
The recovery procedure doesn't do that much work.
Okay, because you said that there's a limit to the size of the transactions, and I thought that that limit was incurred because you don't allow such a recovery phase, but you do allow that recovery phase. And then
Yeah. The limit is actually this is just this logging design reserves a limited space for logging. It does not allow the whole disk to be used.
Right. Okay. Okay.
Yeah. And there has to be a limit because the disk is finite. So. Yeah.
Question, because I wasn't at the beginning of the talk. So Goose allows you to get some Go code and then have a cock, then transfer it into cock. I'm not sure what.
Yeah. I didn't talk about this in any detail.
Okay.
But yes, Goose is the thing that allows us to carry out these Go TXN proofs on the Go implementation. Yeah. Yeah.
So you said you use the Daphne to Go compiler to essentially plug in Daphne code into Go. So you can also go the other way around using sort of the extern tag and plug in Go code into Daphne.
Yeah.
Is that something you considered as well?
So we had to do that to plug in the transaction system code, but I don't know how we would do that for the body of the code, right? Like, we actually want to verify the implementation of the system, so we needed it to be in Daphne in the first place. So I'm not sure how we would do anything better than this.
So the impression I got is that you had a Go implementation, and part of that you use Daphne for and plug it into your bigger Go implementation. I was thinking if you could have taken sort of the Daphne implementation as sort of primary entity and then plug in external Go code into the Daphne one.
Okay, I think this is actually just a matter of perspective. Like, you could view it like that. You could view it as there's a Daphne proof and there's just these read, write, commit operations, and those are externally implemented. It just so happens that the proof about read, write, commit are so sophisticated that most of the proof is from that side. But you could view the Daphne code as being primary here. Or really it's unverified code and then a big chunk of Daphne and then a big chunk of verified transaction system. Right, as I think would be kind of common in a verified project, right? You're gonna have some wrapper code that's unverified, that consumes the verified code.
Okay, I think one more question here.
Yeah.
So you've been doing work on a network file system.
Yeah.
And you can think about it as a singular entity.
Yep.
Talk about how your work would scale to say a distributed file system and what would be required.
Yeah, so some of my colleagues at MIT, they have continued working on this infrastructure to be able to reason about distributed systems. So I think there's two takes on this. One is implementing a distributed file system, of which there's a bunch of designs, there's a bunch of ways to do that. And then the other one is to reason about the NFS client, right? So you already have a little distributed system where you are contacting the server over the client infrastructure. And I think it would be very interesting to verify this whole combination, right? Multiple clients, even against a common server, or a distributed file system. A lot of the infrastructure for that is actually shared with concurrency, right? So the distributed system looks a lot like a big concurrent program, except that there's some memory that's inaccessible. Yeah.
In all the tools that you've used, do you have particular desires for them?
I think I have a long list of desires on every tool that I have used, which I'm happy to talk about offline.
Thank you.
But then you can't hear it on the remote. People can't hear it. So yeah. I think when it's done at the end of the talk, it's much easier. It's just the keynote. So just when you do this. Yeah, I'll tell you.
All right. I'm very curious about the next talk, which is given by Gianluca Redondi from the Research Institute Fondazione Bruno Kessler in Italy. And he will tell us about the verification of interlocking logics, which I think I used to model railway traffic.
Yes, right. Yes, thanks. Thank you, everybody. So yeah, I will start with an introduction on interlocking logic. And we are in the railway domain, where we have different components, sensor, traffic light switches. They all interact with each other. And an interlocking logic is a system of rules that ensures safe and efficient operation among those components. And for example, the logic should ensure that no conflicting signals are sent, that switches are set in a safe position, and that no two trains are authorized to occupy the same section of a track simultaneously. Now, in my research center, there is a collaboration with the Italian railway network to develop a tool called AIDA for the design of such logics. Basically, the idea is that the railways engineers can write down system specification in this tool in a controlled natural language. They can write down phrases such as, when a train is arriving, activate some switches. And the tool is able to generate from the specification extended finite state machine for each component of the logic, as well as C and Python code. And the state machine will have states and transition, of course, and transition are characterized by guards and effect, and importantly, effects will cause other transition of other components to fire. Then, once a configuration is given in the tool, and by configuration I mean the map of a specific plant, then you can actually get code ready to be executed for that particular station. So the goal of our research project here is to automatically verify the properties of the logic. Because, yeah, given a configuration, given a particular plant of a station, we could use, let's say, standard model checking to check whether some safety property holds in that particular station. So the properties that we want to prove are no conflicting signals are sent, trains are in a correct position, and so on. But these properties should hold independently from the configuration, and we want to prove them at the logic level. And to do that, we want to generate, alongside the C and Python code, also Daphne code from the specifications, and use a parameterized model checker to automatically infer invariance for the system. So parameterized part here is really important because the system at the logic level is not configured. We have an unbounded number of components for each component type. So to give you a picture of the workflow here, we have AIDA, the tool, and the engineers, they wrote down the specification in the tool. And then the tool is able to generate C, Python code. So the continuous line here is what we have. And the dashed lines here is what we want to add. We want to add the capabilities to generate Daphne code in a way that when the engineers, they inject some properties, there is an interaction with a parameterized model checker that is able to prove that the property holds in the logic at the Daphne level. And this is all at what we call the abstract level, so no configuration is given. Then if you give the map of a particular station, you actually get some executable code. So in the next few slides, I'll show you some examples of what we have in mind to model the logic in Daphne. Basically, each component will be modeled as a class. All these classes extend a trait, CDL. Each CDL will have a set of, CDL is a component of the logic. CDL has a set of connected entities with other objects that can be affected by the transition of the particular object. We have a predicate violet to define the set, and then we will have a method execute that should mirror the transition relation of the particular object. As an example, here let's have a look at the root class. The root will have a variable state with value in a data type with 4 values. The root will use some tracks, so we have a sequences of tracks used by the root. And in the predicate valid, we see that we state that all the tracks used by the root are in the connected entities, and moreover, all the entities connected to the tracks are also connected to the root. So we have this cascade effect in connection in the logic. And the idea is to have for each transition of the root class in the state machine, we have 2 methods in Daphne, one method for the guard and one method for the effect. The method for the guards returns a Boolean, which is true, if and only if the precondition associated to the guard holds. In particular, here we see that one of the preconditions is universally quantified, so this is mirrored in the Daphne code by a while loop. And we need additional invariants in the while loop, of course, to make Daphne conclude that the body actually meets the specification. But we aim to generate those invariants with the code itself. So via some schemata, we don't need a model checker for this kind of invariants. So this is a method, again, for a guard from a transition that goes from a request state to a lock state. And then we have another method for the effect of the same transition. The method modifies the object itself and the tracks used by the object. And again, we have the requirement, which is the guard of the method, and then the ensures, which are the specification of the effect of the transition. Again, we have a while loop with some invariants, and notably here in the specification, in the body, we have calls to other transition of other components. And this is basically what happens also in the C and Python code generated by the tool. So at the end, each class will also have the execute method that should wrap up all the transition. Basically, the idea is that the execute method of each class will have a bunch of ensures, one for each transition, but the execute method here can modify all the connected entities, so the specification for the execute method should be more sophisticated because we have to state for each of the elements connected to the object how the state changes. For example, here we have to state all the tracks used by the root, they will change the state. All the tracks not used by the root do not change state, and all the other connected entities, they do not change the state when a transition of the root is executed. And the body of the execute method is just a match statement. We have a bunch of cases, one for each value of the state variable. And basically, we fire a transition as soon as it is possible, and we also have some axioms on this state machine that the transition relation is total and fully deterministic, so we know that on each state there is one and only one transition that can be fired. So, to sum up until now what we have seen, we have a design of an interlocking logic in AIDA. We want to generate Daphne code alongside C and Python code to represent components of the logic and their transition. And the idea is that the body of the Daphne methods should mirror the generated C and Python code, whereas the pre and post condition of these methods should be a formalization of the specification of the logic given by the engineers in the natural language. And if we do that already, we have a first result because we have a formal proof that the bodies meet the specification. But remember, this was not the main goal here because we wanted to prove the candidate properties of the logic. And to do that, we need an additional ingredient. We basically have to model the scheduler in Daphne as well. So we define a new class with a set of objects, and then we define a candidate property. And the scheduler will be a method that just picks an object and fires a transition. And what we want to prove is that if the property holds an entry, then after one transition, the property is still true. So each transition preserves the invariant, similar to, I guess, the previous talk. But this, of course, would rarely be the case immediately because candidate properties are hardly inductive on their own. So the idea here is to obtain additional invariants automatically by using a parameterized model checker. But we do not want to go directly to the model checker because model checking, especially parameterized model checking, is very expensive. And so we have designed a SIGAR loop, so counterexample guided abstraction refinement loop, where Daphne and the model checker interact with each other if the proof for the property fails in Daphne, then we are able to extract some part of the system that we can model in the model checker, and the model checker finds some invariants, then we pass back to Daphne. And at the end, we either find some successful verification, or we can also find some counterexample by the model checker. So at the moment, we have some early results. We have modeled a simplified case study of the logic with 5 components, 29 transition, and 18 variables. And we can prove that this logic does not allow for 2 different routes to occupy the same section of a track simultaneously. And we can do that by providing to Daphne an inductive invariant that we found by using a parameterized model checker on an abstract version of the logic. At the moment, unfortunately, the Daphne code, the input files for the model checker, and the interaction between Daphne and the model checker are all manual. So we still have a lot to do. We want to obtain Daphne code automatically from the specifications. We want to obtain input files for the model checker as well. And we want to make the interaction between Daphne and the model checker automatically, because right now I'm using Daphne on Virtual Studio Code, the model checker on its own, and doing everything by hand. And of course, once we do these steps, we can make experiments with the actual logic designed by the engineers. And yeah, in theory, we know how to do that, but in practice, I think it will be very hard to implement this feature. And that's it. Thanks for the attention, and I'm happy to receive questions.
Can you go up to the microphone?
Yeah, sorry. It sounds like from the point of the domain expert writing the natural language specification, you want to generate everything, including the proofs. Is that right?
The proofs, so we generate the proofs that so we ask for the engineers to provide the property. The property will need additional invariants of the logic. These additional invariants, in order to make, let's say, the property inductive, we want them to extract those from a model checker.
Right,
So
and you're hoping to do all of that in sort of an automatic way, right? The point of my question is, I'm just asking whether that is the extent of the automation that you want to get to, and also then my comment is that sounds like a really high bar for automation to get those invariants automatically. But if that's the case, then I think your answer is yes.
We want to start with this goal. With the engineers will have a button. They push the button and they get, okay, your property is true, or no, here's a counterexample. I agree that on the actual logic this will not be feasible, and we probably need to ask the engineers to write some invariants on their own. But it is very difficult because they are not trained in formal reasoning, so, and also they don't see verification as useful, I think, in these early stages of the project. So we want to, right now, give them something completely automatic, yes.
Okay, cool, thanks.
Since in your project, the Daphne code is meant to be generated automatically from another form, I was wondering what you think are the advantages of targeting Daphne instead of Boogie, or even producing your own translation to SMT.
So we actually started by translating directly to SMT. This was very hard for many reasons, and having a object-oriented style programming language is very helpful because it's very close to the internal representation that we have in the tool AIDA. So when the specifications are given, those are transformed inside the tool in basically an object-oriented programming language that it's easier to go directly into Daphne. And then we really, with a one-way SMT translation, this was too big for the model checker to reason. So we kind of want Daphne to be as a shield, let's say.
Thanks.
Hi, thank you very much for the great talk. I was wondering, so the natural language statements correspond to some statements of logic, and what kind of logic you're actually using to specify properties? Is it some form of temporal logic, or what are the, like, what is the system you use to specify those properties?
So at the moment we want to start with invariant properties, so just every reachable state of the system should have this property. More in general, we need to reason about cycles of transition, so we need to introduce a form of temporal reasoning. But
and following up on this, I would be really interested to see the experiments of trying to translate natural language into temporal properties, because there have been quite some interesting papers of people, I think it was a bunch of people from Brown, looking how difficult it is to actually connect LTL formulas to statements in natural language, and we'll be interested to see how the real engineers, actually when you make them write
But we
properties.
still haven't done that.
Okay. Yeah, okay, so. But I'm looking forward to it. Thank you.
Yeah, I'm tempted to ask why you want to do natural language. Sorry. I'm tempted to answer why you want to do natural language. If you're dealing with engineers, shouldn't they be able to cope with some kind of input language with semantics? People have been looking at railway interlocking for, what, 170 years? And I bet there are notations such as track diagrams and diagrams for signals that actual railway engineers use. And you could take that as input. Google tells me the Belgians actually have a specification for precisely that.
So I guess I'll dodge the question, just saying as a PhD student, I was in charge of the verification of this project.
Excellent. Blame your supervisor. Yeah.
No, but...
just because ChatGPT-3 is cheap doesn't mean it's a good idea.
I wanted to ask you a bit about the need for different model checkers. I am not clear whether in the current situation you can check everything you want with Daphne, but you are saying that just using Z3 underneath or whatever. And whether you are saying for some properties it can be that a dedicated model checker will be faster, and what I would like to do is tell Daphne which model checker to use for what. I was not clear about that. And you had a diagram of what does Daphne call? Yes, previous one. Yeah.
So basically, Daphne cannot infer invariance of the program. It just checks if the property is inductive with respect to transitions. And in order to get additional invariance for this proof to conclude, we want to use a model checker. In particular,
so it's not a model checker to do theorem proving, but it's a model checker in order to find more properties and then feed them into Daphne so that it can use it when it does its own theorem proving.
Exactly, yeah.
Thank you.
One more?
So regarding the CGAR loop, so even if you find more invariance, there's sometimes where you might need to assert some kind of trigger in Daphne to get the proof to go through. You might not get an automatic empty proof. Is that something you ideally want to completely automate away, or is there some expectation in your final goal that you might need to tweak the proof to get it to go through or something?
That's a very good question, since first order logic is difficult. I honestly still don't know, because we know that there is some fragment of the logic which is represented by a first order logic which is still decidable thanks to some alternation of quantifiers and stuff like that. But in general, this is not true. So in general, we still don't know, and we could guess the right invariant, but Z3 basically would not be able to discharge that could happen.
It would be really cool if you could like EPRify the.
Yeah.
Okay, nice talk. Let's thank Gianluca one more
Thanks.
time. Okay, there's going to be 30 minutes of coffee break, and then we continue.
All right, maybe we can get started now with our next session of the morning. So our first talk is going to be a remote talk, so fingers crossed, by Sasha Fedgen from Tufts, who's going to be telling us about Daphne test generation. So hopefully now, magically, Sasha's face will appear.
Hi, hello. Can you see or hear me?
We can hear you, but we cannot see you yet. Okay, now we can see. We can see.
Give me a second to join the YouTube stream to confirm. Okay, I believe you can see me. Please do screen me if you can.
We see the.
So,
we see
so,
wait. We see your Discord, but not you.
With the talk.
No. Okay. This.
So.
Wait. Okay. We can't see you yet. Yeah.
Sorry. Sorry. You cannot see my slides. You cannot see the slides.
We see Discord.
So could you let me know if you're able to see the slides?
We cannot see your slides. We can only see Discord. Okay, we see slides now. Yeah, okay, good.
Hello, can you?
Yes, we can see your slides. I don't think you can hear me.
You can see your slides, right? Based on... You can see my slides now. Okay. Great. All right. I apologize for the delay. I'll try to be a bit quicker. So thank you so much for accommodating a remote presentation. I'm Sasha Fedgen, I'm a PhD student at Tufts University, and I'm going to talk about test generation Daphne. And in particular, I'm going to talk about scaling up existing test generation functionality to system-level tests. And this is a joint work with my advisor at Tufts, Professor Jeff Foster, and with my mentors at Amazon, Zvoyner Kamarich and Aaron Tom. So I'll begin by motivating the need for runtime tests in Daphne in general, and then I'll move on and introduce DTest, the Daphne testing toolkit, which allows Daphne users to automatically produce tests from implementation written in Daphne, and then I'll move on and talk about scaling this functionality up and the challenges that we face when trying to produce system-level tests. So the main question, sort of the first question that everybody asks when talking about runtime tests in Daphne is, why cannot you prove everything that you want to hold true about the behavior of your program at runtime? Why cannot you prove it before compile time? Right? This is what verification is about. So why do you ever need runtime tests in a verification setting? And so there are sort of pre-answers. First, you might want tests before you have completed verifying your program. In particular, imagine a situation where you have written an implementation and you have written a high-level specification that tells you what this implementation is supposed to do. But you haven't written any intermediate pre and post condition, any loop invariants. The verifier cannot yet give you that proof, and you have to do a lot of work before that happens. And in this situation, the worst that can happen is that you go in, spend hours and hours and hours writing your proof, and then figure out that your implementation actually has a bug, meaning you have to write everything, and the time you spent working on your proof is wasted. And so in this case, what you could imagine doing first hand is to generate runtime tests from the implementation, and then at runtime check that at least for some comprehensive set of inputs, your implementation abides by the specification. And then once you know that, you can go on and actually write proof and then get the verification complete. Now, the second reason to use runtime testing is that no true end-to-end verified infrastructure exists, meaning that even though Daphne code is verified, when you compile your Daphne code, you might be actually connecting to some standard libraries in the language you're compiling to, or you might be using projects written in the language you're compiling to that have not been verified, and so it is possible for bugs to exist in those projects, and so you might want to generate runtime tests that would sort of give you additional assurance that the whole pipeline is correct. And finally, Daphne is often used for model-based testing. So this is a situation where you already have an existing implementation written in another language, and then you write a Daphne model, and then you might be absolutely certain that your Daphne model is correct, but you still might want to generate tests from the model to run on that implementation that's written in another language that you don't actually have guarantees about, and this way you can perform model-based testing. Okay, so these are the reasons why you might want random testing in Daphne. So now I'm going to introduce DTest, or Daphne Testing Toolkit, that allows you to generate random tests. And this has been presented last year at NFM originally. So in a nutshell, what a DTest does, it takes a Daphne program and it produces unit tests. And it does this by inserting failing assertions, or assert false, at some location in the program, and then asking Daphne to verify the correctness of the program. Now, of course, if that assertion is at all reachable, Daphne is going to complain that that assertion might be violated, and it will give a counterexample. And then from that counterexample, you can extract inputs for a test method, and then repeat that process for a different location in the program, and thereby create tests. So to give a concrete example, you can see here on the left side of your slide, there is a function that computes a maximum of two numbers, and it has two branches corresponding to which of the two arguments is greater. And so if you run dtest on this program, you will get two tests that you see on the right hand of your slide. So as you can see in the first one, the first argument is greater, and then on the second one, the two arguments are equal. Now, DTest can handle much more complicated constraints. So now on your slide, you see a snippet from a program I have written that defines a subset of chess rules in Daphne. And so these definition of these rules allow me to check if a king is under check for a particular configuration of pieces on the board. And so this is what the code on the left-hand side does. It takes as input a configuration of pieces on the board, and then it tells you whether or not the king is under check. So there are still two branches, just like in the example that I showed earlier, but in this case, the conditions that guard the conditional are much more complicated, and they involve recursive and functions and nested predicates, and then the input is also more complicated, right? So it's a nested data type. but DTS can still handle it, and you can read more about it on the Daphne blog. I have a link on the slide. I'll have a QR code. The point is that the DTS will be able to produce configuration of pieces on the chessboard as hypothetical inputs, and you can see some of them on the slide. So now let me move on to system-level tests and scalability. So to motivate doing system-level tests, imagine this use case that I mentioned before of writing a model in Daphne to prove some properties about an existing modalization, and then trying to prove the equivalence of a model and implementation by generating tests from the model. So it is a safe assumption to make that the entry points for the two programs for the model implementation are equivalent in some way. So they take the inputs of the same form. But the details of the implementation, the helper functions and methods might be different. And so what you really want in this case, if you really want to generate tests, you want to generate system-level tests, such that they will use this entry point, which we can assume is equivalent in both cases, and then cover the entire program. And so that's why we want tests that generate inputs for one method, but cover the entire program and all the methods within. And another sort of benefit of system-level testing is that it can help you identify dead code of a particular type. So specifically, I'm talking about dead code that is dead not in the context of a particular function, but in the context of a program. So here you can see the predicate threatens that I have written as part of the example I mentioned before that involves chess. And you can see here the line highlighted in red is dead with respect to the program because it talks about the way a king, the chess piece, can threaten different positions on a chessboard. But the program itself is designed to reason about situations in which a king is under check, and one king can never put another king under check. In chess, that can never happen, and so this predicate is in fact never called with king as a receiver, and so this line is never going to be executed. And DTS can tell you that, and tell you that is provably so, unlike say a fuzzer that will just not be able to generate tests in this use case. Now, to enable system-level tests, we had to redesign some parts of DTS because by default, Daphne performs verification on a method-by-method basis, meaning that when it looks at a method and tries to verify properties of that method, it only has access to specifications of other methods, but not their implementation. Whereas we want to generate inputs for one method, but also cover parts of the implementation in a different method. So the way we went about it is we essentially use the form of bounded model checking through inlining. So we can inline bodies of methods into other methods. And because in general inlining is costly, we also allow the user to guide this process to specify which methods should be inlined. You can, and I'll not go into details right now, but this involves some engineering challenges, and particularly removing short circuiting from Daphne to make this work. But let me sort of jump into motivating why we need user-guided inlining. You can see here on the slide an example of a call graph for this example that I keep mentioning that involves chess. In particular, on the left top corner, you can see the describe method that I previously showed you. And then on the bottom right corner, you see this math absolute value function. And my point here is that for 120 paths to this function, for this fairly simple program, and it does not account for branches within the methods themselves, so the number of paths we could control for a graph would be much higher, for example. And so the idea is that if you try to inline this absolute value function, the test generation will take much longer, but the user can explore this trade-off between coverage and speed by specifying that they do not want, for example, to cover all the different paths to this absolute value function. All right, and then I'm running a little time, so I'll say that you can read more about this particular example and how to solve chess puzzles with Daphne on blog post, and very quickly about some open source results. So we did use the test to generate runtime tests for existing Daphne projects, in particular with the Daphne tildes library, which is currently being transformed to the Daphne standard library, and also on the AWS encryption decay. So we generate hundreds of tests, and we achieve coverage, fairly high coverage, both statement and branch coverage, and you cannot achieve 100% in these use cases. So the numbers are somewhat higher if you account for that. And yeah, I want to thank everybody who has been involved in test generation for the past several years. And this is it. And I'm happy to take any questions. I cannot hear any of those. So let me know if you can. Let me try and join the
Okay, well maybe people can send messages on Discord to Sasha or email Sasha.
Just talk into the mic.
Well, we tried earlier and he wasn't able to hear us when we were talking to him before, so.
Through the mic?
Yes. Maybe we can try again though.
Sorry.
Hello?
Can you hear us?
Hello? Can you hear me?
Can you hear us? Apparently not. I'm sorry. Let me, yeah.
It's not clear it's on your end or on his end.
Hello? I can hear you now I can hear you now through the YouTube stream. Hello?
Oh, through
I
the
can hear you
YouTube
through the YouTube stream.
Okay, that's.
I can hear you.
Okay.
So do we have any questions? Yes, please go on.
Hi, thanks for the talk. I was curious a little bit about the, I guess, one step in your process where you go from a counterexample to a test, or like getting the inputs that cause this particular counterexample to trigger, and maybe just what that process kind of looks like. Because I know Daphne counterexamples can be a little hard to parse back for more complicated examples.
Communicate with outer space.
Maybe,
okay.
Right, thank you. I assume there will be a little lag. So I'll answer this question and then it will be the last one. But yeah, so this is the main part of test generation. And essentially what we have is a model that Z3 gives us, and then we have to convert it right to Daphne syntax. It is essentially. Oh, sorry. Sorry, there was some very sharp echo. Yeah, anyway, I'll wrap up by saying that this is a problem that I'm still working on in making the functionality better, and that a major challenge is preventing incompleteness, right? So sometimes the counterexample can be incomplete, so that's sort of the main challenge, but it mostly has to do with how we write Daphne rather than with counterexample construction itself. Thank you.
Okay, our next talk is also about testing, although of the Daphne compiler as opposed to testing particular Daphne programs. This is going to be a jointly delivered talk by Alex and Dylan. Thank you. Yeah. I think he's supposed to do it for us, but.
Oh, okay.
Okay. So, yeah, we're presenting on the randomized testing of the actual Daphne compiler itself. So, how do you actually test a compiler? So, to do this, well, ideally, you'd have unit tests covering absolutely every line of the compiler. However, things will still happen. Even with testing completely done, there'll still be a way to find bugs. So what you do is you generate a test program, you compile it, and you collect its output. In Daphne's case, this could be introducing a main function and actually having it run. And then by some method, you verify the output of it. And if you detect a bug, you reduce the program down, try to minimize it, either report it and leave someone else to fix it, or try and look into a fix yourself. If you don't find a bug, well then you come back and you generate a new program and try again.
Now, the main problem with doing compiler testing is that it's very difficult generally to identify whether or not the compiler is doing the right thing, and this is known as the test oracle problem. So for unit tests, it's very easy to encode an oracle, the expected output, because you kind of manually program that into a unit test, whereas with a randomly generated program, it's much more difficult. So there are two ways to solve this, the first of which is called differential testing, where you, instead of just running over one compiler, you would take your generated program and you would run it over a number of different compilers. And then the idea is then that you should see ideally the same result across all of them, or if one of them is different or more than one of them is different, then you might have found a bug in one or more of the compilers. Or there's also something called metamorphic testing, which is instead of running over different compilers, you will now take that randomly generated program and mutate it in some way such that its output should be equivalent. For example, you might have an expression x equals a plus b. You could mutate that to b plus a. And then you would compile and execute all these mutated programs. And then again, if more than one of them is different, or sorry, one or more of them is different, you should have again maybe found a bug in one of the implementations. So we applied these techniques to Daphne. We will first generate a program. We do something called reconditioning the program to make sure that the program stays valid and it will compile and run without errors. We then pass it through Daphne to each of the backends and perform differential testing over the outputs to check whether or not any one of the backends has an error in it.
So what have we actually done here? We've created two different tools, fuzzd and Daphne Fuzz, which both generate complex programs which are guaranteed to be valid. We then run these programs and actually test it to try and identify bugs in the programs. And as a bit of evaluation, we've evaluated its effectiveness against XDSmith, which was an existing compiler fuzzer for Daphne, as well as the regression test suite for that. When looking at it, we looked at the number of bugs we identified. In particular, we had a focus on the soundness bugs, so where Daphne would produce a, for example, valid verification saying the program's correct, but the compiler would actually produce something different. We also looked at the line and branch coverage, as well as took a look into mutation testing.
Okay, so for program generation, we took something known as a generative approach, and this means we would recursively walk over the Daphne grammar. We would start with a main function in both of the tools, and then we would select over the constructs of the language. For example, maybe a statement could be an assignment or a function call or something, and then we would use these to then generate the rest of the program randomly. And these would be done using weightings to make sure that we limit the program size to something that can be compiled in a reasonable amount of time.
So in terms of language features, we both look to cover the basic types, so this might be arrays, tuples, basic integers, bit vectors, as well as some of the collection types, so the sequences and sets. But we also took into looking at more complex types, so inductive data types, generic data types, as well as object-oriented types, such as classes. In particular, we also focused on features of the Daphne language that we may have found to be slightly unusual compared to most other languages. So, for example, match statements and expressions, the loops that existed and a small bit on their verification, parallel assignments, and as mentioned, we took a look into some verification features such as pre and post conditions, invariants, and assertions.
In terms of testing, we ran differential testing, as mentioned, where we would run a program over its different backends and compare the outputs. We'd also do metamorphic testing with Dafny fuzz, where it would produce a number of different equivalent programs and test these outputs. And the benefit of this is then that you can just test one particular backend, for example, maybe the Java backend or the C# backend. You can just generate a number of equivalent programs and test one particular backend. We also looked into mutation testing, which mutation testing essentially analyzes the ability of a test suite, or in our case, generated tests, to respond to real-life changes in the code base. So you would mutate the actual code base in some way, so the Daphne code base, and then we would detect the ability of the test suite, so our tests or the Daphne regression test suite, to detect this particular mutation.
In addition, we also looked at expected output testing, so an ability to track what the program should generate. So when we are both generating the programs, we had some sort of value tracking implemented, so then we can actually produce what we expect the output to be. The advantage of this is now we have an oracle that is completely separate from the actual Daphne compiler itself. For example, making sure that regardless of what Daphne's mutations it does, we know what it should have. We also, as mentioned, took a look into verifier testing. However, this was not our focus. It turned out that it was something a lot more complex in randomly generated programs, and in terms of actually having a precondition that was, or any sort of assertion that was actually accurate, was quite hard to do.
So overall testing, which we did in a number of different campaigns throughout the generation of our tools, and also once we'd finished them, we ran a number of campaigns for which we identified 24 unique issues in Daphne, 9 of which were related to soundness, although only 5 of those were classified as soundness, and there's 4 yet to be classified on GitHub. And 9 of the bugs we identified have been fixed. Do you want to go through the different breakdown?
Yeah, so along with this as well, in terms of languages-wise, we found the majority to do with Java. That doesn't say that it's 8 unique issues, because we saw a range of compiler issues with Java. However, we've estimated down to about 8 unique causes within there. As well as that, the next most we found was in the Python backend, and we found a few with C# and JavaScript and Go.
And in terms of our actual testing, I know we've just put a huge number of numbers in front of you. We performed 2 main types of testing: coverage testing for the average line coverage of tests generated by our tools, and also mutation testing for the number of mutants using a tool called Striker. And this would be testing a number of different test suites to check how many mutants could be killed or identified by the tools. So for coverage testing, we found that our tools are generally quite a way off the regression test suite, but compared to XDSmith, which we kind of considered as a baseline, we have made significant progress, particularly with fuzzd, where I believe it was the object-oriented features covered, made quite a lot of progress over XDSmith.
In terms of mutation testing, we saw that fuzzd performed significantly better than both Daphne fuzz, the XDSmith, and the compiler Daphne regression test suite. However, one important thing to note is that the XDSmith here had only 10 tests timed out and none survived. We haven't looked into this too carefully, but there were 2 issues that we saw with XDSmith. Firstly, in order to get these results, we actually had to increase the timeout settings on Striker in order to get them. And secondly, it might be a case that some of these timed out tests were killed by the other testing tools. But it appears at this point that while both fuzzd and Daphne fuzz perform better than the regression test suite.
Okay, so we'll now talk through a few of the different bugs we found. Bear with me while I try and do this. So the first of the bugs is an example of what can happen at runtime. In particular,
with regards to type safety. So in this case, we found a multiset, which is essentially a set where you record the cardinality of the elements as well. And we've created a multiset where we try to set the element 1 to have a cardinality of 2 to the 32 or 2 to the 64. And we found that for both Python and C#, this would result in an overflow exception. And this was evidently a bug because Daphne's integer implementation is meant to be theoretically unbounded. And this was handled correctly in the other backends. So it was clearly just a missing point in the implementation of the other backends. So we'll go on to, I think, this one.
Yeah, so this was a bug actually found during the process of generating both of the tools. What happened was, under the right conditions where you had match statements as well as parallel assignments, what would happen is the actual Daphne compiler would crash. While this seems like something that could be normally just a standard bug report, this was actually introduced as part of another fix that went in. So this was only discovered after we upgraded our Daphne version from what we were working on locally. Luckily, at the time, we were reporting quite a few issues, and the team reacted quite quickly and managed to solve the issue, and we managed to continue testing.
Yeah, and it's a good example of how continuous random testing can show, can identify regressions in compilers. So this one was, again, just a slightly different example. We were testing slightly more complex features, more unique to Daphne, and we found that certain combinations of the language, so for example, if you do a for all statement inside some pattern matching, then you would end up with some more invalid code generations for the particular backend, so in this case JavaScript and Python. So we see here clearly they're trying to reference this 2A, which has been generated by Daphne, where it's not been defined yet, and I think that's been fixed. Sorry, this is really difficult to... Okay.
Yeah, the last one we'll look at is a Go miscompilation issue, and this is where you have an unreachable bit of code, but for the Go language, the way continues and breaks were implemented was by jumping to a label, whereas in this case it would actually cause the Go output produced to crash. So keep scrolling down, see here, it jumps over a declaration. Again, helpfully fixed, and was able to continue testing these statements. Do you want to give your demo?
Yeah, we have a little bit of time, so we'll use what's left to give a demo. I'll just get up the IntelliJ. Yeah, that should be big enough. Okay, it's you. So how our tool works is we'll invoke it using just the name, and I'll get a seed so we can do some seeded generation to make sure that we get the right outputs. Sorry, there's a lag on the display, so I'm having to work from a lag. So if I provide this seed, it will produce a program in output here, which looks something like this when it generates. Okay. Yeah, so this is roughly what our programs will look like. You'll see we start by generating a number of inductive data types. Then we have this global state, which will essentially act as some global values which we carry around the program, as they can help identify more issues as throughout. So instead of losing data at the end of a scope, you can now use this global state to carry on data beyond the particular scope. Then we go through some function methods, which are just mathematical functions. And if we scroll down about 500 lines, you'll see we get to the body of the program, which has a number of different statements and so on. And then when we run it, we'll find a number of issues. For example, this is using quite an old version of Daphne now, so it's crashed on the Java backend and emitted a number of warnings and exceptions. So this is an example where we found potentially a number of bugs in the Java backend, whereas all the other backends have emitted a particular output successfully, and there was no other issues there. So we'll now go back to the presentation.
Yep. And we'd just like to conclude at that. Thank you, and we're happy to answer any questions.
Hi, thank you for the talk. I just wanted to ask, you mentioned two tools that you implemented, fuzzd and Dafny fuzz, I think. Can you explain the difference between those two?
They would just happen to be implemented at the same time. We're both working on the same project, and it meant that there was some small differences in the approach we took. So, for example, fuzzd mainly looked at the differentiating between the different outputs on the back ends, whereas Dafny fuzz looked at metamorphic programs, so they generate equal outputs. There was also some small differences in features that they actually look at and implemented.
Okay, great. Thank you very much. Okay, we're now going to switch over to two talks in a row that'll cover the use of Daphne in teaching. So I think this is an exciting point of discussion. So our first talk will be by Ron Hedinger. We're talking about teaching logic and set theory with Daphne.
Thanks, Joseph.
If you could just try to speak closely.
And let's see if
Yes.
it's being projected.
Okay, let me see. Yeah.
If my... How about the font size? Is it readable or should I... A bit bigger? This way. That's all right. All right, so thanks, Joseph. Hi, everyone. So happy to be here speaking about the way Chezi, Daniel, and myself have been using Daphne in teaching a second-year computer science course on logic and set theory for the past 3 years. So this is now the third iteration of the course, approaching the end in a couple of weeks, in a small college in Israel called the Israel Academic College of Ramat Gan, my birth town, near Tel Aviv. And I mentioned that it's a small college because it's a new computer science program. And the benefit of that was that it started small, and I was given the opportunity to teach a couple of required courses the way I wish to teach them. And I wish to use Daphne. The reason I wish to use Daphne is that I've been using Daphne for the last nearly 10 years for teaching programming, verified programming with refinement, correct by construction programming, stuff like that at Ben Gurion University. And I love it. So I thought, why not use it also for the required courses? And in a big university where you have many lecturers for the same course, it's not really feasible. Here in a small program, it worked. So specifically for set theory and logic, we run this course in two really different parts in parallel. So there is one way we've been using Daphne for set theory. I will show it a little here. And a different way we've been using Daphne for the logical part, for propositional logic. And recently I've seen mid-December teaching material from Amazon being published online about how they've been teaching Amazon developers logic, propositional logic, specifically deductive natural deduction. So really inference rules, how to use Daphne. And when you prove something, you really make small steps that you are aware of what's known and what's needed as if it were a sequence like by the book. And I've been doing the same, but in a different way. So I will say some words about that as well. So I would like to say, so I've seen in this material that was published recently that Daphne is being spoken of as a programming language, as a proof assistant, and as a language for writing correct code, so verified programming. And I would like to say that we've been using Daphne as a programming language. I will try to say how, as a proof assistant as well, but also as a teaching assistant. And that's my main message today. How Daphne can be a teaching assistant, how it can help the students get feedback on their assignment submissions ahead of submitting the assignment, really get the feedback that everything's fine, or if there is a problem, maybe there is a deadline and say verify false and sorry, but if not, they have good confidence that their programs are correct. It also helps me in grading. Is it good or not? Well, I would like to say some words about the grading, what kind of parts of the grading Daphne helps me in a really nice way. It doesn't automate everything, not at all, right? So it just helps me a little bit in really funny ways. And I'm not broadcasting now because there's some issue here with my, I didn't touch my laptop, so it went to sleep. Okay, that's it. Yeah, okay. So this is kind of background, and what I've prepared here is a few examples. So a few examples. I'm teaching the set theory part with inspiration from the course I learned at Ben-Gurion University by Professor Uri Avram, and the logic part by the Huth and Ryan 2002 book, and in two different ways. And Chezi helps me with this. So let's see what kind of examples I prepared here. I prepared here examples from homework assignments. So I have here links to, I'll make it a bit bigger. Or can you see? Anyway, I'd like to show some examples, and then you can browse later. I just uploaded it to GitHub last night so that it will be freely available, because I thought there's so much I'd like to say. How can I say everything in 15 minutes? Of course not. So everything is linkable now, all the material from the course. I deleted all the Hebrew wording from the comments last night, and I hope I haven't missed some, but bear with me if I did. And the nice, so there are really some nice things to share, and you'll be able to see it later if you want, or speak with me until the end of today. So examples. Let's go. Let's look. Some set theory. So right, distributivity of union over intersection. Right. So Daphne already helps me with the primitive support for sets, even for infinite sets, with the operations for subset, inclusion, so unions, intersection. So I can express such a property, and then we can prove it. We can prove it, and we've been using most of what's available on the short article on different. I linked it here on different. Sorry. On Rusten's different styles of proofs column, right? There are different styles of proof, and we've been using all of them, and it's fun. So going back to that example, we can see here some, right, so I've been asked. And the most important thing is that in this part of the course, Daphne helps me too much. It proves things by itself. So what is the student taking away from this? So I've used the labels and the reveal, and I insist in the assignment description, please write a proof that is for the human reader, and try to hide the preconditions for a lemma, the assertions with labels, and reveal them in such a way that, well, I will have to read the submission by myself to be convinced that it wasn't too much the help of Daphne there. But it works really nicely. And then there are all kinds of, so what else we have here? The for all ensures construct, really nice. The calc, I love the calc. Most of my PhD thesis was written with calculations, but on paper. Did anybody read that? Don't know. Don't know. But then at some point we wrote it in Daphne. Yeah, some of it. Anyway, yeah. Case analysis with if and else. So it's like programming, right? And labels, and then we prove. So all kinds of really nice features for proving correctness, but Daphne helps a little too much, so hiding with labels and reveal. And then I have some examples here. Let's see. For example, that set difference is not associative. So here's a lemma. The assignment asks for a lemma that returns a result. So an existential, like a witness, for the fact that the set difference is not associative, right? So the student needs to assign values to the result parameters from this lemma that will make the property hold, that will demonstrate that set difference is not associative. So that's really nice, and then I'm showing them how to prove in the solution, how to write such proof either with calculations on Booleans or calculations on sets as well. Let's see what else is really nice that Daphne helps me. That's simple. Right, bijective functions and cardinal equivalence. Okay, so what is cardinal equivalence? So what does it mean? The two sets are cardinally equivalent. It means that there exists a function from A to B that is bijective. Okay, so we need we used Daphne to define what it is for a function. A function as a relation, a binary relation is taught as sometimes as a set of pairs. So we have sets, we have pairs, we have isets for infinite sets. We have set comprehension. So we can do all those things really nicely with Daphne. And what did I want to say? The set comprehension is so strong, and the infinite set comprehension, and the ability to express an existential quantifier to quantify over sets. This is what has helped me to teach the last part of the course, the diagonalization of Cantor. That there's no surjective function from a set to its power set. And Uri Avraham, in his course in Ben-Gurion University, wrote that on the whiteboard with 4 lines. I wrote that with Daphne the same way, in 4 lines. That there is, and it works. I love it. So this is about sets. Let me pass on to the logical part, which is more recent. So it's the 3rd year running for this course. The first 2 years, only the set theoretical parts were demonstrated in Daphne, and I've used Daphne to show how to prove things. And only this year, we've started formalizing the natural deduction. So here we teach the proof really in a very precise way. And there are lovely stories to tell about that. So I want to show that. Let me show it. I show it here maybe. Maybe I'll show it here. I have it here. So just by the book, we can write a proof of a sequent. Sorry about that. A proof of a sequent. So what is the sequent here? Let me browse for a shorter one. Let me start with a short one. Yeah, a short one. Just saying that if we know that P implies Q implies R, and P implies Q, we should know that P implies R. And there is this short proof here in 7 steps. And so here we've been using Daphne in a different way, like embedding in it like a domain-specific language for formulae. So this is the difference between the way we have formalized natural deduction than the way done at Amazon. The way done at Amazon is great to teach people to prove things in Daphne. I'm trying to teach students to prove in general propositional logical sequence. So we go by the book, and so the formula is a data structure. We have a little parser and going back to strings. We have the proof is a data structure, right? So the proof, the tree of the proof is a data structure. It's just a pair of the result and the justification. What is the justification? There's a data type for the rules, for the inference rules, and they speak. Huth and Ryan describe 15 rules for propositional logic. So we've used Daphne for that. And what I'd like to show about that in a larger proof, right? And those little, what they call boxes are for temporary assumptions. You temporarily assume, for example, not P, and proof by contradiction, you reach a contradiction. I couldn't find the character for bottom, so I wrote F for false. But you reach bottom. At the end of the box, it means that you can conclude that the negation of your assumption holds. Or if the assumption itself was a negation already, you can prove by contradiction the property itself. And so we can prove, so the fact that we can now print out proofs, as the proof is a data structure, allows the students to come up with the proof and try them out without understanding how I implemented the domain-specific languages. It's not really important. They don't need to understand Daphne to a large extent. All they need to do is copy-paste from my examples. I showed them very many examples, and then do the exercises, and they manage. And then they manage. Okay, one thing they managed that was interesting to me as a teaching assistant for me is in grading the first assignment. In the first assignment, I haven't said anything about Daphne, just on paper to write some sequent proofs. And there was an optional bonus exercise that I proved by an ugly case analysis in 31 lines. So this is this ugly proof. 31 lines. And then I see in the submissions of the students, it's done in pairs, one pair submitting a solution in 14 lines. And I look, and I taught them, right, so you try to prove according to the structure of the result. And if that doesn't work, maybe prove by contradiction. If that doesn't work, case analysis. And they did proof by contradiction in 14 lines. Now, that was presented on paper. So Daphne helped me. This proof, the same property, what does the property say? Intuitively, I didn't even know it was correct. What does it say here? It says that if P and Q implies R, then P implies R or Q implies R. If you have intuition for that, great. I don't. So it took me 31 lines to prove this, and they did in 14. In 14, with assuming the negation of the result, and then reaching one contradiction, and then reaching another contradiction, and beautifully, they have a 14-line proof. I don't need you to read actually the proof, although you can afterwards, but what helped me is I immediately typed it into Daphne. And I asked Daphne, is that correct? They made a couple of typos with the brackets, but I fixed that and it works. So it's nice. I teach them how to debug the proof. So the proof really looks like that. I have to show you, and then I have to conclude in about 1 minute. So just before concluding, I'd like to show you how it looks, the proof, and then how, just a hint that they can debug proof. So sorry, I'm not in the right place. I want to go to the short proof. Here is the short proof. Oops, sorry, what did I do now? Don't know what I did. Click the wrong thing. So just to show you how, maybe the shorter proof is more important to see. No, so here I show the printout of the proof, but where is the actual proof here in the code as Daphne code? It looks, one more, there's the sequence, there's the proof. Okay, I made some comments here, but it looks like steps. Okay, instead of the formula in textual representation, it's a data structure, like prefixed the root of the formula, and like a tree of the formula is. So they can write the proofs, and then I showed them. If Daphne says there's ensures that the proof is correct, if it says I cannot prove this post condition, you come up for each step is a line here. each step you can, it's a local variable, you can assert that by itself it's a correct step. And the assertion that tells you, no, I'm not convinced, you know that you need to fix it. So they submitted, yesterday, they submitted one of the pairs that submitted a solution to a proof that was not, that did not verify. And I looked at the justification for one of the steps. All they needed to do was to reverse the arguments to the justification, and it would be fine. So it's really, you need to take care of the details to get convinced of the correctness. What's for the future? I have a slide for that. For the future, well, compare it with how logic has been used for teaching, or proof assistants have been used for teaching in Lean, in Coq. To be honest, I don't know. So it's out here, and let's think, and let's think, what are the advantages? So Daphne is a programming language here because I have the main where I print I print out the proof and the formula. Also the truth tables, I have an example here that given any formula and the variables, we generate all the combinations of truth values to the variables and the last column of that formula in the truth table. I have to finish. So I will just say that Daphne has helped, hopefully helping the students. They don't all like this, it's a burden. But it helps me, and it will be interesting in the future to do the same for first-order logic. Predicate logic I tried, but it's harder. Substitution on the tree of the formula, it's harder. So hopefully this will be one of the next steps. Thank you.
Okay, maybe James can set up and in parallel if there's one quick question.
I've got a quick question, actually.
How many people did you have in your course?
Now it's 70 people in 2 groups. Yeah, it used to be between 30 and 40 in the first couple of years.
Okay.
Yeah.
Cool.
Okay, our next speaker is James, who will also be telling us about the use of Daphne for teaching. So, thank you.
Something like that. We all know that a talk is supposed to be an advertisement for a paper. And I guess this talk is actually an advertisement for this paper, which is a couple of years old, but not enough people have read. And I had to give a remote presentation, so I thought, why don't I come here and wave my arms? Now, I don't want to say I'm here on the basis of false pretenses, but kind of getting close. The experience, this was basically the last thing I did as a professor before my university told me to. Anyway, we can talk about that afterwards in the pub, but I'll need to be quite drunk. And we had this course, SWEN 324, which was actually originally taught by my advisor, Lindsay Groves. If any of you know him. And I sort of inherited it when he left. And the important thing about this course was we have a software engineering degree. We want to put about 120 people through in a software engineering and cybersecurity theme. It's in the middle of the 3rd year of our program. It's a required course. What this means is that if you fail, you either drop out of the software engineering stream into the 3-year BSc non-accredited computer science stream, which a lot of people would choose to do and then go off and get jobs, or if you are committed to doing the engineering side of things, and I guess in this building, IAT building, we hope you would be, you're going to have to spend another year at university until this course comes around again, or at least this was the way it was, until you're able to pass. Unfortunately, my colleague David Pearce made up a new course, and then, which was a lot easier to teach, and when we both, in fact, left Vic, this course was dropped because nobody else wanted to teach it. That's a separate thing. The stuff people have seen there is effectively some first-year courses that are common across the engineering program, which have a bit of basic logic in it. And then second year, there's 261, which is algorithms, and the rest of it is effectively programming. So the way we did this, or the way I did this, was what I call programming first. And in some sense, it's very similar to what our previous speaker was talking about, but in real sense, it's actually the opposite. Because let's face it, none of our students, we're, I guess, a regional university. We used to have a great computer science department. It's very focused on programming. And most of the students are afraid of mathematics. Perhaps they've had mathematics at first year or logic at first year, or they've been forced to do differential calculus. I used to make enemies in curriculum meetings by saying, yes, I definitely want our students to be able to do algebra and calculus. I want Boolean algebra and I want lambda calculus. And let's face it, even the people doing our boutique engineering stream that was there effectively as an employment program for people from the physics department, many of whom are still there, they were all going to get jobs as programmers anyway. So frankly, learning that kind of stuff would have been more useful than learning traditional algebra and differential calculus. These people are programming centered, and what I realized the underlying theory was, well, look, what does it mean? Well, they're going to be able to write for loops. We know they can write for loops. We know they can write SQL queries. They do that at first year. We know that they're able to write if statements or matches or cases. Well, intellectually, how is this different from writing quantifiers? How is this different from doing Boolean algebra? You can't be a programmer if you don't understand whether it's recursion in Haskell or whether it's a for loop or a while loop, or if you can't understand how to build if statements in conditional structures or pattern matches, you can't do it. We know all these students can do it because I've been doing it for 2.5 years. Therefore, there shouldn't really be any more intellectual content except you're going to have to learn a new syntax and perhaps a new way of thinking about things because you're in this magical world of formal methods. That was basically the approach, centered around programming, driven, I guess, like the previous talk, by examples with a lot of iterative and automated feedback, which is one of the things, the great thing about automated marking is that the marking is automated. The not so great thing about automated marking is that it's not automated, and what it means is not only do you effectively have to mark every single assignment before the assignments come in, you actually have to mark every single assignment before you finalize the assignment description. So, because, you've got to be able to write the automated test so that when the assignment goes out, you've got the automated tests ready for when people start working on it. Because as well as automated testing, we want to have this iterative feedback, and the big advantage of something like Daphne is you can actually leverage the fact that it will prove things in order to get you that sort of feedback just with the nature of the fact that it is doing all the, I guess, extended static checking, one could say. We haven't got onto him yet. And we taught this with a flipped classroom. We taught this in what turned out to be the middle of the pandemic. And we did get very good results in the sense that I think we got the best, not individual teaching evaluations, but the best evaluation for the course that this course, which had been taught at second and various versions of it had been taught for something like 20 years. And as far as I could find for the records, we were significantly better. Unfortunately, of the members of the staff, most of them have retired, or the PhD students have, gone off and done other things, etc., etc., etc. So in some sense, I'm here on false pretenses. That's all I was planning to say about the course, unless people have other questions. I do have a set of slides, but basically I was going to be somewhat mean about Daphne. Because, teaching all these people and now doing Daphne myself, there is a longer version of this talk, which I think would make an excellent keynote, but of course nobody's going to invite me to keynote POPL about everything I hate about Daphne and Haskell and Rust, having had to learn these 3 languages in 18 months, which might be why my brain kind of melted when I got COVID. And anyway, right. So, how long have I got? It says I should segue to the final bit in 8 minutes. I'll try and go a little bit quicker, because you all know Daphne, right? When I gave the Haskell and Daphne version of this talk, I'll comment from Jeremy Gibbons said, I was listening along to the Daphne version, and I was thinking, good, is it really like that? That's horrible. And then he said, and then James started doing the same thing to Haskell, which I'm not going to do today. And he said, oh, James is just completely wrong, and it's all rubbish. So bear that in mind. Here we go. one of the things we say about Daphne is it teaches design by contract. I know that's not the official Daphne logo, but it just really, really works for me. Ruslan's got the best hair in the business, we all know that, and he's very enthusiastic. This is actually where we start, and you know, there is a method to my madness that is based on more than syntax. Really, we've got an add method here, we've got an add function here, and you know what's going on. And this is actually an example I would give in the class, pretty much the way I'm doing this now, and say, okay, what should happen? Because the class was flipped. People had to do exercises before the class, and then I would come through and basically say, okay, where are people up to? In fact, I knew that from our exercise system, so I had ideas about what questions they were going to ask, and the preparation for a lecture mostly involved drinking coffee, because I was going to answer any question in real time that people asked with Daphne live. And frankly, spending a couple of days before each lecture to prepare a set of slides would have been less work and less emotional energy, but I don't think people would have learnt as well. And one of the nice things about Daphne is because it's got the IDE and stuff, you can get away with that. So, with a few minutes to go, why does one verify, why doesn't the other one verify? And you can see we've got the red line there. It is, the assertment might not hold. Why not? Well, the reason is because the short answer is perhaps better from I would say Daphne uses design by contract. And as we heard in the testing talk, Daphne's methods are verified against their specifications, whereas Daphne's functions will be looked through and verified in terms of their implementation. And this is something that students need to learn and need to understand and need to get an idea on what I'm going to call the conceptual model of working with Daphne. And so showing examples like this one I in fact quite like, shows that, because the way to fix this is, well, you have to add in the specifications to the method, to the add-m here. Where was the method? There it was. It doesn't have any specifications, so Daphne will not be able to reason about that at all. I've already only got 3 minutes left. So there's a bunch of other things which I'm not going to talk about, which are really amusing, to do with the fact that Daphne is not an expression language like Lisp. It is a statement-oriented language, and refactoring between the statement-oriented parts and the expression-oriented parts is fun, to say the least. But that can wait for another. I particularly like this situation you can get here, which even though I'm programming Daphne and have been for a few years now, I still do on a regular basis if I have to refactor from an expression to a statement or vice versa.
So can you pause on that? Is that because the braces there are used as set building notation?
Yes, that's right. So in the functional subsyntax, which is kind of how you have to think about it, the curly brackets give you a set. But in the expression, which you can see in the first, where are we? You can't see that at all, because both of those. Whoops, where are we? Both of those things are in the function. Both of those things, sorry, are in the functional subset. Even though this is a method, the method there at line 31, when it comes to the expression, switches into the expression subset. Right. You can also see this is because the expression syntax being ripped from Haskell requires a then, or ML, or Pascal, whereas the, requires a then, but actually the refactored syntax, where there is the version that doesn't work, doesn't need a, where is it? Do I have one? I don't have it. Doesn't need a then if you're actually in statement land. Why? Well, because C# doesn't need a then, because C doesn't need a then, because I don't know. Well, we all know that, you know, Bourne and Co. didn't like typing much.
Because it's different, right? That the expression version should be differentiated from the statement version. That's a good thing.
Well, you could argue that, and people have argued that, and I've had this argument with Ruslan at least once, and I'm happy to have it again. So there's a bunch of things like that. This is another one, which is, you know, where can you have this one actually I think is fine. Lots of languages say you can't have mutable state defined at a module level. Well, that's great, so you have constants defined at the module level. But where it comes unstuck is if you try and do this and have those constants inside a method, which you can't have because so this is more than just syntax, and Sophia's not in the room, but I did this diagram especially for her, so if you see her, tell her that James did a diagram for her. This is what I would like to teach people about from the terms of the semantic model, and I've even used Greek symbols here, so we've got some states, and these states are kind of collections of effectively propositions or facts, and we can have pi, which are the predicates, which are confined within a particular state and tell you some information about it, and you have functions that come out of a state and also define some information about it. That's fine, that's half the story, and then that effectively gives you this expression language, and then on top of that, you can transition between the states, and you do that with a semicolon. Or, for the Haskell people, you could call it a monad. I don't actually know what a monad is, but I'm told that that's what it does. So, you can believe that or not. Anyway, there it is, and in Daphne, that monad is represented by the semicolon, which gets you from one imperative state to another imperative state. And that's important because certain things will change and certain things will be carried on, and you may have to reason about the difference between states and whether things are unchanged or not, etc., etc., etc. Come to my half-hour-long talk on Saturday, at WITS. If you want to go into that in some horrible detail. Okay, that's the model. I was then faced with having to explain this. So the good thing is, here, this function, that's easy to explain. It's a function. Why doesn't a function end with a semicolon? Pascal was generally thought bad for having semicolons as separators, not terminators, but in any C format language, you would have to put a semicolon there to terminate the thing, but in Daphne, it's a mistake if you do, the same actually as in Rust, because you've got to let the value out. But the story I've told about states and monads and semicolons is perfect, because it says, well, of course, you shouldn't have a semicolon in there, because there's no state transition. You're in the same state, it just comes straight out, that's fine. And then here, we are doing something imperatively, something similar but imperatively, and we've got a semicolon for our assignment, and we've got a semicolon, colon equals for assignment, and we've got a couple of semicolons as we move along between the various states. That's all fine. Okay, now please explain to a room of quite clever 19 and 20-year-olds what the hell is going on in the last line. Right, it's a function, but we're declaring a variable, which we can change, except we can't change. You can't assign into that variable. And we're using a semicolon even though we're actually defining a value. We're a colon equals even though we're defining a value, and then we've got a semicolon. And this is where I say my only effective teaching strategy was to sort of move from pedagogy to apology, or frankly at this point, phrenology. In fact, you can explain this in terms of the evolution of the Daphne programming language, but it's like, why didn't you just pick let and in? Sorry.
I don't quite understand that, because you're saying you're not complaining about syntax. But that was just a complaint about syntax. I'm having trouble understanding the...
Well, it's not I'm arguing it's not just a complaint about syntax, because what I've tried to build up an argument is we have a conceptual model. That conceptual model is tied to the language syntax, which is the way I tend to teach. And then here, we kind of have to break that and say, well, that semicolon there, it's sort of syntactically the same, but it certainly isn't an operation that changes state. And that use of the keyword var isn't allocating a variable. In fact, it's doing exactly the same as the keyword const does in other contexts, but you're not allowed to use it.
Would you be slightly happier?
Yes, I would be quite a lot happier. Or const, or con, or let. The point is, I guess, this is why this is nice. This I think it's really good, and I think it's really great that the Daphne team sorted out this horrible mess. Which they did at 4.0, because you can actually explain what the hell is going on. If it's used in the proof only, it's ghost, otherwise it's normal. And just trying to explain the difference that I have managed to explain already between the functional stateless world and the imperative world, which uses methods, is kind of screwed up when you've got function methods and predicate methods, because people would, in a class this big, would sit and say, well, is it a function or is it a method? Which world is it in? I am a member of Working Group 2.16, the most recent and the least famous IEEE working groups on programming languages. And, you know, we do like our syntax. But for better or for worse, syntax is the user interface of a programming language. I think the conceptual models are important, and I keep finding this myself with working with Daphne, is you have to kind of understand about how Daphne wants you to think about a program in order to be able to get this done. And again, this links into syntax, because I think if we're trying to teach people these languages, we actually have to teach at the conceptual model level. And, you know, you can go into the old Fred Brooks argument about the essential difficulties of doing something, like can I manage to express the proof, versus the accidental difficulties of doing something. And the trick, to quote Douglas Adams, is you don't want to get in a situation where you get so happy about resolving the accidental details that you miss out the point that you haven't really managed to attack the essentials. Fred Brooks talks about language complexity budgets in the Mythical Man Month. In his later book on language design, he talks about having an ideal programmer or an ideal customer for the system. And I think as Daphne carries on, having a good model of that will also help guide decisions about, you know, well, effectively how to spend your complexity budget, how complex do we want to, do we or the team want to make the language, et cetera, et cetera. Sorry, I'm over time, but started late. Thank you.
Maybe the next speaker can get set up.
Yeah. Sorry about that. Do you want that? You've got your own, do you have your own?
Yeah.
Okay. I'll take questions or abuse. I'm actually not registered for the conference because POPL. But I'll be here for the workshop on Tuesday and on Saturday. You can find me if you need to.
Thank you. Okay, our last talk of this session before lunch is from Jan, who will be giving us a comparison between Daphne and Idris.
Now the trouble is working out where the next one is. Sorry about this. I'm aware I'm just before lunch, so this is actually quite embarrassing, so. Right. This is not going to plan, but that's fine. Cool. So I'm going to try and keep this relatively short because as judges are very angry before lunch, so to our audiences. So this is joint work with our previous speaker, and just to tell you where I'm from University of Strathclyde, but also part of the Scottish Programming Languages Institute, which is a new thing we're trying to get out there. So this is also a bit of a stealth teaching talk because I get to design a new course that will involve these two languages that I'll be talking about, and so this is part of my reason is to learn about Daphne and Idris, and what better way than to be a wolf in sheep's clothing. So, yes, great. So we've been talking about verification of our languages, but let's look at the wider context of where we are at the moment, right? So there is, if you're from Scotland, then you should know about the Greg-Michelson scale, which on one end you have lots of squigglers, and this is all about programming language design, right? So you have squigglers. Squigglers like math, and when they design their programming languages or proof assistants, you'll get really nice tooling for doing theorem proving. So you'll get things like Agda, Rock, Lean, Isabel, and they're very much designed for verification, full verification, right?
But at the other end of the scale, you have bodgers. We like to build things, right? So what tools do we use? C, Rust, Go, Java, that sort of thing. And the scale of verification on one end from bodgers go, well, you can't do anything really to do with verification. But you go to the other end, you can do all the verification you want to do. And there's that sweet spot in the middle of, well, what if you only want to do a little bit of verification in the core parts of your code, and then the rest you can just go on. And we saw that earlier today in the Tej's talk, and talk about and they've done some really cool stuff with the Daphne doing the transactions, but the network stuff they don't do, and they call out to Go for that, right? But the thing is, that's cool. You can sort of say, look, I want to verify a small kernel, and then do that, okay? But what about the sweet spots? Now, 2 languages, Daphne and Idris. So I'm an Idris user. So for those not aware, Idris is a general purpose dependently typed language developed out of the University of St Andrews in Scotland. I've been using it for 10 years now. Wow. I'm getting old. But then so Idris. So I was at the European Conference of Programming in the Pacific Northwest, and I attended a talk by Rustin, and he started talking about Daphne. And I thought, ooh, Daphne sounds very interesting. You can do programming, you can do verification. You can sort of tread that middle ground of having some stuff you don't verify with having stuff you do verify. And it's got that, it's that sweet spot of what do you care about in your program and how rock solid you want it to be. And as Rustin was giving his keynote, I heard things, and it was mapping to my knowledge of Idris, right? And we talked about it a little bit at the end of that keynote, if you remember, and that you talk about Daphne, you talk about your design by contract. You have your specification, and you build your code, and you check your code against your specification. And I go, well, to me, that sounds like correctness by construction in the more Idris dependently typed world, where you build things up from the ground up, but you're building up your specification, and your specifications are code. It's the Curry-Howard correspondence, right? And then you hear about things like, oh, we've got HOR logic, separation logic, blah, blah, blah. And I go, oh, I use dependent types. And as we go on, as Rustin was talking, he talked about ghost types. Well, I'm not afraid of ghosts, but I like quantitative types. And in quantitative typing, it's a bit more nuanced than ghosts in that it's not saying how often, it's not saying when things should appear, not just that. So with ghosts, it's compile time relevant and runtime irrelevant. But in quantitative typing, you have a 0 quantifier saying it's only runtime relevant, and you have 1 that says it's linear. You can only use it once at runtime. And then omega is the big thing of you can use it many times. And this quantitative typing was from colleagues of mine at Strathclyde. But then just going on and just to give you an outline of the 2 languages more, and that Daphne is, multi-paradigm. Idris is really functional. And then Daphne you have interactive editing through the language server protocol, and Idris you have this notion of interactive editing. Now, for those not aware, I use this specifically in that within Idris, you have what are called typed holes. And if you've ever done any interactive theorem proving with tools like Agda, you can put a little question mark, and even in Idris, you put a little question mark, and in Haskell, you can put an underscore that says, tell me what's supposed to go here by the type. And that's a really powerful feature when you think about it, and I won't show examples, I just want to highlight it in that. So when you have a typed hole, you can say, what's missing? And if you're in a statically typed language, the language will say, well, we expect something of this type, okay? And that's really cool because then you can narrow it down saying, well, what do I have in my typing context? What's available at the local level? And use that knowledge to sort of fill in the rest of the program as you go on using some program synthesis. So I'm already starting to talk about the differences between the 2 languages. And we'll get further onto that, but I also want to notice that, Rustin was saying, Daphne's practical. It's used at Amazon. Cool. Idris is practical. It's used in academia. But the thing is, it's in terms of Idris, it's like it is when you compare it to tools like Agda now, we don't like to talk badly about the competition. We like to say positive things. And the way I looked at it is that Agda is very much or all these like verification heavy languages is they're geared towards proof assistant more than general purpose programming. In tools like Idris, it is a general purpose program that you can do theorem proving in. And it's a really nice little mindset switch. And this is what I mean by practical is that you can actually write you can actually write code that does networks, inter-process communication. You can do lots of practical things in this. And so this is like these 2 languages, like, and as Rustin was finishing his keynote, it's like, oh, these 2 are quite similar. When I design my course, I want to use these two languages because they provide different viewpoints of the same thing, which is sliding that scale of what you do for verification. Now, right. And so how could I compare them? Well, I need a co-conspirator, and James was that co-conspirator, and he knew more Daphne than I did, and I know more Idris than he does. And we thought, well, listen, this very naive, unsystematic way to compare the two languages, let's select the same problem, and then verify it in these two languages, and then compare what's going on. Because, it's a litmus test, right? Can we do something, can we tackle the same problem, verify it and say what comes out of it? Okay? Right. Sorry, I'm aware I'm going a bit more faster than I would normally do, but I'm aware because I'm also quite hungry. So the problem we chose was the Dutch flag problem, because that is the quintessential Daphne. If you go to the Daphne homepage, you'll see the Dutch flag problem. You'll find YouTube videos on it, and it's something that I knew I was speaking to a Daphne audience, and you know this problem very well, and so I'll be able to talk about it. But the caveat is, it was designed for insertion sorting. If you're not aware of the problem, which I don't think many would be here, in that you have pieces of the Dutch flag, red, white, and blue, and you want to sort them into their constituent ordering in some way or fashion. Now, the original problem was to do this for insertion sort, but we sort of took a step back from that because of Idris and its functional heritage.
Do you mean insertion sort or quick sort? It's the pivot, routine of quick sort.
Yeah, quick sort, yeah.
Okay.
Yeah. So it's a... This is just a typo, and let's just move on, yeah. Because this is our solution for Daphne, which we took from the web page, because look at it, and you go, the thing from this that's quite important is there's a big gap missing from it, right? And you know what's going to come next, but the whole point is that in this language, you can write your implementation first, and then say, right, I've written it, how do I know it's correct? And you go, well, let's write this specification and check. But you could do it the other way around, right? And that's quite a nice choice of saying, you can concentrate on your business logic, and then say, look, let's verify it, or you can say, let's concentrate on our specification, and then use that to guide our implementation. And that, this is it's a nice way of working that you can do the both. You can do either way. And in Idris, you can do something similar as well. So I'm not going to detail the solution here, because there's a nice video by Rostan on how it works. I suggest you check it out. But what I want to talk about is the intuition behind the Idris approach. Now, we actually use merge sort, because that's more quintessential. And unfortunately, one of the differences is this solution actually goes over 3 slides, and I didn't want to have 3 slides. So I thought I'd just take the quintessential essence of it, which is filtering a list, because if you're doing merging, you want to move things in order. And also I get 1 slide to talk about a specification and a solution. Now, what we have here is a data type in Idris, and it's dependently typed. And there's quite a lot to unpack here, and I don't really want to unpack it too much. But if you ever see a little 0 before binder, and we see it in the very first definition of our type constructor, that is erased at runtime. Okay, it's a compile time only notion, and that is what we have is a generic filter that acts on a generic predicate, and we define the specification for the specification, the input and output, as you have a list of x's as your input, and you want to filter it into things you like, the y's, and things you don't like, the z's. And we want to have a specification that says, that describes what's supposed to happen. And it's a bit more nuanced because we're hiding a lot of detail here, right, of what's happening, and a lot of it's implicit. And so the empty case is not. It's saying, well, if you've put nothing in, you get nothing out. That's the base case. But this is a structural inductive specification. And we say, well, in the keep case, if you do the cons, so if you're consing over your list, well, at your head, you'll have an X. And then you'll say, can I find evidence, an inhabitant of the predicate that says you should keep it, right? And if you can, that's great, but you have to take care about the recursive, the inductive step, and says, right, what about the tail? Okay? And then when you analyze the tail, you get back your Zs. And then you can just shift that X from one list to another. You're not shifting it, but you're saying, look, it should go in the keep pile. In the second case, right, where you have skip, which says, if you find a proof of void, that filter, that decision procedure on your predicate doesn't hold, then that signifies that you should skip it. But you don't throw it away. You say, look, instead of putting it in the pile you keep, you put it in the pile you drop. Now, the reason I'm going into this is that we're just at the data structure. We haven't even started proving that this is correct, right? And the way we do that is we write an implementation. And that implementation is just a little function. Now, you'll see it on stage right, or stage left, you're right. And that to write this filter function, we have to write a function that takes in your list of x's. It's a higher order filter because we need a decision procedure indicated by the deck at the top that says, can you make a decision on something and return that result? And what we return is what we call a dependent pair. It's nested, actually, that you have the things you have to provide evidence saying, look, this is the thing you've lost, this is the thing you've kept, and that the result is an instance, an inhabitant of the type filter. Now, I've tried to match things up a little bit, but sort of say, look, in the nil case, you've returned that evidence, and in the cons case, you do your testing. Can you get an instance of that predicate? And if so, do the recursive step, and then combine the results. But the point is here is that I've written my specification first, and I've written a proof that I can actually construct an instance of it. So that's type-driven. Now, you don't have to do it this way. You could do it another way, but we're not going to show that. But then that's an extrinsic proof. And this is what I mean by correctness by construction, is you're going from the specification, and you're saying you can only write a program that satisfies it. And that's quite a neat concept. And you can do this for large things. We'll see later on, there's a talk about how you can do type safety proofs. We can do sort of similar type safety proofs in this regard here. Now, how does it compare? Well, I've been talking about that over the last couple of slides. And I think one of the big takeaways we've got from this is the code and specifications through specifications are code. And that's quite a mind shift. If you're taking people who haven't learn't Idris or Daphne and think, well, what about specification? Well, say, well, my specifications are code, right? And in Daphne, you know, they're invariants, but some people might not think of that as code at the first sight, but in this way that. But I'm not trying to say one's better than another, but there's different ways of thinking, and that's quite important. And I think we need to learn about how we each do this. But there's other bits here, which is specification verbosity. You've already seen that. I had the Daphne on one slide. My one's 3 slides, if you look at it in fully. I realize the time, so I'm going to sort of try and hurry up. Efficiency and erasure. So the filter thing we saw, all of the proof, the evidence that the filtering was correct was runtime relevant, which means it'll exist at compile time. In our setting, we can make that a ghost variable, and you can remove it, but there's a question is, do you want to remove it? Can we have erasure polymorphism to say, look, in the case where I run it, right, do that, but erase that proof and just give me the result, and you get like an efficiency benefit by removing all the correctness for the runtime, or do you want to use it later on? Maybe if you're writing a library, is that something you want to use later on? And another proof, and where it might be runtime relevant. Other last 2 bits are specification correctness. How do I know that my data structure is correct? Well, the only way I know it's correct is if I can build a function that creates an inhabitant of that type. But then, is that correct? How can we reason about these data types a bit more cleverly? These are wide questions, and you sort of see that in Daphne as well. And the correctness, that's not a typo. In Idris, we're built off a very small language called TT, a very small, about 8 or so constructors, which everything's built up from that. We don't call out to external tools. We don't have Boogie. We don't do anything like that. It's all from the ground up from this very simple language. We compile down to it. And we type that, and we can actually verify that that's correct. Okay? I'm a little bit concerned about the Daphne stuff just because you're calling out to so many external things. How do I know that they're working correctly? And you have a like verification pipeline. And the last thing I want to say about the interactive stuff, the reason why I talked about the type holes is when I was writing my code, I could put a typed hole in saying, well, what's next? What do I have to do? And then, you know, proof search will either help me, or program synthesis will help fill in the gaps, or I have to do a bit more work to try and work it out, and it might tell me something's impossible, and you have to do that. And I think that's one bit I'm not quite clued up on in Daphne, but I'd like to see, you know, can you get that, you know, what I enjoy about Idris, can I get that for Daphne, right? Can I get that beautiful typed hole-driven approach? So, to finish, I think a lot of this, what I've seen is Idris and Daphne, complementary approaches, but the key thing is like that verification dial is like, how do you turn the dial and to what level do you turn it? Okay, and the key thing that I like specifications of code, but then maybe you want to have that separation of like that more intrinsic approach. And it's more of a case of, I'm not trying to say Daphne's bad, that's my co-conspirator's job. What I'm trying to say is, what can we learn from each other? And how can we like develop these tooling so we can, capture that middle ground of these verification-aware languages, like be able to turn that dial. Now, our research, our work is very unsystematic, and I like to say maybe do a bit more of a systematic approach to this comparison to work out what really is the differences. There might be a pedagogical aspect here, or more a case of what are the fundamental approaches to the languages that we can actually see where the differences are and learn from that and try and take it forward. Okay, thank you. And I'll leave that here. That's the merge sort specification of it's 2 data types, but I need 2 more slides to show you the implementations. So.
Okay, it's time for lunch, but maybe if there's one quick question, or if not, maybe stick around.
Happy to take questions offline.
Okay, and we'll see you after lunch. Thank you very much.
All right, welcome back to the third session. I hope you enjoyed the lunch. This session is all about doing proofs at scale and addressing side effects like brittleness that come with it. The next talk is going to be by George Jaloyan from Amazon, and he will talk about enhancing proof stability.
Thank you very much. So hi everyone. So I'm George. I'll be presenting you some nice work I did with Sean, Jenny, and Florian on how to make Daphne proofs more stable. So the claim, which is extremely intuitive but actually not that simple and quite interesting, is that simple proofs tend to be less brittle, so they break less often. I'll detail a little bit more what we mean by simple proofs and brittleness. That is the whole point of the talk. So let's start with Daphne. So a little context on how we are using Daphne in our team at AWS. So fundamentally, we are like doing and rewriting the whole core authorization engine. So this is some Daphne code for which we have written some spec. We have written also an implementation. We check that the spec is the same as the implementation, that implementation verifies the spec using Daphne fundamentally. So this generates some Z3 queries that are then discharged using the Z3 SMT solver. And the implementation is then compiled to a Java implementation and code that will be the one that will be running in real production. So to give you an idea of the scale of what we are dealing with, so fundamentally, the specification and implementation altogether is about like 17,000 lines of code of Daphne. The Java code that we are like generating is about like 3,000 lines of code. And the very interesting thing is that this Java code is running at 2.3 gigahertz. This means that the code is being invoked 2.3 billion times a second. So the scale is absolutely huge. We cannot afford any mistake, so you can guess that this is absolutely critical code, and it needs to be scaled and extremely efficient. So we are like due to this constraint, so the code is really made to work fast, and we are transferring all the burden of verification on the proofs. So we prefer having more complex proofs at the expense of, like, we have simple implementation at the expense of complex proofs. And to give you an idea, we have about like 15,000 verification conditions that are generated, and like the biggest verification condition is in the order of 9 gigabytes. So we have an SMT query that is 9 gigabytes big, and we have to send it to Z3 to deal with. So as you may have guessed, when you have like 9 gigabyte query, like what happens is we have what is called proof brittleness. So Z3 uses a lot of heuristics, a lot of like backtracking and like different things that make it like sensitive to changes that may be minor or unrelated, and we may switch, like if we switch the different version of the tool or upgrade to another Z3 or change Daphne version or just do a minor unrelated change, what happens is potentially the proofs may break. So this has been predicted of going to scale with verification tools, and this is exactly what we are dealing with. So to give you some little metrics, so each time that we had upgraded some tool, so be it Z3, be it Boogie, be it Daphne, we have at least one VC that was broken. So each and every of our updates went bad, so we had to spend some time to fix it. On average, it was 5 verification conditions that were broken on each update. Of course, the consequence of this is now we have to spend some time to fix the proofs and re-establish their validity. And this like blocks us from shipping new code, from working on other features. And usually it's in the order of a few days, but it can go as much as 14 days. And of course, like because of this instability in the proofs, so we had to forego some of the changes that we were planning to do because the proofs were just too brittle, and we said, well, we're not going to implement this feature or this very minor optimization because the proofs are becoming so brittle that we'll not be able to maintain them anymore. So this is a problem. We need to find a solution. So what may be causing brittleness in our situation? So there is some environment issues. So for instance, if we change the ISA, like Z3 compiled on R64 and Z3 compiled on x86 are not behaving the same way. So on same queries, they may give different results. Same for operating system. We have seen some differences in different operating systems. Then there may be the tooling, like Daphne versions that may not be the same, Z3 versions that may not be the same, some libraries that may not be the same, and proof hardness, which is usually what we think about when we're talking about brittleness. For instance, we have huge SMT queries, like with many unnecessary facts in context. We have function bodies that are visible to the caller, again, adding some additional data and facts that may not be necessary to do the proof. This leads to huge SMT queries, and sometimes with complex theories like mixing, arithmetic, set, and this kind of other theories may make the proof the task harder for Z3. So the first two are, I would say, not easy, but like quite manageable, because it turns out that we are a cloud company at AWS. So environment and tooling is exactly what we're able to provide. So there will be a talk this afternoon on like the different solutions to mitigate those two problems. So just follow Eric's talk. And the thing that we'll mostly focus on in this talk will be the proof hardness part. And there is no way to cut the corner. We just have to make simpler proofs here. And this is exactly what I'll present. So this is Dafny 64, which is a coding style for Dafny to make the proof simple. So what is Dafny 64? So let's say what makes a proof simple. So there are mostly two metrics that can be used for measuring the complexity of a proof. So the first one, is using the flag isolate assertions, which will allow us to measure for one VC at a time the different metrics, because Dafny bunches the verification conditions together, so it's hard to measure anything. So we have to separate them. Once we separate them, there are two things that we measure. So the first one is called the resource count, which is defined with the flag resource limit. So this is a metric that is used by Z3, which aggregates a lot of internal elementary operations that Z3 does, and this is just a measure of how hard it was for Z3 to discharge the VC. And the second one is the elapsed time. So this is just how long it took for Z3 to solve the issue. If we look, actually, so this is a graph, a plot of the resource count on the y-axis against the duration on the x-axis. We see that this is quite correlated between the time and the resource count. And we see that harder proofs tend to take more time, be it in resource or be it like in duration. So instead, we'll use just the resource count for now. So we'll just focus on this. The idea of Dafny 64 is to limit as much as possible the use of SMT automation. So our goal is to make sure that Z3 has a very low resource count so that it does not do a lot of work. And our claim is that if we manage to discharge discharge Z3 from a lot of its burden, then we could have proofs that break less often. So how do we do it concretely? So I'll give two little examples. So first one, this is the first focus. The idea is to make everything opaque. So like if we look at a very simple example of code, so this is just a while loop iterating on the variable I that has been initialized at 0, and we iterate until a value that is named foo, and we do some stuff in the while loop. So usually the way we would prove this would just be writing an invariant and let Daphne do the job. So it's extremely great at automating this. So usually that's what happened. We just write the invariant and that's it. What we're doing instead here is marking the invariant as opaque instead, which means that its body will not be available to the loop when it will try to prove. So the proofs will fail because we need to do the proofs by hand now. And what we'll have to add instead is two lemmas. So the first one is invariant initialization, which will ensure that the invariant holds at the beginning of the loop. And we'll do the proof in the three dots by hand. So we'll write literally a set of assertions that will help guiding the proof. And same, once we reach the end of the body of the loop, we'll have to show that the invariant is preserved. So we have another lemma for that we'll invoke, which will require that the invariant holds at the beginning of the loop. And it ensures that the invariant holds at the end of the loop with the new value of I. So this is exactly how we would do the proof by hand. So if I were giving a lecture on how to demonstrate an invariant, I would literally do those two proofs by hand. So this is what we are doing. Second idea is to remove post conditions altogether from functions. So here it's like an implementation of the min function that you can see on the left side, which is how we would write a min function. So it's just a function that takes x and y as parameters that returns another integer. And if x is smaller than y, we return x, otherwise we return y. And we ensure the three conditions for being a minimum, that the minimum should be lower than the two parameters and it should be equal to one or the other. The Dafny 64 version instead removes all the ensure clauses. So we totally take out all the ensures to make sure that they do not get added to the context when I call this function. And instead, I'll put them as a separate lemma. So each time I need to know that the min will give me the minimum of the two values, I will call this lemma, which will ensure me exactly the post conditions. And how do we guarantee this lemma? By revealing the min function, which will help Daphne prove it. So by separating the contract and the implementation, I can control with much more precision. I can control what I add exactly to my context. So it's almost as if I was doing the proof by hand. So each time, at each point of the program, I know exactly what is in the context and what is required to prove each assertion. So does this make the proof simpler? So this is the graph of resource count against time for one of the modules that we have rewritten in Daphne 64 style. So this is the most complex module of authorization, which is the string handling. So we have rewritten it in Daphne 64. So this was before in normal Daphne. So you can see that resource used to go up to 10 to the power 7. So there is a 1000 factor between Daphne flag in resource count and the Z3 resource count. So this would be equivalent to 10,000 in resource count. And once I plot the Daphne 64 version, so here you can see in green, I managed to reduce by 2 orders of magnitude the resource count used by Z3, and also by about 2 orders of magnitude for the time, similarly. So yes, the proofs are simpler. But does this make the proof less brittle? So now let's discuss about a little bit brittleness. So brittleness, as we have seen, is characterized by the fact that when I have a minor change anywhere in the code, some unrelated proofs may break. Same if I change the tooling. So Daphne reference manual has been giving a very good guideline on how to measure brittleness. And there is a feature called the random seed. So the random seed changes the SMT query that is being sent to the solver by changing the ordering of the SMT commands, the variable names that are used, or the random seed that the solver uses when it's making arbitrary decisions. And actually, this is a very good proxy for like those kind of breaking changes, because when I upgrade the tool, I'm not expecting something to fundamentally change in the generated VCs. The thing that may change is mostly the ordering, the variable names, and this kind of minor stuff. So actually, this is a very good proxy for measuring this, for simulating this kind of change. And Daphne has been giving a guideline. So for this, it's quite arbitrary, but it proved over experience that it works well to measure brittleness. So we attempt each proof using like different random seeds. So we use 5 here, which is the good compromise. And then for each verification condition, we have now 5 different resource counts that have been computed. And we will compute the coefficient of variation of those resource counts, which is defined as the standard deviation divided by the average. And this gives us a coefficient between 0 and plus infinity. And if this coefficient of variation is greater than 0.2, then we consider that this proof is brittle. So this verification condition needs to be reworked to make it simpler. So does Daphne 64 reduce brittleness? So this is the histogram of the coefficient of variations that are measured for the same module that we have rewritten. So you can see that like if we look at 0.1, so we have the 1.0 to the power 0, which is like everything that is under 1 and greater than 0.1. So we have about like 100 proofs that are in 100 VCs that are in this category, out of which about like 50 are really brittle. This means greater than 0.2. So we see even one that is like greater than 1 and lower than 10. So there is quite a lot of brittleness in the code base that we worked on. So once I rewrite everything in Daphne 64. So this is my new histogram. So as you can see, like I managed to reduce significantly all the coefficient of variations, all the brittleness, and the max that I have, there is only one VC that is at 0.1 of coefficient of variation, which is still under the threshold of 0.2. So we managed to like remove all brittleness from our like code base here. On the drawback, so a little bit some explanation on the code size impact. So this string processing library has 2 functions. One is string splitting, and the other is shell glob matching. So those are like 2 main functions that are in this library. And fundamentally, before in Daphne, the string splitting was 150 lines of code, and in Daphne 64, it's 50 lines of code now because like we took out all the specification and moved it somewhere else. And now instead we have 18 lemmas that are about 220 lines of code. So we have a slight increase in the code size. And for shell glob matching, it's also exactly the same. So we used to have 300 lines of code with 15 lemmas that were 350 lines of code, and now it's only 80 lines of code with 31 lemmas of 860 lines of code. This is actually like, there is a little like unexpected good outcome, which is now the code is much simpler. Now that we have taken all the spec in a separate file or lemma or separate module, now actually the code is much simpler. So when we read the code that is really doing the real code, the real non-ghost code, actually we can be able to much easily understand what is happening. And conclusion, so we have seen that simple proofs indeed are less brittle. And Daphne 64 helps reducing brittleness on large code bases. And as future work, what we may do is maybe automate Daphne 64 and have it as a style checker. So it would be nice if we could do Daphne -- Daphne 64, and automatically it will check for all of these. And we still have to use the resource limit to play with the resource limit to find another cutoff value. So we took 100 here as an arbitrary value, but we may expect that actually maybe it's 200, maybe it's 500. So we need to play a little bit with this. Thank you very much, everyone. So if you have any questions.
Thanks, that was really interesting. I was wondering, you said at the end that maybe there could be an option for doing the Daphne 64 checks automatically. To what extent could the transformations be completely automated? And for example, could this actually be part of Daphne behind the scenes? Behind the scenes, it will reorganize your annotations in a more SMT solver friendly way, but give you the freedom as the programmer to write whatever you like the best.
Some parts of it may be automated with some analysis, like for instance, all the reveal statements that we're adding. Maybe there may be some analysis or like building some trees of dependencies of assertions to be able to control more finely what is exactly revealed. But some other checks that were like some of the rewriting that we have been doing was also related to changing the types that we're using, or like things that may be like less automatable, like some of the things that like totally rewriting, like for instance, there was one for loop that we had to rewrite in another form, and like instead of having a break statement, we had to instead like have an assignment with a return. So those things may take a longer effort to automate.
So it's not a completely mechanical process. There's some creativity required.
Yes. We spent quite a lot of time to be able to like reestablish all the proofs in Daphne 64 style.
In the example evaluation you showed with the lines of code blow up, what about clients that use those verified modules? Like now they need to invoke those lemmas. Do you have a sense of how much that changes the proof burden for clients of those libraries? Or are these not really clients that have libraries that have end users?
There is only one client, which is like our library, our authorization library. So this is the part, a small part of the authorization library, which is the string handling and string processing. The thing is calling those lemmas, that's one of the main points when we had to repair all the proofs, because now everyone who calls those do not have access to the context anymore. So the strategy we used mostly was each time that we're calling one of those nodes, we're literally revealing almost everything immediately after. So this is not optimal. So the Daphne 64 is really well designed for a small part, and now we are extending to the colors slowly. So now we are revealing everything, and there is way better solution than just revealing everything immediately after the call. So. Yes.
So you suggested that you should remove all post conditions. How does that work for methods? Do you only have functions?
No, we have, I would say, only methods. We have very few functions.
Okay. So how do you do the part, because methods are opaque, but you can't reveal them inside another method, right?
Yeah.
So how do you do the verification of the post conditions of the method if the method definition itself has no post conditions?
There is function by method that we are using for some of them. And then for methods, what we have is we have imperative implementation, and we have a functional implementation, which is the spec, fundamentally. So once we know that the method satisfies the spec, then once we give the spec to the caller, it contains enough information not to be able to know what's inside the body of the method.
All right, thanks.
So you are advocating for this new style of writing Daphne code. would you say that the Daphne 64 mode should be the default? So the other way of asking the question is, are there some libraries where it's more preferable to use to allow everything you forbid rather than using your style?
It's a trade-off because like using Daphne 64 style makes it like you control much more what you are adding in context, but you spend more time writing everything. So if you are writing a small library in which there is no scale issues or like brittleness issues in the proofs, like don't use Daphne 64 in this thing, because like Daphne is really good at automating things, so you want to leverage this. And this is mostly like when we start having like scaling issues and brittleness issues, that's where we had to control manually what we are doing in the proofs, and this is where Daphne 64 really comes handy. But yes, for large code bases, I would advocate for Daphne 64 by default.
I think we have to move on. So let's thank George.
Thank you very much.
All right, thank you. So like Joe said, I'm Joe Cutler. I'm going to be talking about improving the stability of type soundness proofs in Daphne. This is joint work with Mike Hicks and Amina Torlock. So I want to start this talk with a quick story. The story begins 2 years ago at the beginning of my internship at Amazon, where Mike and Amina sit me down and say, can you prove the type soundness of this language that we've been working on? And I say, yep, definitely can do. And they say, so we have an interpreter that's been written in Daphne. Why don't you do the proof in Daphne? And I, slightly overconfident first-year grad student, say, sure, sounds like no problem, sort of mentally thinking, this can't possibly be that hard. Smash cut to 2 years later, I'm standing in front of you today to talk about why proving type soundness in Daphne actually was quite hard and how we managed to do it in the end. Okay. I want to set out sort of a toy language as an experimental platform to demonstrate the work that we did. This work was actually done on the Cedar language. For those of you who are familiar with Cedar, maybe you're Amazon people, think about Cedar. Otherwise, think about a toy language that has arithmetic, sort of Booleans and conditionals, records. It's sort of first order. There's no lambdas, nothing like that. It's terminating, so there's no recursion. It's a fairly straightforward language. The interpreter is written as sort of a definitional interpreter, big step style, that is a function that takes a function written in Daphne that takes an expression e and returns either a value, which is the value that the expression evaluates to, or some kind of evaluation error, which looks like either a runtime type error, you tried to add an int in a string somewhere, or maybe a divide by zero error where you did something wrong that maybe the type system couldn't catch. They also have written in Daphne a type checker, right? A function check that takes an expression and a type and either returns sort of okay, that type checked, or maybe a typing error. The safety property that we're going to be interested in for the purposes of this exposition is that is this one, that E, an expression, is safe at a type T if when you run the evaluator on the expression, one of two things happens. Either E evaluates successfully to some value, and then the value that you get out at the end actually does in fact have type T. That's case one. And then case two is when you run the evaluator on the expression, you get like a divide by zero error. Okay? And so the type soundness theorem that we're interested in proving here just says that when you run the type checker on E and T and you get back okay, then E is safe as a value of type T, i.e. it either runs successfully or it errors with an error we can't possibly catch statically. So, to prove this in Daphne, we just sort of, encode it as a lemma with the precondition that, check succeeds, and with the postcondition that is safe holds. Okay. So, our first attempt at this was basically direct proof, right? To discuss how the direct proof should go, I want to take a look briefly at how the evaluator works and how the type checker works to sort of get a flavor of this. So the evaluator is written in, like I said, sort of direct recursive style, sort of like a definitional interpreter. I'm going to use the case of the add operation. I'm going to use the case of the, I might be using old syntax here or something. The I'm going to use the case of the add operation, just sort of illustrate what I'm talking about. Imagine this extended for hundreds and hundreds of cases for all the constructs in the language. Okay. So in the add case, to evaluate an add expression, we first evaluate one branch, then we evaluate the other. We check that they both evaluate to ints, and then we return the int that is their sum. Right. Straightforward. The checker, also just sort of standard direct type checker. Again, I'm going to look at the add case. We check that E1 and E2 both have type int, the two branches of the add. Then we're going to make sure that the type we're checking the add expression against also is an int. If all of that's true, then we return OK. Otherwise, we return a type error. Okay. I want to briefly take a look and illustrate just sort of at a high level without diving into the Daphne how the proof of the add case of the type soundness theorem should go. So we start by assuming that calling check on add and t returns OK. Then sort of the solver is going to unfold the definition of check and get to the fact that E1 checks against t and E2 checks against t, and then we also made it to the correct branch of the if, the one that returned OK, which means that t has to have been equal to int. Then by applying the IH twice, the induction hypothesis twice, we get that E1 is safe at int, E2 is safe at int, and then unfolding the definitions of is safe and eval and sort of reasoning through things, we get that E1 plus E2 is itself safe at int, right? This is basically because, one of three things can happen. Either E1 and E2 both evaluate to ints, and so their addition does as well, or one of them evaluates to divide by 0 error, and so the whole thing blows up in the end. We can encode this in Daphne just by writing down the two recursive calls to apply the induction hypotheses to E1 and E2. This is actually quite slick. Just apply the IH. Daphne handles getting from check to check of E1 and E2, and then from safety of E1 and E2 to safety of the conclusion, right? This is really great. There's a big problem here, though, and this is where we got pretty stuck. This is super unstable in the sense that when you're trying to build this proof of hundreds of cases, you start working on one case, and you finish it, and you get the little satisfying green check mark in VS Code. And then you go on to moving to do case B. You fill in case B, and you get the little check mark there. And then you go back and you look at case A, and case A now has the red X next to it, and it failed to verify. Right? The proof, the outcome can change dramatically as you change the proof itself, which is really quite frustrating. And this is the part where I step back and say, oh God, what have I gotten myself into? This is way harder than I thought. And our hypothesis about why this particular proof is unstable is mostly because the solver has to reason about two very large definitions simultaneously, right? This check function and this evaluate function are both, quite large definitions with lots and lots of cases that are both monadic. So we stepped back and we're trying to figure out how can we come up with a more robust solution? Because at this point, it was not clear that we were actually going to be able to complete the proof unless we could find a way to make this stable. It just wasn't feasible. Right? So you go talk to various folks, and as we saw in the last talk, the answer to an issue like this is to opacify and specify, right? Find some definitions, make them opaque, give them specifications, only let the solver reason about them through the specifications. But we really ran into a conundrum here, which is what are we supposed to make opaque, right? Check and eval are the two functions involved, and they're both sort of like do what they do kinds of functions. They don't have obvious total specifications that we can use to reason about their behavior, okay? So I want to go back to the proof for inspiration, and in particular, I want to take a look at the last step of the proof. And I want to think about to complete this case of the proof, what do we need to know about the safety property? It turns out that the only thing we need to know about the safety property in this case of the proof is that E1 being safe at int and E2 being safe at int jointly imply that add E1, E2 are safe at int. And that's the only fact that you need to know about the safety property. In fact, you need to know nothing about eval to complete this proof. All you need to know is that fact about the safety property. And so this gives us the spark of inspiration that we can just make is safe, the conclusion of the theorem itself, opaque, and then manually prove these safety lemmas, saying that E1 being safe at int and E2 being safe at int jointly imply that add E1, E2 are safe at int for all of the constructs in the language. And this proof basically follows the structure that I said before, right? Either they both successfully evaluate, or one of them errors, and so the whole thing errors. And this is and then you take those safety lemmas and you insert them directly after the calls to the recursive calls in the proof, okay? This is much, much more stable. The reason is that the solver now only has to reason about check. It can't look through the body of is safe to look at the definition of eval. Okay. I want to quickly touch on what's actually going on here. Some of you might have noticed that all we're doing here is we're using the induction principle of the type system as it was designed. So the type checker, that function that we wrote in Daphne, really implements some inductive relation, right? So the check function is really a decision procedure for some inductively defined relation E has type T, which was written on paper, hopefully somewhere, in a document that has a bunch of inference rules on it. And this basically tells us that the induction principle of the type system means that well-typedness implies any other predicate that interprets the rules of the type system. What do I mean by that? Let's say that we have some predicate P, and we're trying to show that E has type T implies P of every expression in term. To understand this, let's take a look at a case, like add. We look at all the rules, we invert them to get that their premises hold, we apply the induction hypothesis to get that P holds of the premises, and then all we need to know to complete this case is that P holds of the conclusion, assuming that it holds of the premises. This is what I mean by well-typedness implies any predicate that interprets the rules. If we can do this for all the rules in the system, then P holds of every well-typed term. So the upshot here is that if is safe is opaque, but still interprets all the rules of the type system, then all well-typed programs are safe. Okay? A quick question that you may be having is can we go further? There's a whole other half of the proof that maybe we can leverage as well. And the answer is yes. We can play the same game again and notice that the only thing we need to know about the check function to make this case of the proof work is that if an add checks against T, then E1 checks against the type, E2 checks against the type, and the type is equal to int. And so we can play the same game again by making the check function, the type checker itself, opaque, and then proving these inversion lemmas, basically, for all of the rules in the type system. In a sort of nice little twist of fate, all of these inversion principles are sort of automatically provable. You don't have to write any assertions for any of them. And then you take these inversion lemmas, you insert them before the recursive calls, and you get even better proof stability behavior out of this. So I've been saying, we do a thing and it gets better. And then you may say, okay, Joe, how am I supposed to, what does that mean? I have two answers. One is a real answer and one is a glib answer. Let's start with the glib answer. The glib answer is that the Cedar soundness proof actually works, okay? When I was doing this work, it was not at all clear that we were going to be able to finish the proof in Daphne, and we might have had to bail out. But we did manage to soldier through, and with these sort of techniques that we developed, or employing these opacities and specificities, we were able to complete the type soundness proof. So I finished a type soundness proof for the sort of an initial version of the type system for this language. Here, over here on the right, you can see the current publicly available on GitHub top level type soundness theorem for the language. This is hundreds and hundreds of lines of code, but it all follows this structure. I was not the one that did the rest of this work. Other people did the rest of the work. The second answer, the real answer, is how much better, sort of quantitatively, is the proof stability of this. So we played the same game. So of measuring verification stability by way of resource usage. So here I ran some experiments on the toy language that I developed for the purposes of this talk. These aren't graphs about Cedar itself, but I wrote 5 different versions of the type checker and 5 different versions of the proof, 5 different versions of the proof, and then measured the resource usage over 500 verifications of the VCs generated by the soundness proof. So the 3 that are relevant for the stuff I talked about in this talk are basic, which is sort of the direct style version, opaque safe, which is the version of the proof that has the safety property opaque, and opaque safe invert, which is the version of the proof that has the safety property opaque, the type checker opaque, and the type checker opaque. Okay? So the different soundness theorems are on the x-axis. The y-axis is the mean resource usage in factors of 10 to the 6th. So that's 10,000 or 100,000 or something like that. Relative scale is what matters here. You can see that the basic theorems have the basic theorem has significantly higher mean, but also more importantly the standard deviation, the variance of how many resources the solver takes are significantly fewer for the opaque versions. I didn't actually know about this coefficient of variation thing until 20 minutes ago during the last talk, but I computed them, and we can see, in fact, that the opaque safe one is less than 0.2, and the direct proof is bigger than 0.2. So that's good. Oh, sorry. I apologize. The S and the M, those. I apologize. Those M's stand for millions. Yes. And that should not say S. At one point, a version of this talk had times, and now it's resource usages, and the pre-post suffixes got mixed up. So let me end the talk there, and then I'll take your questions. Thanks. Am I on time? What was that time-wise?
Thank you. That was a very interesting talk. So this talk and the last talk has really implied that you're both fighting Daphne to get things to work. Now, instead of, and so the question is, what would you like to see change in Daphne to make your life easier?
Great question. So I have two answers to this. One is an answer that I would have given you 2 years ago when I was working on this. I would have said, please just let me do this in Cocker Lean. Now I will tell you that this the proof that I showed on the second to last slide is actually out of date, and it's all been redone in Lean. My contention about this kind of proof is that for this sort of thing, mechanized meta theory, you probably shouldn't do this in Daphne because they're fairly manual proofs anyways that follow this regular structure that Daphne struggles to infer sort of directly. But I do think that the overall structure of if I could comment on the last talk, which was great by the way, I do think that like specifying and making opaque the definitions that you have in your development is like a very cut and dry, straightforward way to improve the stability, right? It worked like a charm, and I think that personally the trade-off of losing some of the automation to gain stability is very much well worth it because you sort of know what the proof should be to some extent when you're doing it, at least in my case.
Thank you. So I guess this is also a question for this talk and the previous talk. Mm. You both use the metric of the resource count of Z3 or the runtime, and this is something that's very empirical and not that meaningful for the user. I'm wondering if there is some metric that can be more meaningful for the user to say, these are the guidelines you should follow, like how many definitions the VC includes, how many quantifiers are needed for the proof, something like that, where you could say, my guideline is you shouldn't pass this threshold, and this threshold is somehow meaningful to you. I guess this is related to works on decidable fragments and EPR, where we sort of have a different version of that in terms of a quantifier alternation graph. But I'm wondering if there is something like that. And of course, ideally, you would want to have something where you can have a guarantee that if you meet this threshold, then Z3 is stable. You won't have to worry.
So I think that the most relevant user-facing metric for stability is, does the proof have varying verification outcomes, right? The real and downstream thing that you want to prevent is one day the proof checking and one day the proof failing, right? And this these variants, sort of the coefficient of variation, does seem to sort of empirically correlate with downstream variance in actual verification outcome. So I really do think that this is actually a pretty good proxy. And it's also sort of directly measurable by, you can report this to the user for sure. The fact that it's opaque and not sort of directly related to any particular syntactic metric is frustrating, that you can't sort of like, you have too many for alls, go fix your for alls. You have too many ors, go fix your ors. That's a little annoying, but I like the fact that it's at least quantitatively measurable and correlated to something that is really quite bad.
Suppose that you had a different starting point. Suppose that there was a change in Daphne when you started, and all functions were opaque. then you would have been forced to have done something like this to begin with. Wouldn't that have satisfied things? Would you have fleed the automation goodness for some older proof assistant for that?
That's a great question. I think that's a really, really good question. I think probably not. Although there's certainly, that's a really good question. I struggle to speculate about my mental state from 2 years ago, but I do think that there's a good chance that I would have taken the time to think about exactly what the proof needs to look like instead of sort of forging ahead. I think that there's a sort of confidence that comes with the great automation, like the amazing automation that Daphne has, where you just like, you get one small win with like, we built this incrementally. You started with a small version of the language and it all just worked. You just call the IH and everything just checks. And then you start building it out to extend it to the rest of the language and it slowly starts to degrade. And then you have to make a decision. So I think the thing that was the issue was that it was too good at the beginning. And if we had had the ability to make this different decision earlier, that would have been good too. Thanks, everybody.
Okay, so this is John Wood with Clément Pitclaudet. So now let's say you want to do a project in Daphne, and in particular you want to verify a small compiler in Daphne. So you would typically start by writing a simple version of the source AST, and then write some predicates, and then start doing some proofs. And at the beginning of a project, everything is very simple, and so you can really benefit from Daphne's high level of automation. So everything goes smoothly and very quickly. And then you start iterating, so you complexify your definitions, you make some updates, and you start updating the proofs. And while you iterate, the proofs tend to become more and more complex and unstable and take more time. And also they have some random breakages. Now, a big issue is when the proof becomes unstable, it's very hard to understand why it becomes unstable. And when a proof breaks, you don't have much information, you don't have much debugging information, and in particular, you don't have a context to look at so that you can understand what is going on and fix it. And one big issue with that is that while you progress on your project, you tend to spend more and more efforts into going further until you hit this wall behind which you can't really make any progress. So this is a very painful situation. And one question I'm going to tackle is, can we have a trade-off by which you invest a bit more time in setting up the project and structuring it correctly so that you have better iterations later and you can scale up more? And like in the previous talk, I'm going to focus on inductive proofs. So let's look at a very small concrete example. You want to do proofs about lists. So you have this list data type and the obvious append function. And now you want to prove an associativity lemma about append. Now, at this stage, you can really leverage Daphne's high level of automation. And actually, by just asking Daphne to use the induction tactic, you get the proof which goes through automatically. And it's true for many other such proofs. But now you want to iterate. So, for instance, you add a snark case into your list, for instance. And now the proof fails. So you need to debug it and fix it. So you dive in, and in order to dive in, you explicit the inductive structure of the proof by doing a match on the first list, listing all the cases, and then you look at the cases one by one. So you start with the nil case, it goes through, this is great. Then you look at the cons case, and now it fails. Now, at this point, I actually already start scratching my head to try to understand what's going on by closely looking at the goal. And in more complex examples, I would actually grab a piece of paper and a pencil and start writing things down. So in the present situation, you're in the cons case, so if you substitute L0 with the cons of HT in the goal, you get this, and then there are some things which simplify out until you get there. And here you see you have those two terms which you need to prove are equal, and you can get this by introducing the proper recursive call, and things go through. And now, at this point, you can finally look at the SNOC case, which is the problematic one. Now, just before going further, I want to call your attention to the fact that if you look at the nil and the cons case, the structure of the proof closely follows and actually duplicates the structure of append. We'll go back to that later. So now, let's say you anticipated a bit, and you knew you would have to make updates, and the proofs would break eventually. So in order to make the iterations easier, from the very beginning, you detail the structure of the proof. And you will likely do it this way, by doing the interesting cases, the cons case here, and leaving the other cases to be automatically proven by Daphne by having this case underscore, right? So now you add the SNOC case. What happens? Well, Daphne will tell you, I can't prove the underscore case, but you don't know which case it is about. Now, of course, in this situation, I just added the SNOC variant, so I know it must be about SNOC. But in other situations, there may just have been a proof instability, which certainly broke, and you don't know which variant it is about, okay? So now, let's say you were a bit more conservative, and you actually listed all the cases, like nil. Well, actually, what is likely to happen is you will forget to add the SNOC case in this proof. And if you don't do so, Daphne will consider you omitted it because you consider it is unreachable, and you try to prove that it is unreachable. And it can lead to inscrutable error messages, especially, for example, if it times out. So now let's contrast that with what you would do in an interactive theorem prover, say Coq. So it's very easy to port those definitions for list and app, and this is a way of doing the associativity proof. Now, something important is you're actually not expliciting the inductive structure of the proof. You would use the induction tactic to apply an induction principle, right, on the first list. And then it would give you two goals, one for the nil case and one for the cons case. And in particular, in the cons case, you would automatically get the proper induction hypothesis, which is actually all you need to finish the proof, right? So this is something pretty good. And also, actually, you would more likely write it this way. You would try to discharge as many subcases as possible and focus on the interesting cases like cons. So this is a bit equivalent to having this case underscore on the left. So now once you add the SNOC case, what would happen is, of course, the proof would break, but it would tell you there is an unsolved goal here for the SNOC case, and you can have a look at and directly dive in and solve it. So we want to kind of take this good thing on the right and port it to the left. And more precisely, there is something which works very well in interactive theorem provers, which is the use of induction principles. So we want to use that and the benefits which come with it and port it to Daphne and combine it with Daphne's high level of automation. So there is actually a way of encoding induction principles in Daphne, and we can do so by using abstract modules. So the trick was as follows. You define this list induction module in which you declare a predicate P, which is the property you want to prove. And then you declare some lemmas for all the cases in the induction, so induct nil, induct cons, etc. And given those lemmas, it is possible to prove once and for all that P stands for the list, right? So you do this lemma once and for all. Now, when you want to use this induction principle, all you have to do is define a module which refines list induction and then fill in the holes. So you would define the predicate P, and of course you would have to do the proofs. And in the present situation, the proofs go through automatically. The reason being that all you need is the inductive structure to be set up, and then Daphne's automation can take care of the rest. And this is actually the reason why, on the previous slide, in the initial version of the proof, the induction tactic would work, right? So now you iterate. So you add the SNOC case. So of course you need to update the induction principle to add an induct SNOC lemma, and you need to update the induct proof. But then for all the proofs which actually use the induction principle, what would happen is if the induct SNOC lemma doesn't go through automatically, Daphne would tell you, I can't prove induct SNOC. And so you immediately jump in, dive into the interesting part of the proof, and start fixing things out without having to really debug what's going on, or at least you have less work to do. Now, this works on a very trivial example, which is this list example, but it actually works on more interesting examples. So, for example, this was inspired by a work in progress verified compiler for Daphne, which is around 10,000 lines of code and proofs, and is publicly available. And the issue we had when working on this compiler is that the semantics in Daphne are defined by using with an interpreter function, so this interp statement function, which is around 1,000 lines of code. Now, a problem was whenever we had to make a proof, for example, whenever we wanted to check to verify the correctness of a macropass, we had to prove something about this interp statement function. And as a result, we had to duplicate the structure of this function. So basically, you need from the very beginning to have 1,000 lines of code for all your proofs, which is a lot of clutter. So this is what motivated the introduction of this induction principle. And of course, we also had all the other proof instabilities. So let's illustrate how it works on a simplified version of the Daphne language. We'll call that mini Daphne. So you have this interp statement function, which takes as input a statement and a context, which is just a map from variables to values, and it returns the value the statement evaluates to. So we mix statements and expressions here, and we say for illustration purposes that all values are integers, and it returns a new context. In the case of sequences, we just change the execution of the elements in the sequence. Now, the question is, how can we encode an induction principle for that? And for this, a good way of understanding what is going on is to go back to Coq. If you wanted to encode the semantics of the language in an interactive theorem prover, you'd write it as an inductive relation. And after you've defined this relation, you would get an inductive principle that you apply when you want to do your proofs. So this is what we're going to encode. We're going to encode the inductive principle resulting from the encoding relation we want. So it's slightly more complex than we list, but it's not that difficult. And in particular, we need a few more auxiliary predicates. For example, we need not only the predicate P, which is what we want to prove, but also a P-step predicate, which allows us to mention intermediate steps of execution. And in the case of sequences, this gives the following. Okay, so the lemma for sequence, in the lemma for sequence, we mention the intermediate step, which results from evaluating the first element in the sequence. Now, for this mini Daphne language, we applied this induction principle on several proofs. Like, for example, we defined a predicate is pure, and we proved that if a statement satisfies is pure, then evaluating this statement leaves the context unchanged. Something interesting is that the proof of is pure is quite simple. All you need to do is, once again, to set up the inductive structure of the proof. And then, once we've done that, Daphne's high level of automation takes care of everything. So here we just had to instantiate the inductive principle, and then we got the proof for free. We also verified a small pass which eliminates multiplication by zero, so expressions of the shape 0 times some expression, provided that the expression we eliminate is pure. Otherwise, you can't not evaluate it. And the good thing is, if you don't have an induction principle and you want to do this proof, you have to set up the structure of the proof. So you have a lot of work and a lot of clutter just to set up the proof, and before you can actually focus on the interesting elements. Now, when you use this inductive principle, all the boring parts of the proof go through automatically, which allows you to focus on the interesting part, which is the multiplication case, right? And finally, we also verified a small property about a variant change predicate, which checks whether a statement leaves a variable unchanged or not. It might seem trivial, but we actually need that to verify an inline pass in the bigger development, and it actually proved a lot harder than what we had expected. And we also checked what happens when we iterate on the AST. I will not detail that, but the important point is whenever we updated the AST to make some modifications in the language, we of course had to update the induction principle, but then whenever something broke in the proofs, we were able to we had a very specific lemma that we were able to look at so that we knew what was going on. And because those lemmas are small and simple, it's the response time is very quick, which means you can very easily iterate and understand what's going on and fix the proofs. So overall, it led to a far better experience when iterating on these kind of rules. So thanks for your attention. Yep.
Hi, thank you for the very interesting talk and work. So originally at the beginning, you gave it like a sort of initial motivation for introducing induction principles, given that Daphne treats missing cases as unreachable cases, and that renders using a match to sort of get the same experience impossible. If Daphne didn't do that, if Daphne treated missing or erred on missing cases rather, would you still have gone immediately for these induction principles? Do you think you could have been able to use just matches more often?
No, because this is actually only one of the problems. Like another problem is there is this underscore case where you don't know what's going on. And also in many situations you actually have, so it's not something you see on the list example, of course, but sometimes you just have, you listed all the cases, but for example, you have a timeout. And then you don't know what's going on.
Right.
And so it's very important to be able to split all those small cases into small LMS, for instance.
All right, thank you.
So I guess for mutual induction, I need to write a module that captures the mutual induction principle. Like if I have two data types and they're recursively.
So we didn't try it with mutual induction. I guess I don't see why it wouldn't work the same way.
Okay.
But one would need to try it. The important thing is, I think it should work. You just need to list all the cases.
And in this example where you've changed to sequences, did you have to write an induction principle for sequences as well, or are you using now Daphne's?
That's a good question. We had to, so whenever we made a co-modification, we have to update the induction principle. And in this specific case, we had to introduce lemmas which correspond to an inductive principle for sequences. So indeed, we have some sort of a mutual induction. And the good thing is, as you can see, the proofs went through automatically, because once again, putting aside the problem of setting up the inductive structure of the proof, Daphne's automation was able to take care of everything.
And one last thing, could you imagine Daphne generating these for you automatically as Coq does for its own induction principles?
So I totally imagine that in the case of data types. However, for the interp statement function, we're actually encoding an inductive relation, and this is a lot harder to automate.
Should be good.
hi everyone, I'm Eric, and I'm going to present the work that I did at Amazon this summer, which is named Portfolio Solving for Daphne, aka the fourth talk about Daphne brittleness. And so why do we use Daphne? So for the record, you've seen the talk, like the first talk about on the session, I was in the same team, so this is pretty much the same thing. We have a critical piece of code that is in Java. It's critical, it's used all the time, and so everyone is scared to change it. And because of this, nobody changed it, because any change is risky. You can potentially put down the whole AWS. And so in order to prevent that, we implemented this. We implemented a specification, and we re-implemented a critical Java code in Daphne, and we verify our Daphne code with regard to the specification. And so thanks to that, we can then recompile Daphne code into Java, and we get this added flexibility and more release and more confidence in any new release that we do. Because now our code is verified, so potentially under the assumption that we're making, supposed to be bug-free even when we make a change. But the question is, how is Daphne working? What does it mean to verify in Daphne? And so here I took like a really simple function. I'm going to go quick there, supposing that like everyone knows Daphne a bit. But basically, imperative programming at its best. But we add this annotation where we want to prove this postcondition here that y is greater than 0. And why? Because this is an absolute function, so all the return value should be greater than 0. And so what's happening here is once we have this postcondition that we want to prove, Daphne is going to transform it into what we call the verification condition, which is then going to be encoded in this like universal language that is standardized, which is called SMTlib. And it looks a bit like this. So this is an assertion. And this is a global way to send a message to the solver asking, OK, can you prove this thing under, can you basically prove this thing? And so you can send it to Z3, you can send this to 65, any solver that takes SMTlib as a format, as an input format. And the thing that is important is you can get three types of answers: valid, invalid, or timeout. And timeout is basically, it doesn't verify in the time that you allocated or under the resource that you gave. But the only thing that we care at Amazon, since we want to ship our code and bug-free, is when the input is valid. Any other result would be a failure for us, and we cannot ship this code. So meaning that like delay in a release, which is a problem. So now the thing is, what can happen wrong here? And let's try to take the example of Alice. Alice is an engineer in the team. She developed a new release with some addition and deletion of code. And now she's trying to verify it. And great. It's verifying on her laptop. Everything is great. Now time to do the pull request. She does the pull request, sends it to the CI pipeline, and tries to verify it again. And it times out. Why is that? Well, again, the same concept that the previous talk talked about. It's a brittle proof here. We have like a particular proof goal that may fail to relate it to seemingly unrelated change. And what are these change here? What is the change? Well, the difference is the proof was verified first on the laptop and second on the CI server. And this is a change of machine. But this is not the only thing that can trigger a brittle proof. So here we talk about the machine, but this is not the only thing. George talked about like some code changes. You change some part of the proof, and you will change the way it's encoded at the end, and then your proof may fail. You might have like some Daphne updates. You update Daphne, and your code that was proving and is exactly the same in terms of code might change because Daphne changed the way it's desugared, for example. There may be change in the encoding. Now the order of your queries is different, and the solver takes different path in the heuristics. And there can be a last type of changes is like what happens if the solver is updated. They made some improvement to the solver, and now the solver is faster on certain type of queries, but slower on others, and now it times out on the previous proof that was like verifying well. And because of this, the huge problem that we have is a proof that is valid, inherently valid, now times out. So how can we solve that? So you saw before a lot of talk about like better proof engineering. I'm not going to talk about that. I think we talk enough about it. the encoding can be improved potentially to like remove certain quantifiers, have like queries that are easier for the solvers. And the last thing is also we can have better solver or use multiple solvers. And this is an area of improvement that could be really helpful to like how do we deal with quantifiers in a better way in the solver world. And so that's what I focused on. Like first, what's the state of the art when we use different solver? How are some solver better than others are like solving the queries that we have in our code? And so what we have right now when you use Daphne is Daphne is shipped with like a version of a solver. Currently it's like Z3 4.12.1. And you have one unique solver and it gives you an answer. What we decided to do is instead of having one solver, you can have 2 or 3 or X solver. And even then, what we decided, since we're a cloud company, is this solver will be hosted in the cloud, which means now you have like basically something that is machine agnostic. You are basically verifying, everyone is verifying on the same machine because it's on the cloud in the server that is like always the same. And so you have something that is scalable, where like you can parallelize basically solving your different VCs all in parallel. You have something that is like in a standardized environment, but now you require a network. You cannot not anymore like verify only on your laptop. You need to have some access to the cloud. And so this is a solution. Now, what are the results that we get? How do we get the results, sorry? And so to aggregate the results from multiple solver, you can have different heuristics. The first one is compete. Basically, the first solver to return a valid or invalid result, you listen to the solver and you decide it's good. And this is useful for performance, and this is something that we use on a day-to-day basis. The second thing is wait for all. Wait for all, as the name indicates, is you're going to wait for all the solvers, then compare the output between the different solver and see if there is any disagreement. This is mainly for experiments and also to test soundness. So if you have like some differences, a valid solver that returns valid and another one invalid, you know there's a problem somewhere. And finally, which is something that we started to work on but didn't finish, is a sort of hybrid mode where you would wait for k in n solver. And this is a way basically to still have some confidence by like having the answer from multiple solver at once, but while avoiding the worst solver. So like some solver might time out or might not be able to answer this query, but still you're waiting for at least like, let's say 2 solvers. So now that we know how to get the result, what kind of result do we get and what did we look at? We did 2 kinds of experiments. The first kind of experiment is, can portfolio solving help reduce brittleness? And for this, we only focus on Z3. And why only on Z3? Because Daphne has been developed with Z3 and is really Z3 specific in the way it encodes the queries. The second thing that we looked at, and since Daphne is Z3 specific, how much effort would require the adoption of other solvers such as CVC5 or like Turing provers such as Vampire? And for this, we use the same experiment setup that George talked about before, which is like you have 17,000 lines of code in 64 files with like 14,000 VCs that are like around 9 gigabytes. So huge in terms of like proving. And so let's look at the solvers. And so intuitively, what we would think is like the most recent version of the solver is better than the oldest one, right? Well, not really. Let's look at this graph. And so the way you read this graph is on the x-axis, you have like different queries. And on the y-axis, you have what we call the time difference, so how much faster it is. And so what you need to understand is when it's positive, 4.8.5 is faster. And when it's negative, 4.12.1 is faster. So what we see is the older version is way faster in general than the newest version. And another thing that we can look at is way faster? No. It's only by like 10 milliseconds, which is quite negligible because like when you have like a proof that is brittle, it's not 10 milliseconds that is brittle. It's like minutes. That's what we're talking about. So you could have a reasonable question is like, why do we care about using the latest version of Z3 if the oldest one is better? Well, I would put this table as a counter argument. Here we can see something that like where we compare the 3 different versions of Z3. And what we see is a confirmation first of the result that we saw in the slide before. The number of like faster wins, which means like when the solver is faster than any of the 3 other solver that is. So here we can see that like in 86% of the case, the oldest version of Z3 is faster. It is indeed faster. So, but the thing that we see on the other column is the number of timeouts are unknown. And what we see is 4.12.1 is the only solver able to solve all of our proofs. Which means that, like, if you remember, a goal is to be able to verify everything, so to have like everything be valid. If we have one timeout, we cannot ship a code. One is enough. And so which means that here we have to use 4.12.1 at least for the 7 queries that cannot be solved by 4.11 or like the 13 by 4.12. So now we could think of like having a sort of mixed solution using both 4.12 and 4.8 because they're both faster, and why not 4.11? We can throw a third solver at it. And what kind of result do we get? And so if we aggregate, if we compare 4.12.1, the most recent version of Z3, with a portfolio that contains like 3 different versions of Z3, what kind of result do we get? First, on the solving time. Well, this portfolio is like, in general, 25% faster. So meaning using the portfolio, you get the performance of 4.8.5 mostly, and you get like a 25% improvement versus one solver. The second thing is we have this cutoff where we consider that like a VC that takes more than 20 seconds is starting to be considered hard. This is something quite arbitrary, but like by experiment, we decided that like it seems it had high chance to be unstable, basically above 20 seconds. And what we see is when we use a portfolio, it decreases from 3 to 9. And so the number of like quote unquote unstable queries is lower. And finally, when we update to Dafny 4.2, and we had only one solver, which was Z3 4.12.1, our whole like repository timed out and couldn't verify. And the thing is, if we had used at the time the portfolio, it would have verified because these queries were failing for the latest version of Z3, but not for all of them. So while this is not something that is durable, like we cannot rely only on 4.8.5, this is past code and it doesn't verify for everything, we can still use some of the advantages that were there. And so what we see, yeah, we can identify the hard proof and it can simplify version adoption. And I think this is at the core of like reducing brittleness because when we have this, we reduce the proof that are like, inertially hard, and we also avoid like this proof that are timing out for unrelated reason. Now, the last point I want to make is about like adoption of oversolvers. And so we look at CVC5 Vampire. It's hard to consider Vampire as really a solver. It's a weird beast, but still, let's look at it. The first thing that we want to look at is how much queries can be processed by these solvers, like just like how much can it try to solve. And the first thing that we see is the parse error. Indeed, like there's some queries that cannot even be parsed by these solvers. And the CVC5 problem is like sort of a minor problem where there's a difference between Z3 that has like BV2int API versus BV2NAT in CVC5. They have quite some small differences, but this is something that can be overcome with some engineering. For Vampire, I think it's quite more fundamental, where like the bit vector theory is not something that is implemented, and it will require way more effort from the Vampire developers. But at the end of the day, this is something that's quite doable. This is some NCEP-TLib compatibility, and this is, after all, like some engineering. The second thing that we look at are the timeouts. And the timeouts, what's interesting is like there are 213 timeouts with this version of CVC5. And we contacted the developer of CVC5 that were still working on like newest version, and they were like, yeah, well, now we have better quantifier instantiation in CVC5, and 22 of these queries were able to be solved. And what we concluded is like, we hope that like in the future, CVC5 will be as good as Z3 on certain point, and that for now, at least this query, the timeout, are a good benchmark for the solvers. And finally, again, we have the faster, like when the solver is the fastest, and like the improvement in terms of time. And so what we see is CVC5, for example, is faster 5.9% of the time. But if we look at the time improvement that these 5.9 queries represent, it's 12.1%. So meaning that like the amount that like of improvement that we get from like this low amount of wins is quite significant. So meaning that like when CVC5 is better than Z3, it's better on the query that matters. It's better by a good margin that improve the time significantly. And even more for Vampire. Vampire is better on 0.3 queries, percent of the queries, but the time improvement is 7.2%, which is quite significant compared to the number of wins. And so finally, I would like to conclude by saying that like we had a problem that everyone has here. It's like this brittle proof. They go from valid to timeout. It's a problem for the productivity, and it prevents us from releasing a code. What we decided to do is having multiple solvers and putting these solvers in the cloud so we have a standardized environment. And finally, the result we get is we have a portfolio solver, and now to verify it's 25% faster. It is indeed more stable, and we have better integration of other solvers such as CVC5 or verifier. And that's it. I'm happy to take any questions. Yes.
So can we get it? Oh, just speaking the...
Not the, I think the implementation of the portfolio is closed source for now, at least at Amazon.
Yeah, thank you for your talk. So you mentioned here that in your portfolio, you gave examples where you tried different versions of Z3 and CVC5. Of course, anybody who uses SMT solvers knows that they have 1 million different options that you can play around with. Have you also explored, different configurations of Z3 in your portfolios and things like that?
We did try a different version of Z3, but in general, the thing that we looked at is, there's previous work in the team where like they looked for the optimized parameter for code. And so we stayed with these optimized options in general.
Yeah.
So because even if you would be better for like one VC, you would lose so much on the rest that like it would be a problem. But you could imagine a portfolio where you have different Z3 of the same version with different options.
Yeah.
But you have to always to make a trade-off. Is it like worth it to spend this amount of resources with like different options in order to get faster or more stable?
Okay. Thank you.
So if you have a particular budget, like a dollar budget, how would you decide between just splitting into smaller VCs versus trying two different versions of some solvers for the same VC? Did you think about this? Or you have infinite money and you don't care?
No. To be fair, when I was to be completely honest, when I was doing it as an intern, I was actually heavily using compute, and I didn't care. But at the same time, I think the main problem is like, if you really don't care too much, at some point you're going to be in a case where no solver at all will be able to solve what you need. And that's where we need to like split the proof in different VCs. So I think there's a trade-off there. And I also think, like, to be honest, like 4.12.1 has some regression from 4.845, and I hope that like the newest version, and I know the newest version of Z3 won't have all of these problems. Yeah.
All right, let's move on to All right, great. Thanks for the introduction. My name is Pranav. I'm a PhD student at the University of Michigan. And today I'm going to talk yet another talk about automation at scale. And I'm going to talk a little bit more about how modules might offer a potential lens for us to be able to better understand and manage automation when it runs awry. This is joint work with John, Oded, and Andrea at VMware Research. So this trade-off has been talked about a lot already, but I'll talk about it again. But quick caveat before I begin, the work that I'm going to be presenting was done using Virus, which is a Daphne-inspired language built on Rust. But it follows the same using of SMT for verification. So both languages face this trade-off that we've been talking about a lot today, right? We want to have maximizing automation. We want to push towards writing as little proof as possible. But at the same time, as we tend to go towards that side, we might be sacrificing fast and stable verification, right? And ultimately, this is predicated on the size of the quantifier search space. The more quantifiers you end up having in your search space,
the more you might be able to find for free, but the chance of running into some kind of unhelpful instantiation and falling into some kind of rabbit hole search might end up ending up costing us verification. And we might move towards the other side with a smaller search space, but this is when you might need to manually intervene with some kind of assert that wasn't able to be found automatically. And there's been some talk about different philosophies as to how to manage this trade-off. So one talk, the Daphne 64 talk was an example of this, and there's this recent Daphne blog post as well that kind of says maybe we should aim more towards the fast and stable side by breaking down our steps and having a little bit more physically written down. And I'm here to maybe present a slightly alternate philosophy to this idea, which is maybe we should be pushing towards as much automation as possible, but we need good tools to be able to diagnose when automation is hurting our performance, so we can just kind of rein it in at those points as opposed to maybe forgoing it overall. So before I talk about what tools currently exist, I'm just going to do a quick recap or introduction to what quantifier instantiation is. So say here, in this case, we have a verification condition of pong of 4, and we start with this initial fact of ping of 1. This, with our 2 instantiations that are available in our program, will trigger the ping pong lemma in this case to be able to learn some new ground term of pong of 2, which in turn will let us learn ping of 3, which in turn will let us learn pong of 4, which is our verification condition. And what the quantifier instantiation graph is really capturing is this causality of this search, right? This is a relatively straightforward example. There's not much of a graph here, but in general, this search process is a much more complicated DAG that captures what instantiations are happening and what is causing those instantiations to happen. And so the current tools that kind of work with this quantifier instantiation are pretty good at what we call local fixes, right? So the Axiom profiler has a way to visualize this full quantifier instantiation graph. And it's even pretty good at identifying what we call trigger loops, like the one I showed on the last slide, where ping and pong can potentially go on forever and fall into some rabbit hole of search. Another example is this cost metric, which is a way for you to aggregate across this quantifier instantiation graph and get a ranking of which instantiations are particularly nasty or causing a lot of cascading instantiations. And then we used our usual techniques of fuel and opaque to try and patch these points up. Right? So the current workflow looks something like this. We have some search space that's available to us based on our current definitions. Maybe we add some more definitions, but we added some problematic quantifier that's slowing everything down. We use our tools to be able to identify, okay, this is the one that was causing that, and then we patch that. But at a certain point, maybe the search space itself becomes an issue, right? Once you get to larger and larger scales, you can't just continually introduce new facts into your context without running into search space. And the way we go about managing complexity in standard software engineering practice is to start encapsulating, right? We use logical separation of concerns to be able to split this idea. But the way that modules interact with automation is probably slightly more nuanced than that, right? In that we have a notion of automation leaking through module boundaries. And this can be a good thing, right? So here's a quick example. We have 2 modules where the data type of the larger one builds on the smaller one. And say we expose some interface in like a standard software engineering paradigm. We expose some lemma and 2 predicates. And even if module B is only ever using predicate 1 and predicate 2 in an uninterpreted way, in this case we don't necessarily care about their definitions, the latent automation of this for all is still available in the search space of predicate module B. And I would argue that that's probably a good thing, at least in like smaller cases, right? But when we start to run into issues is maybe when we're okay paying this cost at a local scale, but when we start building on top of this, we don't want to necessarily continually pay the cost of lower automation. We might want to be able to put up, we don't want to end up paying this cost. And one way we might handle this is to kind of put up a clean interface at module B that kind of prevents us to be able to leak through. So the question that we try to investigate a little bit further here is that, okay, we have this idea of where we have the tooling to be able to put up these kind of module boundaries, but we don't understand where to put them up in a larger code base. We don't have good tools to be able to identify when this automation is leaking in a way we don't understand. So can we use a module-based lens to better understand how automation is scaling on larger code bases? Okay, so that was the motivation. So the rest of this talk is going to be a case study on a relatively large Virus code base for a key value store. It's on the order of around 20,000 lines of code and proof altogether. And it has a pretty rich module hierarchy. So that's why we thought this would be a good candidate to try and identify, can we pick out the problematic modules in some kind of meaningful way? Okay, so let's talk a little bit about what kind of transformations we did on this base idea of this quantifier instantiation graph that we started with, right? So when we directly just tried to use the quantifier instantiation graph, our proofs had on the order of like 100,000 instantiations, so directly visualizing it proved to be quite untenable. So the first thing we wanted to do was try and improve the visualization of this, this graph in a way that preserves the module information, but is slightly coarser, and we care more so about what modules are causing instantiations in others. So if we go ahead and label all of the instantiations with which modules they belong to, so each shape you can think of as a different module. The first insight is if we're talking about modules at a sibling relation in the graph, and they belong to the same module, if we only care about module granularity, we can go ahead and merge those, right? And we can do the same, I have another example down here. We can go ahead and merge that as well. And now I've introduced some numbers as well, which I'll explain right now. So this 4, all it's basically capturing is how many instantiations lie below this point in the original graph. So the original graph had 4 instantiations that fall below. And this is not dissimilar to what the cost metric is doing. This is just doing it at a slightly more modular granularity, if you will. Okay, so now that we have this idea of like a module granularity quantifier instantiation graph, the next question we can kind of ask is, okay, if we cut off the automation at a particular module boundary, what would that look like in this proof tree? So for example, if I were to cut off the search at the blue square module, then we effectively eliminate 10 instantiations in this toy example, right? So we can come up with this metric of how much of the proof am I cutting off by putting up a boundary at this particular module. And we can do the same thing for each of the 2 examples here. And we'll get like a total histogram of all the modules. And it's worth noting here that this is not a partition of the instantiations. We're not exactly characterizing what caused a particular module or what caused a particular instantiation. It's more so a way to get a ranking of which modules might be good candidates to put up boundaries at. Okay, so let's talk a little bit about running this on our code base. So this is an example of the result we saw for a particular proof inside our inside the code base. And this was a refinement proof in the filter about a filtered BE tree. And so there's some candidates here that you would expect, right? You would expect the module itself that has this proof to show up with particularly high blame. And because it's pretty tightly coupled with the underlying data structure, you'd expect those 2 types to appear pretty high. And the other thing you might expect to see here is modules that represent the standard library, right? This is part of the latent automation of tools like Daphne and Varus. So those are not particularly worth considering a little bit more. The module we decided to investigate a little bit further was this one that we couldn't quite explain. It was a buffer seek module that appeared slightly lower in the hierarchy, and it was causing this ballooning effect, and we didn't really quite understand why. And moreover, when we compared it just to raw instantiations, it actually appears quite low. So it seemed like a good candidate to try and investigate where is this automation running away within this particular module. And the strategy, as many people have talked about before, is that opacify and specify, as we've seen before, right? So we were able to identify which quantifier inside this module was being particularly problematic, which happened to be a predicate definition. And the strategy for doing that was very similar to being able to merge across a specific quantifier as opposed to a module. So not dissimilar to the cost metric once we distilled it down to where the automation was going wrong. And then, yep, we make the definition opaque. And then we took a look at this intermediate stage when the proof is broken. What did the search space look like here? And the instantiations actually cut down to only 33,000. I realized I forgot to point out the number before. In case you forgot, it was around 100,000 instantiations. So like this kind of suggests that just by cutting off this one definition, we were able to, I guess it suggests that this definition is causing a large ballooning of search to happen underneath it, even though maybe there's some Z3 mysticism going on there that we don't fully understand. But somewhere within that triangle of proof that we saw underneath, we we had some fact that we cared about that we needed to figure out what it was and expose. And this is the new interface we want to present for the buffer-seek module, right? So we were able to isolate, okay, this is the reason why that proof was going through before. And we were able to expose it as its own independent lemma. So this is the same strategy that we've seen like presented multiple times today already. And after we did this refactor around this opaque definition, we were able to, well, yeah, let's take a look at the results, I guess. So the big win here is that we have a large reduction in the total instantiations that have in this roof. And this translated over to a runtime reduction as well. I think it's like on the order of like 2x. I don't remember the exact numbers. But what's still not quite clear to us, and still warrants further investigation, is why buffer-seek is still appearing particularly high. So maybe this is a tool that you might use when you have something problematic, and now that this is running in some acceptable threshold, we don't necessarily need to. But it's clear that this tool is not telling the full story as of right now. There might need, we need further investigation to be able to maybe decipher between what's happening at the module boundary, and maybe the new lemma is, so let me back up one sec. Most of the instantiations that were falling out from the tree after we did this transformation were due to the precondition of that lemma we introduced. So there's perhaps some distinction we can have between what we expose as the boundary, and maybe you can quantify this as not necessarily part of that module's count. So maybe there's further work to be done refining this metric. But that leads to some questions, which is there actually such a metric that can unambiguously identify the difference between like a leaky module and when this automation is failing us? And then popping back one level even above that is, we started with this assumption that leaky modules would be a good way to curtail automation, but perhaps that's not even really what's going on here. Maybe there's a different way you can, different lens you can use to try and view this, this problem that can point out other things. And then one more pop-up, I started with like this philosophical claim that maybe we should be pushing more towards automation and having tools go about it. But I think there's a lot of discussion to be had here, as I personally think that the automation is a good thing, and if we have like the tools to be able to pick out when it's failing us, then we can leverage that automation a lot better. That's all I really had. Thanks for your time. Yeah, and questions, yeah.
Yeah, maybe it's probably me, but I didn't quite understand the tree you showed with the different modules. Mm-hmm. Some modules occurred multiple times.
Yeah.
So I wasn't really sure. Is that like different usages of different members in the same module, or?
So even instantiations can, or sorry, even quantifiers can appear multiple times in that instantiation graph. So each node represents a specific instantiation. So even within like a standard quantifier instantiation graph, you might invoke like the ping pong lemma like 3 different times. So that will appear like 3 different nodes.
Yeah,
but
makes
yes,
sense.
This is also aggregating across multiple. If there were multiple quantifiers inside the same module, we'd also aggregate across those.
All right, thanks.
Very great talk. You said, if I understood right, that the preconditions were also creating like their own instantiations. Mm-hmm. Have you tried like making the precondition in an opaque predicate, for instance?
Oh, that's a good idea. I haven't tried that, but okay. That's definitely a good thing to try. Yeah.
Okay.
I guess that's all. Thank you very much.
you started to.
Do I speak into the microphone? Or
yes, you should speak into this microphone, but I'll do it and I'll push it over. So. Okay, welcome back for another afternoon session. Our first talk is going to be by Fabian Zeitzer, who's going to tell us about a library for verified Monte Carlo in Daphne.
Yeah, thanks, Joe. So yeah, I'm a PhD student at Oxford, but in the fall I completed an internship at AWS where I worked with Stefan Zetsche and John Tristan on VMC, which is a Daphne library for verified Monte Carlo algorithms. So, since not all of you might be familiar with Monte Carlo algorithms and probabilistic sampling, quick reminder. So, probabilistic sampling means generating random samples from a desired probability distribution. This is important in various areas in computer science, such as cryptography and differential privacy. And it's hard to do correctly. And I'll give you two examples for this. The first one is the Fisher-Yates shuffle, which samples a random permutation of a list. And if you look at the Wikipedia article, it has a whole section on potential things you can do wrong and that people have done wrong in the past. Another thing is differential privacy, which also needs probabilistic samples from specific distributions. And this paper here describes an attack on differential privacy that was caused by a very subtle implementation error for a sampling algorithm that was proven correct on paper mathematically, but there was a subtle mistake in the implementation that completely destroyed differential privacy. So why is this hard to get right? Let me give you a simple example of why reasoning about probabilistic programs is difficult. So here we have a very simple sampler that returns 0 or 1. It only uses simple distributions like geometric, Bernoulli, binomial, and simple operations. So it shouldn't be too hard to figure out what the probability of returning 1 is, right? Well, it turns out it's 1 over pi. And that's a bit surprising because everything we do is like rational numbers. So where does this come from? And it turns out that what this program implicitly does is computing this infinite series, which just happens to converge to 1 over pi. And I think this illustrates why reasoning about probabilistic samplers is harder than like deterministic programs. And this is where the project Daphne VMC comes in. So VMC stands for Verified Monte Carlo. Monte Carlo algorithms are sampling algorithms are an example of Monte Carlo algorithms. So this library provides a number of samplers for various distributions, including proofs of correctness that are formalized in Daphne. And it's interoperable with Java. So you can call these samplers from Java, and the samplers will use the random number generator provided by Java. It's currently work in progress, so it's partially axiomatized. But it's already open source in GitHub, and you can check it out if you're curious. So what are the components of a sampler in Daphne VMC? There's 5 parts. The first one is a functional model, like a mathematical description of the sampling algorithm. Of course, this has to be proven correct. But in practice, we want to use an imperative implementation that actually uses an external source of randomness, such as the operating system random number generator. And to relate this with the functional model, we need a proof of correspondence between the two. Of course, assuming that the external random source is correct. And we also have statistical tests in place, because not all the samplers are fully verified yet. In this talk, I'll focus on the first 2 aspects. All right, so how would we express functions that can return random values in Daphne? Well, this seems difficult because Daphne's functions are deterministic. They give the same output every time you call them with the same inputs. So they need to take the randomness as input already. And the way we model the randomness is just with random bits, with probability 1/2 they're 0, probability 1/2 they're 1. And since we don't know how much randomness is needed, we just pass in an infinite stream of bits. Then the function can use these random bits to compute a random value, and it'll return the unused bits for future computations. So you can think of the randomized functions in Daphne as bit stream transformers. In code, this looks something like this. So this bit stream type is an infinite sequence of booleans. And if you wanted to model a fair coin, you could just take the first bit from the bit stream, return that, and as the second component of the return value, you'd return the rest of the bit stream. So the original shifted by 1. This works fine, but it's a bit error-prone to pass these bit streams around all the time. So it's nice to have an abstraction for this. And in fact, Joe Hurd introduced such an abstraction, which we call the Hurd monad. And this way, you just need to use a small set of combinators, which are coin, return, bind, and while, to express all the samplers in the library. So in code, it looks like this. The Hurd type, Hurd monad, is a function that takes a bit stream as input and returns a value and a remaining bit stream. And the primitives that I mentioned look like this. So coin is basically the same as before, except it now uses this Hurd type. The combinator return just takes a value and deterministically returns it without touching the bit stream. Bind does composition. And finally, we need some construct for looping, which is called while, which operates on a state of type A. And as long as the condition is satisfied of the state, it transforms it with the body function. All right, so this shows how to include randomness in Daphne, but how can we actually reason about the probabilities of those random values? For that, we need some probability measure. And we put those on the bit streams because the bit streams is where the randomness comes from. And the probability measure we put on the bit streams expresses the idea that all the bits are independent and uniformly distributed, so probability 1/2 of being 0 and 1. And Hurd proved that this probability measure on the bit streams makes them a probability space, which we have currently axiomatized but want to prove in the future. And in code, this looks something like this. We have this prob function, which takes a set of bit streams and returns their measure. And for convenience, we have this function probability mass, which takes a probabilistic computation, returning values of type A, and is also given a result value, and returns the probability that we get this result value from the computation. In other words, takes the probability measure of all the bit streams where the result equals the result we care about. And with this probability mass function, we can express the correctness of the coin example. So we can say that the probability mass of coin returning false is 0.5, and the probability mass of coin returning true is 0.5. Now I want to talk to you about my project during the internship, which was to implement and verify the Bernoulli exponential distribution. And I think this is a nice example because it illustrates many of the challenges we faced. So on the surface, it's quite simple. It returns true with probability exponential of minus gamma, assuming that gamma is between 0 and 1. But this is actually quite tricky because we can only use rational numbers in the computations. But the probability we get in the end is irrational. In fact, this distribution is the source of irrational probabilities for all the samplers in the library. And it's a building block for many important distributions, such as the discrete Laplace distribution and discrete Gaussian distribution, which are important in differential privacy. So in pseudocode, the sampler looks something like this. So we get the gamma parameter as input, and we return a Boolean, true or false. And we have a state with two variables. The first one's a Boolean, a, and the second one is a natural number. And as long as a is true, we increase k by 1 and resample a from a Bernoulli distribution with the parameter gamma over k. And finally, we return where the k is odd. So why would this give you this exponential probability? So just to give you a rough idea of how this works, first of all, let's look at the probability that the k we have at the end of the loop is greater than some number n. For this to be the case, we need to have had n loop iterations, and in each iteration, the probability of a being true is gamma over k. So to have at least n iterations, we get this product, gamma over 1 times gamma over 2, and so on. So overall, gamma to the n over n factorial. So the probability of having exactly n iterations is the probability of having at least n minus 1 and not more than n. So we take the difference between the two probabilities. And finally, we care about the event that k is odd. So we need to sum over all odd numbers. And if you rearrange this a bit algebraically, you see that this is just the power series for the exponential function. All right, so how do we do this in Daphne? Well, we have this function that returns random booleans. We can formulate this precondition on gamma as follows. And then we have this while loop, which operates on a state that is a pair of booleans and natural numbers. And the loop condition just says that the boolean should be true. Then what does the body do? The body increases k by 1, and then samples from the Bernoulli distribution with the gamma over k parameter, and then takes the result and combines it with the k that we computed for the next iteration. The initial state is a being true and k being 0. And in the end, we return whether k is odd. OK, so this looping construct is quite important for this distribution. So how would we express this in Daphne? Well, the first idea might be something like this. So this while function takes a condition and a body statement, a body function. And given a state, if the loop condition holds, we enter the loop, run the body transformation on the state, and then recurse, running the loop on the result again. And if the loop condition is not satisfied, we just return the initial state. So this seems natural, but if you try this in Daphne, it complains and says we cannot prove termination, because this recursion may not be bounded. And this is a problem, because many samplers require loops. So rejection sampling, for example, is a common technique, and that requires a loop. In fact, it's even more fundamental. If you look at the uniform distribution on 3 objects, you want a probability of 1/3, but you cannot get that with a bounded number of bits. Because if you have k bits, then you can only get probabilities of the form something over 2 to the k. So you can't get a third. So the samplers may not always terminate, but they always terminate almost surely. But Daphne can't reason about almost sure termination. So what do? Our idea is to track non-termination in the probability monad type. So we change our probability monad as follows. So this was the old version, which returns a pair of A and the remaining bit stream. And instead, we return a result type, which can either be diverging, if the computation doesn't stop, or it can be, again, a pair of a value and the remaining bit stream. And all the combinators we had before, we can define just fine. I won't show you the definitions. And now we can also define, and this allows us to talk about the probability of non-termination and to state that the probability of non-termination is 0. All right, with this in place, we can actually define while loops properly. And first, we define a while loop with a bounded amount of fuel, so where the number of iterations we can do is bounded. So it takes an additional argument, fuel, and we first check whether the fuel is 0. If we're out of fuel, in that case, we say it's diverging, we bail out. Otherwise, if the loop condition is violated, we stop the loop and return the initial state. And otherwise, we do the same thing as before, recursing, but now decreasing the fuel by 1. So this is just normal recursion. And Daphne can prove that it terminates. Now, how does the unbounded while loop work? The idea is that for a given initial value and a given bit stream, we check whether there is an amount of fuel for which the bounded loop terminates. If that exists, then we just take that bounded loop. And otherwise, we diverge. So this shows how to implement the while loop, but how can we actually reason about the probabilities arising from it? So how can we prove that the loop produces a result with a probability p? And the idea is, again, to reason about the bounded version first, where you can just use induction, and then take the limit as fuel tends to infinity. So for example, we use this lemma, while probability, which is currently axiomatized, but we want to prove it, which yeah, it takes the condition, loop body, initial value, the result we care about, and its probability. And we have to verify that the result violates the loop condition, because otherwise we would keep looping on it. And then we look at the sequence of the probability masses of the bounded loop as the field increases. And if that converges to P, then this lemma tells us that the probability mass of the unbounded loop for yielding the result is also P. And this required formalizing some real analysis in Daphne, for example, limits. So with this lemma, we can prove the correctness of the Bernoulli exponential distribution, where we again have to use a limit argument. So this proves that the probability mass of Bernoulli exponential returning true is the exponential of minus gamma, and analogously for the false case. And for this, we had to define the exponential function in Daphne, which is currently partially axiomatized. So yeah, in summary, Daphne VMC is a cool project, at least I think so, for samples of various distributions with proofs of correctness. You can check it out on GitHub. And in particular, I think the verification of the Bernoulli exponential distribution is interesting because there's two challenges. We had to formalize some real analysis in Daphne, for example, limits in series. And there's interesting research on probabilistic loops and non-termination to be done. Thanks for listening, and I look forward to your questions.
Thank you. Very interesting. I was wondering, you have been able to encode to make an API that has everything that, I suppose, everything that you need in order to reason about probabilistic programs. Mm-hmm. But I was wondering if Rustan were designing Daphne now, would you suggest that he designed it differently in order to be able to express what you need? Or is it fine to do it the way you did it?
There's one main limitation that we can't do yet. It again has to do with non-termination. So I showed you how to deal with non-termination for the functional model, so the mathematical description. But for the imperative side of the sampler, we can't do something similar. So there we cannot prove termination and can just prove partial correctness. So if there was a way to tell Daphne, this function doesn't, this method doesn't terminate, it only terminates almost surely, that would be nice, but then it's not clear how to exactly encode that in Daphne and how such a property in Daphne would look like. But that would be cool.
Sorry, I had to miss most of your talk, but I have a question on partial correctness. What is partial correctness of a sampler? Or of...
Yeah, so in what I just said, yeah. I meant that if you have a method that samples, like an imperative method that uses an external source of randomness, so that is not the pure mathematical functional model, then there it can happen that it doesn't terminate. If you have a loop, and you always get
the sampling method, you mean?
Yeah. So.
Okay. No, that answers my question. Yeah. Thanks.
Okay. Maybe we can thank the speaker and move on to the next.
That is not expected. Okay. Do you have maybe some another desktop and you're only sharing part of it? This is. Don't know why it's only to window. Okay. Yeah, Okay.
Yeah, thanks for the introduction. So this is also about probabilistic programs. This is about Caesar, our deductive verifier for probabilistic programs. This is based on joint work with Kevin Butz, Benjamin Kaminski, Jos Peter Cartoon, and Christoph Matea, which was published at UPSLA last year. So as a first example, let's look at another probabilistic program. This is what we call the geometric loop. It produces a geometric distribution. So as you can see, it's just one while loop, two variables, and then we have this probabilistic choice over there. And here with probability 50%, we set run to false and so terminate the loop. And with 50% probability, we increment C. And you can kind of imagine this as you flip a coin and you stop when you hit heads, and you also count how many iterations you do. So we can look at various different properties of this program. And so one very simple one is, what is the probability that we terminate in a state that satisfies C equal to 1? Okay, you can maybe run this, look at this. This is 25%. Then a bit more complex or more interesting is, what is actually the expected value of this? So this is an infinite sum here, and the infinite sum evaluates to 1. So an expectation, or the expected value at the end of this program is 1. So you can see this as, on average, we do 1 incrementation of C. Then this program can diverge. So there's one execution going always to the right-hand side branch where we do not terminate, right? But the probability of termination of this program is 1. And so we call this program almost surely terminating. This is also a property that we might want to verify. Furthermore, this program is what we call positively almost surely terminating. So the expected runtime of this program, let's say this is the number of times we evaluate the loop guard, is 2. Okay, so because the expected runtime is finite, we call this positively almost surely terminating. The probability of termination is 1. So these are two separate properties that we want to verify and need to distinguish. So in general, what we wanted to look at was various different properties. So we wanted to look at lower and upper bounds of expected values of probabilistic programs. We want to look at stuff like expected runtimes, almost sure positive, almost sure termination, maybe amortized expected runtimes, and more. So there's other properties like probabilistic sensitivity, which describes how much does an output change depending on a change in the input, relevant for differential privacy, or conditional expected values, expected resources, and so on. And then on the right-hand side here, or I guess your left, there's proof techniques that we want to use. So this is just a small number of them. Proof we'll call Park induction is kind of what you might know in the classical setting as just your standard Hall logic rule for loops. Then we have K-induction, martingale-based reasoning, and more. And our goal, of course, was how do we automate reasoning and verification about probabilistic programs, so especially verifying properties that we've seen before. And how do we make this extensible? So how can we add more properties afterwards, add more proof rules to reason about these programs? And our idea was, hey, let's build the probabilistic version of Boogie or Viper. So we built an intermediate language to encode verification problems for probabilistic programs. And so this is what Caesar is based on. So Caesar uses our quantitative intermediate verification language that we call HAVL. And we encode the program, the specification, and the proof rule into HAVL. And then we have semantics of this language that we call verification condition generator that generates an expression in a real value logic that we call Halo. And so then we encode, as I said, all of this stuff into HAVL. And in the end, we have our implementation Caesar that takes such encodings and then uses an SMT solver to try to prove correctness. And yeah, this is all integrated into our tool. So let's see how these specifications look like more closely. So in the classical setting, you might imagine you have a Hall triple with pre and post condition. Let's imagine we have total correctness. And we have a pre and post that are Boolean. So each state, that's the sigma, is mapped to true or false. And what the specification might mean is, for example, P describes a subset of the states that terminate in Q. Okay, so we can write this using weakest preconditions, really saying, okay, P is a subset of the weakest preconditions of Q. And yeah, you can see also that weakest precondition reasoning really is this backwards kind of reasoning. And what's cool about these classical IVLs, and which you probably know from Daphne, right, is that you can use assumptions and assertions. You can assume that P holds before the program, then you run your program, and then you assert that Q holds afterwards. And this is something that we want for expected value reasoning as well. So what does this look like in expected value reasoning? Well, we have a pre-expectation and a post-expectation, F and G respectively, and now each state is mapped, each state sigma is mapped to a non-negative real value or infinity. Okay, so now we reason about expected values and assign each state such a number. And what this is supposed to mean is F is a lower bound to the expected value of G on termination of G, of the program. And so we have a generalization of weakest preconditions to the probabilistic setting, which is known as weakest pre-expectations. And what's cool about our intermediate language is that we also have now these variants of assume and assert statements. So we can assume F and assert G, and now F and G might evaluate to numbers. So we can literally write assume 2, assume 5, which is something different than saying assume X is 5. Okay, so we'll see that how that works in the following. So the idea is that we look at semantics, or that we look at semantics by defining a logic to reason about expectations, so expected values. Let's just define the semantics of an assert statement as a minimum. So if we assert an expectation F and we have a post expectation G, then we just take the minimum of these two values in each state. Now, a big question for us was, how do we define the semantics of an assumption? What should an assume statement mean then? It should be some kind of implication, right? But now this implication is between expectations. So F and G can evaluate to numbers, and the result should also be something that evaluates to numbers. And we looked at a couple of properties that we wanted to have. And one is from hating algebras, which says basically that if you have an implication G implies H, and we have a lower bound F on it, then this should be the same as basically pulling down the left-hand side, saying the minimum between F and G implies H. And you can kind of read this in the Boolean setting, saying, okay, if you introduce an implication G implies H, and you have a pre-F before it, then it's the same as introducing G as a pre, so making more assumptions. The other property that we wanted to have was really being able to encode kind of exact comparisons. So this deduction theorem here says F is a lower bound to G if and only if our implication that we're defining is equivalent to infinity. So imagine infinity is something like true, and this means really we can encode comparisons with this, which is very important doing comparisons when you're doing probabilistic reasoning for our probabilistic proof rules. So the definition that we arrived at is something that I'll show you with a picture. This here is 42 implies G, right? You can see 42, this is just a number, and the implication, this Gödel implication here, named after Kurt Gödel, is supposed to mean something like assume any value G at least 42 to be true, okay? So from the definition, this means that if you plug in anything up here, then you get infinity, kind of like true. And if you plug in anything less than 42, then you get the identity function. Okay, so this actually generalizes the classical implication to the probabilistic setting, to the quantitative setting, and works pretty well for us. So, okay, so let's run an example. This is the loop body of the example that I showed you in the beginning. We now clearly assume something quantitative, right? We assert C, and C evaluates to a number, and we assume C plus 0.5. And to check whether this program now verifies in our quantitative setting, we check whether the semantics going bottom up evaluates to infinity. So we start at infinity and check whether that's infinity. Same as starting with true and trying to see if true is a result. So we assert C, and what the result of the semantics here is that we take the minimum between C and infinity, which is just C. Then we compute the expected value of this probabilistic choice, which is, in this case is fortunately very easy because there's no loops, nothing complicated happening. So this expected value is with 50% probability you get C, with 50% probability you get C plus 1. Yeah, okay, you can simplify this and then you get C plus 0.5. And as I said, the assumption now generates this implication. How is this supposed to be read? C plus 0.5 is at least C plus 0.5, so we get infinity. Okay, a very easy example. So the final result is infinity. We started with infinity, which means by our definition, the program verifies. And by the correctness of this encoding here, this really means that the expected value of C after running this program is at least C plus 0.5. So that's kind of how stuff works, how encodings work in a very basic setting here. Now, this is behavioral. This is the basics. So we've seen the assertion, we've seen the assumption as minimum and the Gödel implication, and we have a non-deterministic choice that in the quantitative setting here corresponds to an infimum. And if you look at the classical semantics, right, in the classical setting, it's a Boolean AND, okay, corresponds to minimum. Classical Boolean implication corresponds to this generalized Gödel implication, and the for all corresponds to the infimum. So behavioral really generalizes classical intermediate verification languages, and we actually have a theorem for this. And then there's a second thing that we needed, which is very natural in the probabilistic setting to think about. Why not think about, we want to think about upper bounds of expected values, not only say the expected value is at least something, but also say it is at most something. Imagine the probability of an error being at most, 50%. And so what we added was these dual statements for reasoning about upper bounds of expected values. Co-assert, co-assume, co-havoc. Co because they're really just the duals. So we now have a maximum between expectations for co-assert. For the co-assume, we have what we call a co-implication. It's just basically flipping the directions, flipping the arrows. You can see the full definitions in the relevant paper. And the co-havoc is, not surprisingly, the supremum. So this is allowing us to do upper bound reasoning in this language as well. Maybe you also see a relation to this. What you could also do, for example, is try to do incorrectness reasoning with this, because this is also upper bounds reasoning. So to show you that this idea works, we implemented this, of course, in our tool, Caesar, and we have more than 40 examples of probabilistic programs that we've verified. So we have 12 different proof rules for loops, which shows you there's not just one proof rule, not just induction. There's much more. So we have lower and upper bounds on probabilities, kind of like partial correctness. Then we have lower and upper bounds on expected values with proof rules like K-induction, omega invariance, and so on. And we also want to reason about conditional expected values, expected runtimes, as I said. And we have also two separate proof rules to show almost sure termination, or specific proof rules to show almost sure termination and positive almost sure termination, showing that you can really encode a lot of stuff into this intermediate verification language. These examples also include procedures. We have recursion in there, user-defined data structures. A lot of stuff that you would expect. So let's see how one proof rule works, namely the simplest one, the induction one, the standard loop rule. So just like in Daphne, to reason about while loops, we can use invariance. And in the classical IVL, how you would encode verification about a loop is something like this. You have a Boolean invariant, a predicate, and if you have a loop while b do as, then before the loop you assert that the invariant holds. Then you enter the loop, that's the havoc statement, and you forget kind of everything about the modified loop variables. Only you assume that the invariant holds in the beginning. Then if you enter the loop, you run the loop body once, and then you need to assert that the invariant holds at the end. And the assume false kind of means you don't run afterwards. But if the loop body does not hold, you just continue with the program. And in behavior, this looks almost exactly the same. Again, I is here an expectation, so it can evaluate to numbers, but we still have this assert, havoc, assume thing going on, with the only difference being really in the encoding that we have this additional validate statement here, which is unfortunately necessary in the probabilistic setting, but we have more explanations why this is important. So you can see definitely that we have a really nice generalization that of classical IVLs that also generalizes the encodings of classical proof rules. And of course, this is sound for probabilistic programs. So we have a website, caesarverify.org, for our tool, Caesar. It's written in Rust, it's open source. We also have a bit of language documentation and an extended version of our POPL'24 paper, where we describe all the theoretical details of Haviel and the rest. So in the language, you really can see the semantics of Haviel and Halo, this logic to reason about quantities, and some more detail on the case studies that we've encoded and verified automatically or automatically. Yeah, thank you.
Thank you very much for the excellent talk. I have a question of a more theoretical nature. I was wondering how much of the theory you've built actually realized that you're working with reals with extended infinity, and how much of it, for example, holds in quantalic setting or in some sort of residuated semilattice setting. And maybe if you take a Boolean quantile, does it become like ordinary boogie-like language?
Yeah, so we kind of, the reason why Haviel is called Haviel is because of hating algebra. So I think quantiles are kind of other structure a bit. But you can definitely instantiate just this framework with just Booleans, and then you get just the Boolean stuff that you would expect. So then it's just, yeah, I would say Boolean, Boogie's Boolean semantics. You can plug also in other stuff, like just 0-1 bounded stuff, but this is not what we focused now in this paper.
I guess it will be some sort of intuitionistic boogie then?
Yeah, you can think so, yeah.
All right, thank you very much.
But this generalization is future work, yeah.
Thanks, that's very neat. Have you thought at all how you might integrate this with, say, a non-quantitative valued logic for verifying the rest of your program, perhaps that's not randomized?
So, I mean, for Boolean logic, we can easily integrate it. I mean, it's just, you map everything, you map false to 0, you map true to infinity, and then you're done. So, kind of just Boolean reasoning works just out of the box easily. Yeah, and I think that's basically the answer. So, really just, like in theory, you can just take your normal Boogie program, and if the language features are supported, then you literally just transpile it and have, and add maybe some conversion to 0 and infinity, but that's about it.
Okay, thank you. Okay, let's thank Philip and have the next speaker get ready. Okay, our next speaker is Cassidy Waldrop, who's going to talk to us about verifying Daphne contract integrity.
You maybe just try to go outside. Okay, yeah. You don't have like an extended desktop or something.
I don't think so.
Yeah, okay, because that was the problem. Okay.
I don't know. I mean, I could try like a different port.
So it's like an issue with it. Yeah, try another port.
I don't know. I could try.
Yeah, I don't.
I could maybe log into somebody else's computer and go after the next person.
Okay. Yeah, maybe you could try about someone has a computer.
Should I go after and
Sure,
log
we
in on
could
somebody
swap
else's
you
computer?
if
Okay.
Is the next speaker here ready? Yeah, maybe we'll try. We'll
Okay.
rearrange it, please. Okay, slight change of plans. In fact, our next talk is going to be by Eli Goldweber.
Yep, you got it.
Who's going to tell us about testing specifications in Daphne.
Hopefully this goes better than the other. All right. Well, good afternoon, everyone. My name's Eli. Thanks for the introduction. I'm going to be talking today about the importance of testing specifications and specifically how we did this in Daphne by building a specification testing framework and applied it to 6 different open source specifications, finding spec bugs across each. This is joint work with my colleagues from the University of Michigan, Wei-Shin Yu, Armin Vakil, and Manos Kirpritsos. As we know, when trying to verify a system or an implementation, one starts by first capturing the system requirements in the trusted specification, and then a passing proof shows that the system is verified and maintains all the properties defined in the specification. Verification is attractive for these strong guarantees that it can provide. Tools like Daphne and recent advances in automation has only increased the adoption of verification, but these guarantees are only as good as the trusted spec. If there is a bug in the specification, then that bug could also exist in the protocol or verified implementation and could potentially be hidden by a passing proof. Current techniques to ensure that a specification is correct rely on manual inspection. The insight being that specs are typically small enough and understood well enough to make this task feasible, but even experts have been found to make mistakes. This is an example from a bug in a notional finance verified smart contract. There was a double spending vulnerability that was the result of a bug in the specification. There have also been a few academic studies that have, through mostly manual means, identified specification bugs in different various systems, though these rely mostly on the manual effort. And so in this work, we're trying to improve the reliability that we can give to one specification through the means of testing. The problem, though, of ensuring a correct specification is difficult by its very definition. Specifications are trusted, so they can never be proven correct, so any attempt to ensure a correct spec will always be best effort in some way. So it's kind of a constant battle between the intent and understanding of what you want your system to be specified and what's actually written in your current specification. So we're trying to show that there's a better way that we can increase our reliance on our specs rather than relying on manual effort, and that's through testing. And we've demonstrated this by building a Daphne-based specification testing framework that helps facilitate spec testing through automation and a manual testing methodology. When a specification is buggy, it may be buggy in different ways. It could be that it's too weak, including some additional buggy behavior that's not intended, or it could be too strong, which excludes some expected behavior. If a specification is too weak, it may include this buggy behavior, and a developer may write an implementation that also contains that same bug. They may even come to a passing proof, falsely giving the illusion that their system is correct, but it's in fact buggy. In the opposite case, if the specification is too strong, it excludes some expected behavior. So a developer writing an implementation and trying to come to a passing proof, their proof would eventually fail, and they may be left with the question of, is my proof failing because I don't have enough invariance in my proof, I'm missing something in the implementation, or in this case, because the spec is wrong. So having confidence that the specification is correct only helps to alleviate this. In the quest to test a specification to make certain that it's neither too weak nor too strong, purely relying on manual inspection is insufficient. And so we've designed IronSpec, which is a spec testing framework that combines the automation of sanity checking and mutation testing with a manual testing methodology. Before talking about IronSpec specifically, I wanted to share an example of a specification to give some insights as to why this problem can be subtle. Consider a specification for sort, which takes an input sequence of integers and returns an output sequence of integers, and the spec is a single post condition that says that the output be ordered in ascending order. At first inspection, this may appear to be a correct spec for sort, but it's in fact incorrect. This is a mistake that many newcomers may make, might make when starting to specify this. It's too weak because there's no constraint that maps the values in the input sequence to the values in the output sequence. We can illustrate this by maybe picking some arbitrary points to see whether or not it's either allowed by the spec and matches our intent for what a correct specification for sort should actually do. So we may pick some arbitrary values. In this case, our input-output pair is both allowed by the spec and matches our understanding of what a correct implementation of sort should allow. But we may quickly find a counterexample where in this case the output sequence is ordered in ascending order, but it shares none of the values that were in the original input. This is because our specification is too weak and includes this additional buggy behavior that we don't want our method to have. To fix this, we would need to add an additional post condition that says the multiset of the input is equal to the multiset of the output. This effectively strengthens our specification, removing that buggy behavior from our original spec. And then we can see that our two specific examples now match our intent for what our correct spec should allow. In the opposite case, if a developer were to accidentally drop the multiset relationship and just say that the input be equal to the output, they've unnecessarily made the specification too strong, which excludes the expected correct behavior that we would want our specification to have. So having automated and methodical ways to approach this problem can be quite helpful, especially as more and more non-experts are writing specifications and trying to prove their systems. We also leverage the notion that specification bugs, like any type of bug, occur because of a disconnect of intent. There's a disconnect between what's intended and what's actually written in the current specification. Note that specifications are often meant to be abstract, so they may include some additional behavior that the system might have, but that might be considered benign. But if there is a bug in the specification, it's due to this disconnect. And so we leveraged this notion when we designed IronSpec to help guide the testing process in trying to focus on and identifying these potential areas of disconnect, hoping to help streamline the testing process. IronSpec itself consists of 3 different testing techniques: an automatic sanity checker, a manual methodology for writing spec testing proofs. You can kind of think of adapting unit tests to the realm of specifications, and then an automated mutation testing framework. For the rest of the presentation, I'll go through each of these to give some high-level insights as to how this helps achieve testing in the different avenues that these unlock. Starting with the automatic sanity checker, which simply flags common cases of disconnect between the input and output of a verified method and its specification. So in an extreme example, if there's a complete disconnect between the input and output of a method and what's mentioned in the specification, we can provide a very strong hint that that may be an underspecification. So in this case, we have an example of a method bar that returns a value foo of type f, but there are no post conditions constraining the output whatsoever. Now, in most cases, this may not be intended, and so we can flag this with pretty high confidence to direct the developer to say this is missing. In a less straightforward case, there may be only a partial disconnect where part of the output is constrained. So in this case, the output is a data type with multiple fields, and only one of the fields is constrained. So we are still able to flag this, but with less strong of a hint. It may not necessarily be a specification bug. That's kind of up to the developer in the specific context of the system. But the hint is focusing the developer on that specific aspect that may have been missed. As another example, we can revisit our 2-week sort specification from earlier, and we can apply the same reasoning. We can map the output to what is mentioned in the single post condition, and we can see that the output is constrained, and every index in the output is constrained in some way. But we would see there's a complete disconnect because there's no constraint concerning the input whatsoever, which is actually the reason why we were able to see that counterexample from a few slides earlier. Note that these are just hints to the developer. They're not outright indicating a specification bug, and they still will require some manual effort to diagnose or exonerate, say that this is actually intended. But the tooling we actually are providing to help answer these questions takes the form of a spec testing proof. This is a manual methodology for writing tests similar to unit tests, but for specifications specifically. So they're still proofs, but rather than trying to prove the whole system correct, each proof is about a very specific, context-specific question that we wish to ask about our specification, and we can ask different questions by forming our STPs in different ways. As an actual example, we can revisit our sort example from earlier, and we might try to write a correctness STP where we're trying to show that our specification is strong enough to reject some intended invalid output. Where the notion of intent comes defined by the developer themselves, they have to act as the oracle. So like a unit test, the developer would specify context-specific values that they wish to test, in this case as preconditions. And furthermore, because we're testing the strength of the specification, this example is an example of an intended invalid output because the output drops the value that was contained in the input. The proof obligation is the negation of our sort spec, and if our specification is correct, we would hope that we would be able to prove this lemma. But if we run this with our 2-week sort specification, we would find that this lemma fails to verify. But because this is a proof, we're not certain if that's just because we have missing proof annotation in the body of this lemma, or because our specification is actually too weak and we can't actually prove this obligation. So if we become suspicious, we may choose to write a counterexample, where in this case we can structure it pretty much identically, except we're trying to prove the opposite. We ask the question of if our specification is indeed weak enough to prove this case, and with our 2-week sort spec, we would see that this would automatically verify, which is a counterexample to that 2-week spec. So far, we've touched on the automatic sanity checker and the methodology briefly for writing STPs. It's also important to note that neither of these have any dependence on the proof or the status of an implementation. So this could be leveraged or written at any point in the development cycle, akin to test-driven development. But if we have a proof, we can further apply automation in the form of mutation testing. So we are able to automatically, given a passing proof, the original specification and the implementation, mutate the original specification in some way to derive some slightly different mutated spec. Now, we can then check to see if this mutated spec still allows the proof to pass. If the mutated spec lets the proof, like if the proof still passes given this mutated specification, that serves as a pretty specific hint to the developer that, hey, we found this different spec and our proof still passed. What's going on here? And so we can provide that as a specific hint to the developer of this difference between the original specification and what is not allowed by this new mutated specification. And this is a hint to focus the testing effort on trying to understand and ask this question of whether or not that's actually intended or not. We automatically generate these mutations, but as some of you may be guessing, not all mutations we generate are relevant to consider. In this same example, if we were to, let's say, come up with a mutated specification that's weaker than our original spec, we would expect the proof to pass, but we would also not be given any new information because all of the behaviors contained in the original spec are also contained in this weaker specification. So we can safely filter these out and remove the chance of potentially alerting the developer to any false positives. In general, we start with the original specification. We then create a number of mutations, mutated specifications based on mutation operators. We then are able to automatically filter that set of mutations based on some automatic tests, like the relative logical weakness, as well as testing to make certain that the mutations are not causing the proof to go through trivially. The set of remaining mutations we then test with the full end-to-end proof, and if the full proof passes, we consider that an alive mutation and a hint to the developer for further investigation. We further classify the set of alive mutations into a DAG based on relative logical strength, presenting the tester with only the root of each component of the DAG, which serves as the strongest hint to then minimize what is actually expected for them to investigate further, hopefully by writing STPs. So just to recap, the iron spec prototype consists of 3 different testing techniques that all kind of help focus the testing procedures on trying to identify these divergences of intent, where the automatic sanity checker looks for these general kind of common cases where there's a clear disconnect between the specification and the input-output. STPs help answer context-specific questions based on the understanding of the actual tester, and mutation testing helps try to automatically find differences between the specification and the corresponding implementation. So as I mentioned before, we've built this in Daphne to be able to test Daphne specifications, and we've applied it to a corpus of in-house specifications, but we've also applied it to the specifications of 6 different open source verified systems, and we're able to find 10 different specification bugs across these 6, most of which have already been confirmed by the corresponding authors. As I mentioned before, STPs will always be the end of the story because they help answer that either proving a counterexample or proving that the behavior is correct. But we've also kept track of which aspect of IronSpec led to that initial hint, which then led to the discovery of these different specification bugs. Whether it be the hints from the automation, either the automatic sanity checker or the mutation testing, or just the 3 rows labeled STPs are the result of writing a suite of STPs like one would write a suite of unit tests. So the results help show that by applying these testing techniques that we use in imperative code to specifications, it's useful in actually increasing the reliability by identifying cases where the intent of the developer diverged from what was actually written. And with that, thank you for listening. I'm happy to take any questions if there are any.
In the examples, so the bugs you found in the specs, I mean, did those end up actually, were the specs just too weak, or did it also turn out that the implementations had bugs because of the too weak specs?
So there was a mix. I would say most of those cases, we found that the specification was too weak, but the actual system was correct.
Okay.
There were 2 cases where the system was too weak and that bug translated. But for the most case, it was just a under specification, either because they missed it, they didn't think it was necessarily important, but a different implementation could have contained some bad behavior. But yeah, there were a few, and then there was one example of finding a specification that was too strong. So there was an example of a specification for a QBFT protocol where the authors specified the adversary behavior, but it was too restrictive, we found. And by weakening it to be what we thought was a correct behavior for the adversary, we found that the proof actually broke. And then we went through the efforts of fixing the proof to see what was actually going on. But in terms of either case, I guess I would say that the examples that I talked about with the mutation testing looking for too weak specifications, it also works the other way. Let's say I want to test the preconditions to make certain the preconditions of a method are not too strong, or in this case, an adversary is overly restricted. You could still apply the mutation framework just with a different parameters.
Okay, if there are no other questions, let's thank Eli and.
How do we go for screen? Oh, I got it.
Okay, so now we have the talk promised earlier from Cassidy. So thank you, Cassidy.
Yeah. Thank you. I'm really glad that worked. All right, so I'm going to be talking about a really similar problem that I've been working on. Called verifying Daphne contract integrity. So the goal of this work, we leverage Daphne's backend to detect issues and provide feedback to improve contract integrity. And contract integrity we define as, well, first let me say, Daphne proves, so I guess the issue with proofs in Daphne sometimes is that, and this was mentioned a little bit before, is that our proofs are only as good as our contracts. So Daphne is going to prove that an implementation is a safe substitution for a contract. It's never really looking at that implementation in a method. And so we need to know that our contracts are good, and it's hard to write correct specifications. So integrity in this work means that the contract is free of these 4 common pitfalls that I've run into a lot and that I've seen other people working in Daphne run into. Contradiction, vacuity, unconstrained outputs, and redundancy. So I'll get into what each of those means. First, I want to mention a little bit of related work. So the biggest thing is the Daphne 4.4, so the most recent version, has some really cool stuff that's really related to this as well. So in Daphne 4.4, it has the ability to detect when a part of a contract is not used in the proof. So it has the ability, it looks at the proof and the SMT unsatisfiable cores and is able to say, hey, you didn't use this specific part of the specification in the proof, and so it's doesn't need to be there. It also has the ability to find contradiction in the specification and also with regards to the specification and the implementation and how they interact. So I want to say that my work is a little bit different from this in that I'm not looking at the implementation at all. So this is kind of looking at this from a contract-driven development point of view. This tool, you can look at purely the specification. So that's where those differ a little bit. Maybe they have a little bit different use cases. And then there were some other related work I drew from that I'll skip over for the sake of time. So let's go into these pitfalls. We have contradiction. So a really simple example, a contradiction in your specification is when you have a clause that cannot be true. So for example, I don't think anybody would ever write this, but for the sake of example, we want to require that A is not equal to B and also that A is equal to B. Obviously, that can never be true. So how do we detect that? What we do is we generate an assertion that in Daphne that we can then have Daphne send back to Boogie in Z3 and tell us whether or not we have a contradiction. So the assertion for this one would be we'd negate the clause, and if it proves out, meaning that the negation is always true, then we know that the original clause can never be true. So we know we have a contradiction. Vacuity is the opposite of contradiction, something that will always be true no matter what. I can't think of a case where you would want to write a specification that's always going to be true. You're always trying to constrain something and say something interesting. And the case where I'd say is the most common that I've seen is where you have an implication with a false left-hand side. So if it's false on the left-hand side, you can prove anything. So this is vacuously true, always going to be true no matter what. The way that we detect something like this is even easier. We just assert that clause. If it proves out, then we know that it's always going to be true. And obviously this is a super simple example, but you can run into this really easily, at least I have a lot, where I write something that I think is not a contradiction on the left-hand side of an implication, and it is. And then everything proves out, and I think everything's great, and it's not. So that's always really sad. So that's kind of motivated me looking into this. Okay, so then unconstrained outputs. The last talk talked a little bit about this. The idea is that if you're specifying something about, say, a method, and you have an output, you want to know what's going to happen to that output. And so you don't want to write a spec and then, you don't even know, your spec isn't even saying anything about what the output is, or maybe it's not fully saying what's happening. So the way that I kind of looked at this was I said, okay, there are cases of the amount that an output is constrained. So we could have a case where, let's say we have an output x from a method, and we just say x is always equal to 5. Great, then we know it's fully constrained. We know that we are, we know what x is going to be. Then a really bad case is you don't even mention x in your ensures clauses, and obviously you know nothing about x. And then the trickiest and probably most common example of where you can have unconstrained output is where you constrain an output in some ways, but not necessarily in all ways. So maybe you have a conditional that tells you what it's going to be in this case, but you forget to constrain it everywhere. So I'll give a little example of what I mean by that. So we have this method, unconstrained. It takes in 2 integers and returns result, another integer. And if we look at these ensures clauses, we have if A is greater than B, then our output result gets set to A. And if B is greater than A, our output gets set to B. You might notice that we're missing the case where A is equal to B. And that can be really easy to forget to throw in there. So if we had an implementation associated with this, if we have a case where A is equal to B, we can't say anything about this result. It's not constrained. So we want to be able to detect cases like that. So what we do is, I'll walk through this assert statement. This is the assertion that would get generated in order to detect this. We take our preconditions on the left-hand side of an implication. So we want to say, given these preconditions, and then we want to take each of the conditions that constrains this specific output result, and we want to OR them together. And what this is saying is this, so what we want is this assert statement to be a tautology, always true. In this case, it is not going to be, because we have a counterexample where A is equal to B. So what we're checking for is a tautology where we OR together all of the constraints that tell us something about our result. All right, and then finally, the last pitfall I looked at is redundancy. This is a little bit different. This doesn't necessarily point to an error itself. We don't want clauses in our contract that don't need to be there. That just makes everything more confusing and makes it more error prone. So let's look at this little example. Again, a very simple example. We have A should be equal to 1. A should not be equal to -1, and B should be greater than 0. So A being equal to 1 is a lot stronger than A not being equal to -1. A not being equal to -1 could be any number except for -1. And if we already have this requirement that A is 1, then we don't need that second part. So so to detect this, we want to ask the question, are any of these contract clauses implied by other parts of the contract? So the way that we go through generating assertions for this is we first look at this. Okay, so we're going to take these first two requirements and we say, hey, does A being equal to 1 and A not being equal to 1 imply that B is greater than 0? No, it does not, so that is not redundant, so we're good. The second one, does A being equal to 1 and B being greater than 0 imply that A is not -1? Yes, it does, so this is redundant. So we know that we don't need this clause. And the next one is not redundant. So we're going to generate an assertion for each one of the independent clauses in a contract in order to detect which ones don't need to be there. All right. So I've hinted at this a little bit, but we're leveraging the Daphne backend, and by that I mean, when I first started thinking about this, I thought, I should generate these SMT constraints and pass them in and get them back, and then I realized that Daphne's already doing all this work for me with all of everything in types, and so I am using the SMT solver, but indirectly through Daphne and generating these assertions. And I use Daphne rewriters to generate these assertions. And I want to say thank you to Aaron Toom. I don't know if he's listening right now, but he gave me the idea and showed me Daphne rewriters. So that was very helpful. Okay, so here's an example of kind of what happens. So say we have this specification for binary search. You don't need to try to read through it all. I will point out that there is a problem in the specification. This is under constrained output. So we have the case where R is greater than 0 and the case where R is less than 0, but we are not covering the case where R is equal to 0. So we should be able to detect that we're not fully constraining this output. We run Daphne with the contract integrity option. This is in my branch of Daphne, so if anyone's interested in trying this out, it's right here. And then just to show you a little bit, tiny snippet of the code, so I have this contract integrity rewriter. It's from the rewriter interface that already exists in Daphne. And I'm creating assert statements and inserting them into the original program. So the assert statement that gets generated for this, for detecting this unconstrained output, these were the preconditions of that function, and then we check that they imply the conditions that constrain the output. Obviously, this is not going to work because R could be 0, and then we know that we have unconstrained output. So in the report, we get this nice little report that tells us that the test of unconstrained for our output R in the binary search method failed. So again, that doesn't necessarily mean that there was, maybe you didn't mean to, maybe you were okay with it being under constrained, but again, it'll just let you know that you don't have this output fully constrained. Okay, so I've tested this tool on quite a few Daphne programs. So I'll just walk through this table a little bit. This is the number of contracts in each one of these, well, the number of methods in each one of these files, then the number of requires clauses and ensures clauses. This average length of contract clause is just the number of words in each clause. And that was just to try to give an idea of the complexity, how long these are. But a better way would just be to look at the examples, which are available on our BYU Daphne stuff. And then if there were any errors in the report, got those, and then the issues that were detected. So this very first one was just me making up all the ideas that I could think of issues that you could run into. It detected all of them. That's good, because that's what I was testing it on. And then these 5 files are just some examples of the ones that I ran it on. These had been pretty heavily tested, and they have implementations, and it still detected some issues with unconstrained output and redundancy in a few of these. It didn't detect any contradiction or vacuity, and I would say that's because these were already really well tested. They have implementations, and that's something that we probably would have found along the way. But had we been writing specifications from the start, we definitely ran into contradiction and things like that. And then one more thing I want to point out is this tool does not work for all types of contracts. So in this last one, we had some things that were not correct, and I'll go into what it does not handle correctly. So it handles pretty much, well, everything that I've tested, it's handled correctly. And then the biggest thorn in my side working on this is that it does not work for existential quantification. So if I try to say there exists something and it doesn't work. And that is a problem because a lot of Daphne contracts have universal quantification, and because I'm negating these clauses with universal quantification, that turns into an existential quantification clause, and then Daphne isn't able to find me that witness. And then the old keyword is less of an issue. I just need to, that's more engineering, I just need to introduce a new variable and the original and another one, 2 variables, so that it can deal with that. So it's mostly existential quantification that is the main problem right now. So yes, future work, figure out some heuristic for dealing with this existential quantification problem. And then other things I want to add. Right now, it tells you that there's an issue, but it doesn't necessarily point you to exactly where it is. So I want to get some more informed feedback for fixing issues. And redundancy, is a little bit rudimentary right now. Just going through and doing an assert statement for each independent clause can be a little bit costly, and I think I could reduce that down better. So yeah, that's all. Thank you, and I'll take questions.
For your thank you. That's cool. For your redundancy, your example showed that you're actually reordering some conjuncts. That may mean that you introduce some well-formedness errors. The one that you showed was A was equal to 1 and A was not equal to -1. But suppose that one of those expressions involved division, then it could be that maybe when one of them appears before the B, maybe the B greater than 0 tries to divide by A. It could be that if you reorder them, that you now would introduce some errors. So my question is, if these assertions that you're producing, if they would cause well-formedness errors, would you flag those as possible errors, or do you just ignore them, or what do you do in those cases?
I think if I ran into a well-formedness error, I would probably toss it out. To be safe, but yeah, I haven't run into that, and I haven't thought about that, so it's good to think about. Thank you.
So you generate these assertions, and then you want the assertions to pass, and if not, you tell the user, hey, there might be something wrong with your specification, right?
Yeah, I mean, either pass or fail, and I interpret what that means. But yes,
right, because I can imagine that the verifier is simply not able to prove the assertion, even though in theory it could be proven, and then you give a false positive to the user. So I also wonder whether you considered flipping it around, so you only give a feedback to the user if you know for sure that there's a problem with the specification, but then you might have false negatives,
right?
So you get the other issue. But like from a user experience perspective, you could weigh those two and sort of figure out which you prefer.
Right. Yeah.
I'm just wondering whether that was whether that idea even makes sense, and whether it's something you consider.
Yeah. Well, let me see if I can rephrase what you're saying. So, are you saying rather than Yeah, sorry. Can you like, do you mean like sometimes I want an assertion to pass and sometimes I want an assertion to fail, and should I just make it all so that they're all supposed to pass or they're all supposed to? Is that what you're saying?
I feel like you're relying on the solver to tell you whether maybe sometimes an output is unconstrained. And if there's a scenario where it is unconstrained, but the solver simply not able to prove it because of the complexity of the expression that you're passing to the solver, then,
I see what
the
you're
user
saying.
might be told, hey, your output may be unconstrained and might be unconstrained. That's actually what you are, if you're being very honest to the user, that's what you say, right? Either you say, well, we're sure it's not unconstrained, or you say it might be unconstrained.
Right,
But
totally.
I guess you could flip that around and go for the option where you say, yes, we know it's unconstrained.
But we might have missed some.
Yeah.
I don't know. I almost would lean towards just reporting everything, just because it's just so that the user can go and look and just maybe have the caveat that maybe there's no issue here, but just take a look.
Yeah.
I don't know. That's kind of what I would lean towards, but
Yeah, and then I guess I wonder if you're telling the user it might be unconstrained, that you really want to give them the option to provide extra proof so the verifier can say, hey, actually it's never unconstrained.
Yes,
But,
and that's kind of where I was saying, like, I maybe point that, yes, there could be an issue. I want to give them a little bit more information of where I'm pulling that from so that they can actually go and easily see if that was an actual problem or not. So.
All right, thank you. It's very cool work.
We have a short break now. Oh, sorry. Let's thank Cassidy again.
Please say yes. Is that right?
Yeah, that's like the second display now.
No, his desktop is extended. If you wanted to do PowerPoint presentations, it makes sense. There you go.
Perfect, thank you.
Excuse me.
Is this not remote to Brazil? Like work around it being called Brazil? So no. Okay. Or Blaze. Blaze is the public one.
I didn't.
This is the Google. I think Blaze maybe it's the other way around. Basil is the public one. Blaze is the.
But the other, I mean, those systems are complete.
Makes sense. Now that I saw the talk, that really good.
Those are great. Yeah.
Bricks. Yeah.
All right, that's easy.
Thank you. Well, thank you for checking.
Hey, yeah, it's well, it's very easy for phonetic English native speakers. Let's give it one more.
Sure. Is all of POPL going to be organized in this building? Or does it
Yes,
extend?
and in fact, this room is going to be used for many POPL talks. So it's not great that Macs cannot work since many of my colleagues use them.
Well, it's good to know about
No,
this
today,
now.
yeah. Okay, maybe we can get started with the last two talks of the day. So please take a seat and prepare yourself for some exciting remaining talks about code generation. The first talk will be by Christopher Bricks, talking about generating verified assembly code using Daphne and reinforcement learning. That's very exciting since I don't think we've heard any AI today, so this will be the first AI. So yeah, thank you.
Great. Thank you very much for the introduction. I'm Christopher, and today I would like to talk about reinforcement learning with Daphne. What I'm going to present was joint work with my supervisor when I did my internship at Amazon in the as an applied scientist intern in the Amazon Web Services team, automated reasoning. Yeah, and John Tristan was my manager back then. And today I would like to talk about the results of that internship. So maybe you noticed a few months ago, last year, there was a paper called Faster Sorting Algorithms discovered using deep reinforcement learning, published in the Nature magazine by Google DeepMind. And there they talked about an algorithm called AlphaDev. And AlphaDev was used to generate assembly code for several tasks. One of them was sorting sequences of integers. And crucially, this AlphaDev algorithm was able to come up with assembly programs that used fewer instructions and had less latency than the prior human benchmark. So they were able to improve this assembly implementation using reinforcement learning. And for my internship, I looked into how we can extend AlphaDev, possibly using Daphne. But before I'm going to talk about Daphne and how it can be used here, let's talk a bit about artificial intelligence and reinforcement learning, because that's kind of the important concept here. So in reinforcement learning, you treat your problem as a game, and then you teach an agent to play this game. So for example, we could say that the game is chess, and we want our agent to learn to play chess. So the agent, in some way, is defined as a function that receives as an input all the information it needs about the current situation of the game. For example, all the locations of the pieces on the chessboard. You could also use the picture of a chessboard with the pieces on it as an input. Then you would have the color values of the pixels in the image as an input. And the agent is then tasked to come up with a move, and we'll eventually use some heuristic, some external oracle to evaluate whether this move is good or not. So in this example here, our agent predicted to move the white knight to capture the opponent's queen, and that's a good move, we decided, so it gets a positive reward. And eventually, the agent collects experience in the game and is able to learn what moves yield a positive reward. So over time, it will come up with a strategy to maximize those rewards. And then we can say that it has learned to master this game. In deep reinforcement learning, the agent is implemented using a neural network. So we have our neural network that receives the current state of the game encoded. And as an output, we predict the next move that the agent wants to perform. But we also predict the reward that the agent expects to receive for this action. And here, the benefit is that we can then we can compare the actual reward that the agent receives with the predicted reward, and eventually the network will be trained such that the agent is able to predict the reward correctly. And at that point, we can use the agent to have a strategy to maximize the rewards that we get. Okay, so this was a very short general introduction to reinforcement learning. But what is AlphaDev in particular? So AlphaDev is a deep reinforcement learning algorithm. And here the game wasn't chess. Instead, it was to generate assembly programs to solve a given task. And in their paper, they focused on sorting sequences of integers, I think up to length 8. Here for this example, I picked the task of reversing a list of 4 integers. You can basically insert any task that you're interested in. Now, because we've changed the game, the input of our program changed. We can also see this in the formal definition of our agent. It's no longer the pieces of a chessboard. Now it's a partial program as well as exemplary memory and register values. So what does that mean? The idea of our game here is that we'll start with an empty program, and then a move in our game consists of adding a new instruction. So in the second move, you already have a partial program that has one instruction, and you'll append a second instruction. And you keep on appending new instructions until eventually you've solved the given task. So here the current program already consists of 2 instructions. And then we also have a snapshot of the current memory and register values. And that just means that we've randomly sampled a possible input that our program could receive, and we've executed the partial program on this input. And this isn't strictly necessary, but it helps the agent to reason about how the individual instructions modify the state of the machine, so it's able to learn faster and generate code programs easier. As before, in the chess example, the agent now has to predict a move. Here the move is a new instruction that should be appended to the program. An external oracle decides that this was a neutral move. There's no reward. We append the instruction to our partial program, and we repeat this process. So now the input has been updated. The agent predicts a new output, a new instruction, and this time there's a reward, because in this situation we have partially solved the task. Okay, so again, over time, the agent will learn what kind of moves and what kind of sequence of moves yield positive rewards, and will favor those, and over time generate very efficient programs, because moves that receive negative rewards or neutral rewards are avoided. Okay. In the paper about AlphaDev, the authors highlight one problem, and it's that the generated program generated by the agent isn't known to be correct. It could have a bug in it. And to make sure that the generated code is correct, they test it, and they do that exhaustively. So for sorting sequences of integers up to length 8, you can just enumerate all possible input permutations. And you can prune away most of them because lots of input permutations are actually equivalent. If you restrict your operations you can perform on this list sufficiently. But still, as you increase the length of your sequence, the number of test cases that you have to run through increases exponentially. And you can see this here in this plot. Testing eventually becomes infeasible. So this was kind of the motivation why we wanted to integrate Daphne in this pipeline. Okay, so the proposed solution here is to use Daphne, because using Daphne we can have a problem specification written in Daphne. We can then use reinforcement learning and eventually receive assembly code that's not just tested to be correct, but actually verified to be correct. Okay, so how can this be done? And the way we did this was to provide Daphne with some code to allow it to reason about how each individual assembly instruction would change the state of a machine that executes this code. So first we start with an enumeration of all the assembly instructions that we want to support. So here this is a subset. For example, we want to support moving a value from memory to a register. We want to have comparisons between two registers, and we want to have conditional move operations dependent on the prior result of the comparison. This is just the enumeration of all the instructions we want to support. And then we have some logic that defines the state of a machine that would execute this code. So here we have a list of all the memory and register locations. We would also list the flags that are used for the comparisons and so on. Based on the state of a machine, we can then define how the state can be mutated. So for example, we can write to register, and that means that the respective register location is updated, the state changes, and now we store the updated value in this location. And we'll have similar functions for writing to a memory cell, writing to a flag, and of course also reading from all of those locations. Finally, here in this block of code, we need to map from our instructions that we want to support to a sequence of read and write operations on our state. For example, if we want to move a value from memory to a register, we first have to read that memory location, and then the resulting value is written to a register, and the state is being updated. And we write this mapping for all of the instructions that we've defined in the beginning. This is a little bit of work, but you only need to do it once, and you only need to update it if you increase the set of assembly instructions that you want to support. Then we write down the property that we want to verify for the assembly program. So, for example, if you want to swap the order of a sequence of 4 integers, then we could write down that, yeah, the input and the output both have length of 4, and the output is in the reverse order compared to the input. Then we task our reinforcement learning agent with generating code for this. And whenever we have a new updated partial program that we now need to test to evaluate whether the task is solved or whether we need to continue with this game, then we translate this generated assembly code to something Daphne can parse. And this can be done automatically. So there's a clear one-to-one mapping between the assembly instructions generated by the agent and the instructions we defined at the beginning. So moving a value from memory to register and so on. And we just list, here on the right, we list all those instructions in sequence, and then task Daphne to verify that when these instructions in this sequence are executed, then yeah, our property does in fact hold. Okay. Yeah, in the scope of my internship, I didn't get to look into the more complicated problems that the AlphaDev paper explored. I mainly focused on a simpler problem of swapping list of integers to keep the reinforcement learning aspect of this problem simple. But just for this problem, if we limit ourselves to a very small subset of assembly instructions of 32 possible instructions, then we have about 2 million possible programs that could be generated by permutating those instructions in different orders. And this 2 million already includes that we've pruned away many different programs that just don't make any sense syntactically. If we now perform reinforcement learning on this problem, we can see that initially, so if you look at the yellow line here, Initially, at the beginning, none of the generated programs are correct. But then, after let's say about 20 minutes and about 250,000 generated programs, the agent generates a correct program for the first time and then rapidly starts to generate those all the time. And crucially here, of course, we have not needed to enumerate all the different programs and verify all of them, but the agent was able to learn to generate a correct program faster than just enumerating all different possibilities. Of course, if you do reinforcement learning, performance is very important. So there are some tricks that you can apply. It's very important to generate games as fast as possible, so you've got lots of data to learn from. So we didn't perform the verification of the generated partial programs on the same machine. We moved that to the cloud. If your verification process takes any significant amount of time, then we can keep generating new games while in the background in the cloud the already generated programs are verified. And of course, we are doing machine learning, so we're using GPUs to parallelize our data generation. So we are not playing a single game at any given point. We are really generating like 512 different games at any given point in time. So if you take all of that together, then we've got thousands of games being played at any given time. And then there's a second possible improvement here. So there's no need to rely on Daphne for verification all of the time. So if we have a partial program and the verification fails, then Daphne can provide us with a counterexample. And if you keep track of this counterexample, then there's a high likelihood that if we append one instruction to this current partial program, then probably the program will still fail on this prior counterexample. Of course, eventually we hope that it will successfully run, but the likelihood that it still fails is high. So if we can keep track of this prior counterexample, we can first test it, just like the original AlphaDev algorithm did, before going to Daphne and verify only if the test cases have passed. Yeah, that of course reduces the runtime and allows us to generate games even faster. Okay, so in a comparison, if we are just using AlphaDev, then we would show the correctness of the generated assembly programs using tests. And if we are using Daphne, then we can now prove the correctness. And if we want to improve the performance further, then we can combine testing and verification and test in those situations where we have a hunch which possible inputs might constitute counterexamples. Daphne uses an enumeration of all possible inputs. That's not feasible for problems where the input space is large. And this is where Daphne can shine and verify the problem for all possible inputs. Because we can combine testing and verification for small tasks, basically we fall back to the original implementation and can solve this fast. And for large tasks, as I said, AlphaDev might not be applicable, but in the combination, this could now be solved. Okay, with that I conclude and take any questions.
Hi, so you use 32-bit data, and you said if you had to take the combinatorial space, it would be like 2 million. So if we did 64-bit, it would be much more greater. But as you're considering machine learning, would it still take same amount of time in your method if we instead took 64 bits?
So the okay. So it's just to clear up possible confusion. It's not necessarily bits. It's possible instructions. So okay. the number of assembly instructions that we wanted to support just happened to be 32.
Sorry. My question was like if you consider the data to be instead of 8-bit. If you made it 16-bit, would there be a difference in time in your case?
So Daphne might have a harder time verifying this if we are actually verifying it on the bit level. So yeah, then basically if we go to this slide here, then the block where we do the verification, that might take longer. And that, of course, stretches the amount of time that any given game takes. So we'll then have more games running in parallel. The throughput would be the same, but the learning process would be a bit slower. Yeah.
Okay, thanks.
You mentioned that in the machine learning, it gives a reward based on the program. And sometimes, even if it doesn't do the complete correct thing yet, you can already give a positive reward if it does a partially correct thing. So I guess you have some sort of clever evaluation function. I'm wondering, in the Daphne approach, where you have a specification to check whether the program is correct, would there be a way to also give this give a reward for a partially correct program by somehow being clever with the specification?
I think there are ways to do this in a clever way. I did it in the stupid way of handwriting simpler properties. So if we are interested in reversing the order, then I also specified properties that the first index now has the value that previously was at the last index, and that the second index now has the value of the second to last prior index. You need to, with my implementation, you need to do this by hand, but it would be very interesting to come up with a solution to do this in a clever way.
I can think of something that's probably very stupid, but just an idea, which would be to sort of see how much difficulty the solver has with proving that the program is incorrect. Whether it immediately finds the counterexample or whether it would be a complicated one, something like that.
Yeah, that might be possible, yeah.
Okay, let's thank Christopher then, and yes, let's try this. Okay, so our last talk is going to be from Chuyu Sun, who's going to tell us about Clover, which stands for Closed Loop Verifiable Code Generation. Okay. Maybe you can try. Oh, yes, it's on there. We can see. Yeah. Oh, now if you hit play, maybe. Oh, no, it doesn't go.
I think it's up. Move up. Move up.
Or maybe you go into display options. You can try to mirror the display or something. It's also
Oh. Maybe it's down. Yes, it was below. Okay. And then you can move your notes, I guess, over. The other way, I suppose.
Up.
Yeah. Okay. Oh. Let's be content with this. Yeah. Okay. Thank you, Chuyu, and take it away.
Okay, cool. Hi everyone. My name is Livia. I'm a second-year CS PhD student in Stanford, and I am advised by Clark Barrett. Today I'm going to talk about our work, closed-loop verifiable code generation. This is joint work with Induction and O'Day Patton. So some outline for today. I'm going to begin my talk by introducing the motivation and some background for this work. And then I'm going to introduce the data set we create for this work. And Next, I'm going to talk about specifically how our framework Clover works. Next, I'm going to show you how the experiments demonstrate the feasibility of our framework. And to conclude, I will talk about some discussion about the limitations and future work. So I hope this has not become a cliche yet, but I will start my talk by talking about large language model. So LLM has recently demonstrated remarkable capabilities in many applications. And among the many possibilities, their ability to synthesize code from natural language doctrine is stunning. This means that we could potentially be walking into a future where it could potentially enhance the productivities of programmers significantly. So this brings up the natural question, how can we trust the generated code? Formal verification provides mathematically rigorous guarantees on the correctness of code. What if there were a way to automatically apply formal verification to the generated code? This would not only provide a scalable solution, it could also lead to a future in which the generated code is more reliable than human written code. Currently, formal verification is only possible with the aid of time-consuming human expertise. The main hypothesis of Clover is that LLMs are well positioned to generate the collateral needed for formal verification to succeed. Now, how exactly do we do formal verification? First, we construct a mathematical model of the system, and then we provide a formal specification. And finally, we prove that the model satisfies the spec. Right now, step 1 and 3 are pretty much optimized, but traditionally, step 2, it requires significant human expertise to ensure the spec's correctness. There are two key insights moving forward. The first one is that it's simply a shift in perspective. And the result of any AI-based code generation technique should aim not only generate code, but also formal specification with a natural language doctrine. The second insight is that given these components, we can then use formal tools coupled with generative AI techniques to ensure that they are all consistent. So our contribution, Clover proposed a solution for a trustworthy code generation in which we reduce the problem of checking code correctness to checking consistency among code, annotation, and docstring. Second, we also introduced a new dataset called Clover Bench, in which we introduced 60 handcrafted Daphne examples with docstrings. And finally, we conducted an evaluation of the Clover framework using GPT-4 and Daphne. And our results show that GPT-4 understands Daphne, at least at our dataset level. And then the consistency checks are pretty promising, in which we show that with 10 independent tries, we are able to accept 87 of the ground truth examples. So we name our approach Clover, short for closed-loop verifiable code generation. And we predict that Clover, coupled with steadily improving generative AI and formal tools, will enable a future in which the automatic scalable generation of formally verifiable code is possible. There are two phases of the Clover paradigm. In the first generation phase, some process is needed to create the code annotated with a formal specification accompanied by a natural language doctrine. In the second verification phase, a series of consistent checks are applied to the code annotation doctrine. The Clover hypothesis is that if all of the 6 consistency checks pass, then first, the code is functionally correct with respect to the annotation. And second, the annotation captures the full functionality of the code. And third, the docstring also accurately reflects the functionality of the code. The idea is that we can unleash the powerful generative AI technique in the generation phase and then use the verification phase as a strong filter that only approves of the formally verified, accurately documented, and internally consistent code. There have been many popular datasets for code generation in different domains, but none contain annotation or use the Daphne language. We want to carefully curate the program used to test our first prototype. So for these reasons, we introduced a new handcrafted dataset called Clover bench. We expect to add and improve it over time. Currently, it has 60 small handwritten Daphne examples that you might find in standard CS textbook in standard CS intro textbooks. We are also working on adding support for other verification frameworks and languages such as Virus and Rust. For each program, there are 4 variants. The first one is the ground truth variant, whose code annotation and doctrine are all consistent. There are also 3 incorrect variants where we either mutate the code doctrine or the annotation. Associated with each example, there is a set of unit tests. As an example, you see here, this is a fully annotated ground truth Daphne examples. Let's take a closer look at how Clover works. Clover expects the output of the generation phase to contain 3 components: code, annotation, and docstring. The verification phase checks the consistency of every pair of the component and succeeds only if all checks pass. One key idea used to check the consistency between components is reconstruction testing. Given these 3 components as input, we try to reconstruct one single component from one other single component out of the 3. And the check only passes if the reconstructed component is equivalent to the original one. We do this for 5 out of the 6 directed edges. One special case is checking that the code conforms to the annotation, in which we use deductive verification tools. And in our case, we use Daphne. So the annotation soundness edge, a deductive verification tool, is used to check that the code satisfies the annotation. The annotation completeness edge, given the annotation, we use an LM to generate new code, and then we check that the generated code is equivalent to the original one using unit tests. For anode to doc edge, an LM is asked to generate a new docstring from the annotation, and then the 2 docstring are checked for semantic equivalence using an LM. For the doc to anode edge, we generate a new set of annotations from the original docstring, and then we use the verifier to verify that the 2 set of annotations are equivalent. For the doc to code edge, an LM is asked to generate a new code, and the unit test is used to check for 2 code equivalence. Finally, for the doc to code edge, the new docstring is generated by an LM, and then also the same LM is asked to check if the 2 docstrings are semantically equivalent. For the experiments, the first question we wish to answer is, can GPT-4 generate reasonably good Daphne code and annotation? Recall the integer square root example that you saw earlier. So if we use this as an input to an GPT-4 and we ask it to generate a full set of annotations, it's actually able to succeed in one try. The example you see on the right, it can pass the Daphne verifier. For a more complicated example, such as this one, it's checking if all the characters in a string are digits. If we use this one as input, For the first try, GPT-4 gives a syntactically wrong answer. But if we feedback the Daphne compiler feedback, it's actually able to fix itself. And what you see here is correct and verified by Daphne. For even more complicated examples, such as this one, this is saying that we return a new array that contains only the even numbers of the input array. It's unable to get it under 3 tries. But just for reference, this is a fully annotated version of the function that you just saw. It's I think it's unreasonable to expect GPT-4 to return this answer. So to conclude, can GPT-4 generate good Daphne code and annotation? Although not perfect, out of the box, GPT-4 can produce some correct annotations for the majority of programs in our simple set of configurations. This suggests that using LM for specification generation is feasible, and we expect that further efforts in this direction, including fine-tuning for specific tasks, will likely lead to even stronger capabilities. So as mentioned before, each program in our dataset, we created 3 incorrect variants. For the first one, we mutate the annotation and keep the docstring code the same. For the second one, we mutate the docstring. And for the last one, we keep the docstring the same, but we mutate the annotation and the code in a way that the Daphne verifier still pass, but it's inconsistent with the docstring. And our main experiments will evaluate the capabilities of the Clover consistency checking algorithm. For each example in the Clover bench, we run all 6 consistency checks using 3 tries with maximum feedback from Daphne verifier or compiler wherever possible. We also evaluated the effect of multiple independent runs, meaning that we repeat each of the 6 checks the number of k times. If any of the k attempts succeed, we consider the check to pass. We see that when k equals 10, it has 87 acceptance rates for the correct one, and we maintain 100 rejection rate for the wrong variant. So this table shows the result of 6 checks for each wrong category. We observe that the doc2NO has the highest rejection rate. This is because the annotation equivalence checking is very strong because we use the Daphne verifier, and this will guarantee that only logical equivalent annotations are accepted. Overall, there are no false positives. Of course, there are still many limitations to the framework. Firstly, the capabilities of LM can still be improved. And right now, our annotation only specifies functional properties. This means that we cannot enforce any implementation detail checking or to check if a particular kind of optimization still passes the functional correctness. Also, there could be a case where the LM is internally consistent, but it's misaligned with human intention. For example, because the natural language is ambiguous, the LM could have a different understanding of the property with what we understand. Finally, right now the Clover bench only contains very small self-contained examples. This means that we have not yet proved the Clover bench's capabilities on larger code base, where it includes some intra-procedure calls and multiple layers of function calls. So to conclude, we introduced Clover, which reduced the problem of checking generated code correctness to consistency. And we also introduced a new data set that features 60 textbook algorithms written in Daphne. And after performing our consistency checking on the data set, we see that it's pretty promising with a 87 acceptance rate for the correct one and perfect rejection rate for incorrect examples. For the future work, we believe that better verification tools, improved LM generation capabilities, and better equivalence checking can all improve the performance of the Clover framework. We also plan to scale to larger code base. This means that we will extend our framework to verify intra-procedure calls and also extend our context window for verifying function calls. Thank you. This is my talk for today.
You mentioned the LLM can sometimes generate a better program after you give it feedback from the compiler about an error in a previously generated program. I'm wondering, since we're working with verification, you could also provide a counterexample for an incorrect program and pass that back to the LLM to tell it, hey, this is the sample for which the program is incorrect. Do you think that could help the generation?
Yes, definitely. I think any kind of feedback will be helpful. But in a case of Daphne, because the counterexample it provides, it's not even very readable by humans. So LM has an even worse understanding of the problem. So I think right now the capabilities of LM it's only good enough to understand simple compiler feedback, where you directly tell it where the problem is. And the problem with counterexample is that it involves some logical reasoning, so I don't think right now it's able to guide it to fix itself.
Okay, thanks.
Am I understanding correctly that Clover Bench, the programs in it is the program text, but without the specifications?
It has it has all degrees of annotated programs.
Okay.
So the most detailed one, it has docstring, full annotation, and the code.
And when you run your tool to generate things, have you ever tried to generate the code instead of that is keep the specifications and generate the code instead of the example you showed?
Yeah, here. So yes, we did try code generation. It's actually
okay, great.
It's actually easier than annotation generation. So here you see that the code generation, it has a higher pass rate than annotation.
Oh, great. Thanks.
Hi, so it's a two-part question. So how large are the programs, and have you studied if there is any correlation with like increasing number of lines of code or variable count with success rate?
So for a Clover Bench, it's around 10 to 30 lines of code. And definitely, I think because of many reasons, including like LM parse window for a context, and its ability to understand things, with the increase of line of code, the capability dramatically drops. So I think if the success rate will be very low after 50 lines of code, if it's a non-contaminated example.
Like instead of lines of code, we can increase the number of variables by trying to keep the lines of code similar, or increase the number of nonlinear operations or something like that, and see if that causes difference in success rates.
I think with LM, it's more a problem of has it seen the example before. So if even if it's a very complex example, but a very classical one with many nonlinear operations, it's able to give back very good answer.
So for things that are protocols and stuff which have never been verified yet, so for that it will probably not work.
I think for protocols very specific to policies, then it's not able to give very good answers as the complexity increases.
Thanks.
Okay, let's thank the speaker again. Daphne workshop. Thank you very much for your participation. Hopefully we'll do one of these again in the future. And since it's been the first one, of course, we're very happy to hear your feedback. If you'd like to share it with us as organizers and the steering committee, suggestions about talks to solicit, format, anything, that would be wonderful. one quick note is that a couple of people are planning to go to a pub that's nearby. It's called the Coal Hole, and they're planning to meet at 6:45. It's basically right across the street from the conference hotel. If you can't remember the name of it, we've added a social tab to the Daphne conference website, so you can double check there. Am I missing? Oh, okay.
Please go to downstairs to the clock room because it will close soon. If you want to get your stuff back, please gently go to get your stuff. Thank you very much for that.
Okay, thank you.